outside and the softer inside, like the marrow on chicken leg, So those two parts of your bone, they go away and come back at different rates, and we were finding astronauts were coming home with less dense bones. So we developed a chemical therapy, some medications that they can take. But the biggest thing is we changed our exercises. We have a machine that's like a big weight machine, and you got to lift heavy. Right before you come home for landing, you are lifting heavy weights, up to 600 pounds, and it's a vacuum tube because there's no weight in microgravity. But you've got this weight protocol and a running protocol. We actually started sprinting because they found that the heel strike helps your bones to stay more dense. Well, guess who really cares about that? Half of the world's population, women, osteoporosis. Yeah, so that research is going on right now, but I can guarantee you those things are being fed.
Types of cultural heritage monitoring, not only to detect signs of human activity, but also to understand the impact of natural events. For example, observation can be used to monitor environmental degradation affecting cultural heritage sites due such as to climate change. It can be used to monitor the effects of natural disasters such as fires, floods, hurricanes and earthquakes, providing support to the entire disaster life cycle, from early warning to rapid mapping to post-disaster analysis and damage assessment. Another example where Earth observation can be used to support cultural heritage monitoring is in the assessment of the structural integrity of cultural heritage sites. This can be achieved using synthetic aperture radar, such as that provided by the Copernicus Sentinel-1 mission, to detect centimetric, even up to millimetric scale displacement, such as due to subsidence.
How can a satellite orbiting hundreds of kilometers above Earth detect changes on the ground at the scale of millimeters?
A satellite orbiting hundreds of kilometers above the Earth may carry a radar instrument which sends microwave signals to the ground and measures the return reflected from the Earth. Very precise measurements of displacement can be made by comparing the phase between two signals. We can see, for example, that over the city of Rome, certain particularly more recent buildings suffer from subsidence due to their location on unconsolidated alluvial sediments of the Tiber Basin.
Satellite data are essential for monitoring our cultural and natural heritage worldwide, helping to preserve the irreplaceable archaeological record for future generations. And the Copernicus Sentinels are fundamental in this respect.
Neighbor to Earth. Presently the focus of man's greatest scientific adventure, the first celestial body that will be explored by man. Landing men on the moon will be a truly great achievement, but only the beginning of a new era in space exploration. No one can predict the exact missions that will follow in the years and decades ahead. But the most exciting possibilities will require the acceleration and deceleration of very heavy loads, such as the maneuvering of large Earth-orbiting spacecraft. The transportation of large amounts of equipment and supplies to the lunar surface. And the sending of heavy spacecraft to the planets. Today's missions are being accomplished with rockets that burn chemical fuels. But chemical fuels are heavy and the cost of putting each pound into Earth orbit is very high. Nuclear rockets, when perfected, can provide the same propulsion energy with less overall weight. They will expand our ability to explore space. This is the story. This is Saturn V, the most powerful launch vehicle being built by the United States. A three-stage rocket that will place the Apollo spacecraft in the vicinity of the moon. The total weight of Saturn V is about 6 million pounds. Its three stages have chemical engines that burn fuel to generate thrust. The first and second stages provide most of the energy needed to put the third stage and the payload, about 250,000 pounds, into Earth orbit. At present, only chemical rockets can provide the high thrust needed to do this job. The third stage accelerates the payload to the velocity needed to get it to its destination. Here, travel time and payload weight are determined by the efficiency with which the propellant is converted into thrust. By substituting a nuclear third stage for Saturn V, the velocity of a given payload can be greatly increased, cutting travel time for some missions in half. This is particularly important in sending deep space probes to Jupiter and beyond. Or if shortening travel time is not essential, propellant weight can be traded off for an increased payload weight. This is important for a lunar supply mission, Earth orbital operations, and some unmanned missions to the planets. Why is the nuclear rocket so much better than the chemical rocket? In rocket propulsion, exhaust velocity determines propulsion efficiency. At a given temperature, the lighter the exhaust gas, the higher the exhaust velocity. And the higher the exhaust velocity, the more thrust is generated for each pound of propellant consumed per second. The nuclear rocket merely heats hydrogen, the lightest element of all, and expels it at tremendous velocity. Chemical rockets burn fuel to produce exhaust gases that contain heavier elements. So at the same exhaust temperature, the exhaust velocity is much lower, and each pound consumed per second produces less thrust. Rocket efficiency is stated in seconds of specific impulse. This refers to the time in seconds that 1 pound of propellant will deliver 1 pound of thrust. The higher the seconds of specific impulse, the greater the propellant economy. Our best chemical rockets of today are limited to a specific impulse of about 450 seconds, and only slight improvement can be expected. On the other hand, full-scale nuclear reactor tests have achieved 800 seconds, and laboratory tests promise even more, perhaps as much as 900 seconds. This means the nuclear rocket, with its lightweight, high-velocity exhaust, will use propellant about twice as efficiently as chemical rockets. This, then, is the principal advantage of nuclear propulsion.
It was at the AEC's Los Alamos Scientific Laboratory, high in the mountains of New Mexico, that the first steps were taken. Here, in the mid-1950s, scientists set about to determine if nuclear energy really could be used to provide rocket propulsion. Theoretical studies and early experimental work revealed many problems that would have to be solved. Problems in reactor design, material, radiation, structures, control, to name but a few. The nuclear rocket was found to be feasible. A series of experimental reactors was planned to convert theory into workable hardware. Optimum reactor designs were worked out by analysis. Prototypes were built. A comprehensive test program was started. These reactors, called Kiwi, were to be used to prove out design and operational concepts. They would be built only for ground testing. All Kiwi power tests took place at the Nuclear Rocket Development Station at Jackass Flats, Nevada. Here in the desert, scientists and engineers checked the actual performance at various power levels and for various time periods. Each experimental Kiwi reactor was received in sections, assembled and checked out in a special reactor maintenance, assembly, and disassembly building called simply RMAD. When the reactor was ready for testing, it was placed nozzle up on a special rail car and delivered to the test stand a mile or so away. This car could be controlled from a remote station. Liquid hydrogen from nearby storage tanks was pumped through the reactor. First tests were begun in 1959 and were run to the 100 megawatt level, about 1/10 of Kiwi's ultimate goal of 1,000 megawatts. Later tests, beginning in 1962, operated at the full 1,000 megawatts. Films of these early tests show the flaming torch on the test stand that burns off the hydrogen exhaust gas and prevents an explosion hazard to the test facilities. Upon completion of these tests, each reactor, by then radioactive, was transported by remote control back to the RMAD building for disassembly and inspection. Here, men working behind shielded walls used remote-controlled manipulators to remove the components for careful checking and analysis. Each test firing added information that helped scientists evaluate the reactor's performance and enabled them to make adjustments and corrections before the next reactor was assembled. But not all tests showed perfect performance. In this one, for example, the flashing in the exhaust gas indicated a structural breakup caused by excessive vibration. Extensive redesign and testing were needed to correct the flaw. And in this test, a hydrogen leak caused a fire on the test stand. Again, a correction was made. Each test brought the scientists a little closer to the performance they were seeking. Until finally, in September 1964, the 8th Kiwi reactor was brought up to full power and held for 8 minutes. And a few weeks later, it was restarted and operated at full power for 2.5 minutes. Specific impulse, about 750 seconds. This concluded the Kiwi test series. It had proved that a nuclear reactor could be built that would power a spacecraft.
The next step, already underway, was to develop complete engine technology. This project was called NERVA, Nuclear Engine for Rocket Vehicle Applications. It was to be a combined industry-government effort headed by the Space Nuclear Propulsion Office, a joint NASA and Atomic Energy Commission activity. The principal contractors were to be Aerojet General Corporation and Westinghouse Astro-Nuclear Laboratory. The NERVA technology reactor, given the letter designation NRX, was essentially the same as Kiwi. But now the contractors had to extend its lifetime and put it into an engine configuration. Here is how the nuclear rocket engine will work. The reactor is a solid core, heat exchange type, cylindrical in shape. Fission of uranium atoms in the core is the source of heat. A reflector made of beryllium surrounds the core. The core consists of many graphite elements impregnated with the uranium-235 fuel. The core contains a number of channels running down its length. Hydrogen passing through the channels picks up heat generated by the fission process. The channels are coated with niobium carbide, a material which resists the corrosion that would occur if the hot hydrogen were allowed to come into direct contact with the hot graphite. The hydrogen is stored in a liquid state to achieve the lowest possible volume. The flight model will use about 1/3 of a million gallons for a 30-minute firing. To start the engine, the cold liquid hydrogen at minus 420 degrees Fahrenheit moves through a pump down to the nozzle, through internal passages in the nozzle walls, and back up inside the reactor pressure shell and reflector. This cools the nozzle, the reactor shell, and the reflector, and at the same time warms the hydrogen. The hydrogen then passes through the hot fuel elements where it is heated to about 4,000 degrees Fahrenheit. From there it is expanded through the nozzle to provide thrust. The bleed line carries some of the hot hydrogen back to drive the turbo pump. The whole engine system is amazingly compact for a nuclear power source. The reactor works through fission of uranium-235, which constantly emits nuclear particles called neutrons. When reflected back toward the reactor, these particles will set up a chain reaction, generating terrific heat. The heat is controlled by rotating rods installed in the beryllium reflector around the reactor. The rods are also made of beryllium, but one side is coated with boron, which absorbs neutrons. Initially, the rods are turned so the boron side is toward the fuel elements, and sufficient neutrons are absorbed to prevent nuclear fission from starting. Beryllium reflects neutrons. By turning the beryllium side toward the elements, a point is reached where sufficient neutrons are reflected for fission to begin. The amount of heat produced depends upon the position of the rods. Heat increases as more of the beryllium side turns toward the core. When the desired rate of heat production is reached, the rods are turned back to stabilize it. Heat decreases as the rods are turned back. When the boron side absorbs enough neutrons to halt the fission process, heat is no longer generated. These rods can be operated by remote control.
Test facilities for engine components were built near Sacramento, California. The problem? Get adequate performance with minimum weight. The pump must move huge quantities of liquid hydrogen under pressure at minus 420 degrees Fahrenheit, while the hydrogen-cooled nozzle must expand high-pressure gaseous hydrogen at 4,000 degrees to low pressure. The reactor was designed to meet the structural requirements of ground handling, launch, and spaceflight. In a late 1965 test, it operated intermittently for an hour, including 16 minutes at full power. But in that test, as in all reactor tests before it, the hydrogen had been forced through the reactor by test stand pumping facilities instead of its own turbine-driven pump. In early 1966, the new technology reactor and the chief engine components, including the turbo pump, were assembled for test. It was called a breadboard because they were not arranged as they would be in an actual engine. It would be the first self-starting test, and it was a vital step in the nuclear propulsion concept. This engine test model started perfectly and increased to full power. proving that a nuclear rocket could be started by its own pump. During a 2-month period, it was started and stopped 10 times and operated at different power levels for a total of 110 minutes, 28 minutes at full power. Technology had now advanced to the point where performance limits could be extended. Work was already underway to increase reactor power and operating time. In February 1967, this reactor, the Phoebus 1B, was operated at a power level roughly equivalent to 75,000 pounds of thrust. And in December 1967, this reactor, the NRX A6, was operated at full power for an hour. Also in 1967, a new test stand was completed that would permit a test engine to be fired nozzle down into a vacuum chamber below, at least partially simulating the space environment. In early 1968, the first ground test engine was mounted in the new stand. Its success was a new milestone along the long road leading to a flight engine. Heavy shielding was used in this test engine to protect some of the components from intense radiation. In flight engines, all components will be radiation hardened and less shielding will be needed. These tests will complete the technology for a nuclear rocket engine for application to space missions of the late 1970s and beyond. Its thrust will be approximately 75,000 pounds. For missions that require higher thrust, 2 or more of these engines may be used in a single stage, or several engine stages may be assembled side by side. This versatility will give us the capability to perform a variety of advanced missions.
Someday, a manned trip to Mars and return may become the mission assignment. Exactly how it would be carried out depends upon a number of factors. But here is one way it might be done with nuclear rocket propulsion, using the technology developed for earlier missions. Using several Saturn V launch vehicles, components of the huge spacecraft would be placed into Earth orbit and assembled. Separate nuclear stages might be provided for each major step of the mission. The first stage might consist of 3 clustered rockets for departure from Earth orbit. 2 other nuclear stages consisting of 1 engine each would be used in the vicinity of Mars. The first stage cluster fires to accelerate the spacecraft to the velocity needed to get to Mars in the time that was decided upon, say 200 days. At burnout, the first stage cluster is jettisoned and goes into orbit around the Sun. Mid-course correction is made by chemical rockets. About 200 days later, the space vehicle approaches Mars. There it is slowed down by a single nuclear rocket and enters an orbit around the planet. The used second stage is put into a higher Mars orbit than the space vehicle. A chemically powered module departs for the planet's surface. For the first time, men from Earth will set foot on another planet. For the return trip, the module is lifted by chemical power back into a Mars orbit, where it docks with the main space vehicle. The men transfer to the main craft and jettison the module, leaving it in an orbit around Mars. A third nuclear rocket accelerates the vehicle for the return trip. And it is jettisoned. Again, mid-course correction is made chemically. Just before reaching the vicinity of Earth, the crew transfers to a re-entry vehicle and jettisons the large spacecraft. Chemical rockets slow down the vehicle to re-entry speed, and they are jettisoned. After deceleration through the atmosphere, the re-entry vehicle returns to the Earth's surface by parachute. A trip to Mars and back, for centuries a dream of earthbound men, is now much closer to reality. Of course, there are many, many other problems to be solved before such advanced space missions can be attempted. Life support systems for extended space journeys, for accurate space navigation, communication systems, power supplies, and so forth. But any successful advanced mission must begin with propulsion, the power to get there and back. Lower overall weight, larger payloads, shorter travel time. These are the chief advantages of nuclear propulsion. The technology needed to build a nuclear rocket is well advanced. It will be available when this nation determines its next great objective in space.
Beautiful, Mike, really is.
I'm in first grade and I'm watching Neil Armstrong and Buzz Aldrin dancing around like every other kid who's out there watching this. They want to go do this. This is the coolest thing ever. And I remember asking my dad, what kind of job do I need to have growing up that I can make enough money that I can go fly to the moon? And he goes, well, there's a job out there called being an astronaut. And if you are that, they will pay you to go to the moon. They're going to pay me to go to the moon. Yeah, that's it. I've made my career decision. I'm going to go be an astronaut. I did not think the experience of spaceflight would change me. I hear about these people going having this overview effect, and they come back and what am I going to go experience out there that's going to change who I am? But it made me think about a lot of things. And so for the first part, we all had that part where you're seeing the Earth, and you see yourself next to the Earth, and you feel very tiny next to the Earth. Then you turn the other way, and the Earth seems very tiny compared to the cosmos out there. And so you feel like you're 2 orders of magnitude down in terms of the size of things out there. All of life, all of the history of life, all of your life, and everybody you know is in this little tiny membrane of air that sits on top of this planet. And beyond that membrane of air is this abyss of space. It's just, there's nothing life-giving about it. And that's it. That's all that separates you. And it makes you feel like we're in a very tiny spot out here. As big as the Earth seems, it seems suddenly very, very finite. One of the things that got me one day, we had some time off, and I wanted to go get some pictures of items that had flown up for other people out there. And so I get out there and I crank open all the different panels on the cupola window, and just by dumb luck, we were flying down the spine of New Zealand. So you've got this emerald green island with all the mountains, and you've got the ocean out there as the backdrop for all these photos. And it almost made me forget to take the pictures because I was too busy gawking at New Zealand out of the cupola as we went over it. Going on my very first spacewalk, I looked down, and that was my first mistake because this was the Amazon rainforest beneath me. It's February, I guess it's summertime in the southern hemisphere, so I could see all the way down to the river itself and all the dark green lush jungles, the brown river and all the estuaries flowing into it. I can see this muddy delta going out into the Atlantic Ocean, and I could see the gray and snow-capped peaks of the Andes Mountains all out to the west. And so despite my best intentions, Mother Nature was saying, you will not ignore me, you must pay attention. And I'm just sitting there just gobsmacked back looking at this thing and trying hard to tear myself away. Fortunately, my lead spacewalker, Steve, he just sat there and said, just take your time and take the scene, and you will never see something like this again, ever, so you might as well get the experience now. My advice for humanity is, this is a great place to start, but don't stick around here very long. We have opportunities out there. I forget who it was who said, if humankind was meant to explore the universe, God would have given us a moon. We need to take advantage of that, use that as a leaping pad to get off into other places. Someday we're going to need to be from.
We are working on something that is the cleanest we've ever really attempted to send into space.
Perseverance mission has as its central goal astrobiology and also being the first step in Mars sample return. We're going to collect a suite of samples, about 35 samples, that each weigh about 15 grams.
And the reason we collect those intact samples is that we are the first mission that's part of Mars sample return, and it's our job to collect the samples intact to be brought back to Earth for further analysis.
To better assess the question of, was there life previously on Mars? Inside the belly of the rover sit a number of sample tubes and an entire adaptive caching assembly that is used to help collect these samples.
Extraordinarily complex robotic system. And to make it even more complicated, it has to be super clean. We don't want to have these samples come back from Mars and discover life in them, but then realize, oh, that's life that was in the apparatus when we sent it to Mars.
That was a big challenge for the mission because we were meeting cleanliness standards that no rover mission has ever had to meet before.
The requirements that we have for this mission are extraordinarily challenging.
Once we would go through machining the tube itself, getting all of our protective coatings on there, and then looking at our beautiful tubes, we found carbon contamination in places we were not expecting. So as a team, we all had to really come together and look at the entire manufacturing process, how we're handling these tubes. We had to start polishing the interior board prior to putting on some of our protective coatings.
It meant having to come up with an entirely new technique to clean all of the hardware and demonstrate that the hardware could maintain that cleanliness all the way to Mars.
That's what JPL does. I mean, we discover problems and then we solve them.
Having these very strict controls and this record of how much contamination or how clean these tubes are prior to going to Mars is essential for that return sample science.
Great discoveries require remarkable evidence, and so the cleanliness of the sample tubes and of all of the hardware that's going to be collecting those samples is paramount in making sure that the evidence and that the story and that the discoveries that come from these samples that are brought back are irrefutably Martian.
When considering the possibility of life beyond Earth, we look for three main ingredients. The first one is key elements such as carbon, hydrogen, oxygen, and sulfur. The second is a source of energy. And the third, and perhaps most important, is the existence of liquid water.
Water is a necessary solvent in all chemical reactions that have to do with life. Energy is required to drive these chemical reactions, and organic matter is the material from which all life that we know of is made.
Life as we know it requires liquid water. Scientists believe that life on Earth started in our oceans. Now, through our exploration of the solar system, we've realized that the moons around the giant planets have the right conditions that there could be liquid water underneath their surfaces. So that really sort of expands our whole concept of where you could have a habitat, where we might find life.
Water is fairly common in the universe. We've seen traces of water in large molecular clouds between stars. We've seen traces of water in protoplanetary disks. We've also seen traces of water as water vapor in the atmospheres of giant planets around other stars. And we know that water is in the atmospheres and interiors of our solar system's giant planets. So we know that water is ubiquitous throughout the universe. As far as liquid water, that's a little less common. Earth is the only planet in the solar system where we see liquid water at our surface. Moons such as Enceladus and Europa may have liquid water beneath layers of ice.
We're really expanding our understanding of what makes a place habitable. Instead of just looking for an Earth-like terrestrial planet that's a very specific distance from its star, we're learning that there can be hidden habitats that are underneath icy layers, and they can be a lot further out from the sun.
So we believe icy moons in the solar system actually harbor kilometers-thick oceans underneath their icy surfaces. These icy moons and their subsurface oceans may be some of the best places to search for life elsewhere in our solar system.
Enceladus is one of Saturn's many moons, and it's a very small moon that people tend to kind of ignore because it's so small, about 500 kilometers in diameter. But decades ago, in the 1980s, from ground-based observing, we found out that the location of Enceladus relative to Saturn happened to coincide nicely with Saturn's E-ring. And so we were thinking that Enceladus had something to do with the E-ring particulates, the icy material, but we weren't sure. What we later find from Cassini was that we directly determined that there are indeed plumes jetting out of the south polar region from cracks in the south pole of Enceladus in the crust, and it's dominantly water-rich material, just jetting out into space. And so the way we saw it, Cassini happened to be located where Enceladus was backlit from the sun, and so you saw this curtain of beautiful diffuse material jetting out of the south polar region. Quite breathtaking, actually. Even more, we were able to use the different complements of instruments on board Cassini to go after the chemical composition of the plumes, and that's where things got really interesting. So number one, that's because of liquid water. There's definitely a liquid water reservoir. It's subsurface below the icy crust, but that is there. Number two, the chemical composition of the plumes told us that there's a lot of organics, things that make up amino acid, and things on life that are very interesting. And number three, what we were really looking for is a source of energy. On Enceladus, photons from the sun aren't going to work because you can't penetrate the tens of kilometers of icy crust to get down to where the liquid water reservoir is. But what Enceladus does have is hydrothermal vents. It's very hot into liquid water that has a lot of analogies with the ocean floor, where we have a form of releasing chemical energy via something called serpentinization. And so we think that Enceladus might have that potential to have an energy source being chemical, not sunlight. And so you put all that together, and Enceladus has all the ingredients, or most of what we need for life. That makes it a very astrobiologically interesting object to study.
Europa is one of the largest moons of Jupiter, and we believe that Europa has a subsurface ocean tens to hundreds of kilometers thick. And so this ocean may be one of the best places to search for life in the solar system.
There's been 3 space missions that have provided evidence for Europa harboring liquid water. The first one is Voyager in the late 70s. The second one is the Galileo mission in the late 90s. And most recently Hubble, which detected plume-like emission from hydrogen and oxygen, which is closely related to the existence of water beneath its surface.
These plumes may be directly ejected through cracks in the surface of the moon, and therefore what we're seeing in water vapor plumes is the actual ocean water from the subsurface of the moon.
As these plume particles are ejected to space, solar radiation is going to excite these water particles, creating vibrational modes. Now, these vibrational modes are signatures that can be detected at infrared wavelengths by the Keck Observatory. So we observed Europa on 17 days. What we found is that the majority of observations have no presence of water. However, on one of those days, we detected water. We detected H2O. In the past, Hubble provided indirect measurements of water by detecting hydrogen and oxygen. But now we have directly detected water for the first time.
Both the Webb telescope and the Europa Clipper mission will give us a much more detailed picture of the surface of Europa, its cracks and crevices, detailed pictures of the water vapor, as well as other molecules that may also be emanating from the subsurface of Europa. So both of these missions will give us a great picture of whether Europa is truly habitable.
a moon of Saturn. It's the second largest moon in the solar system, and it is about 2 times larger than Earth's moon and actually bigger than the planet Mercury. And Titan is also interesting. It's the only moon in our solar system with an atmosphere. It's surrounded by sort of an envelope of gaseous nitrogen, just like our own Earth is. Titan was first discovered by telescope observation back in the mid-1600s. The first spacecraft observations were made of Titan during flybys through the outer solar system. That was in the late 70s and in the 80s. But we really were able to explore Titan in depth with the Cassini-Huygens mission. The Huygens probe was dropped into the atmosphere of Titan, and it made measurements of chemistry, and it took images as it fell to the surface, and that was back in 2005. And since then, the Cassini orbiter made over 100 close flybys of Titan.
Cassini, in its design with the different instruments, we purposely were picking instruments that could go into longer wavelengths into the infrared so we could really understand the moon. We were able to basically peel back the layers of Titan to really see what was below, and it was remarkable, very Earth-like.
The landscape is similar to Earth's in many, many ways, but with a little bit of a twist. So on Titan, you can find dunes, you find lakes, there are river channels, the atmosphere is very dense, and you can get clouds and smog, and you even get rain.
We saw winds, we saw seasons, and one really important thing we saw was liquids pooling in the polar regions on the surface, a lot of it.
But because Titan is so cold, those features are all made of very exotic materials compared to what we would find on Earth. So the lakes and the rain are made of liquid methane. The crust that forms the surface of Titan is actually water ice, but it's so cold that it's as hard as rock. And in the atmosphere, we get this organic chemistry that forms large organic molecules and particulates. They fall down to the surface and then behave like dust or like sand does.
So it makes us want to go back to really understand the complex organic environment of that surface and what it means for either past life or maybe future life.
Dragonfly is a mission that was just selected by NASA to fly to Titan and arrive in the mid-2030s. Dragonfly is going to make a whole bunch of measurements to help us understand the environment on Titan and its potential for habitability. We'll be taking measurements of the atmosphere. That includes things like pressure, temperature, winds. We'll probe the surface to try to understand what materials the surface is made out of. We'll also be drilling into the surface to look for the types of organic molecules that are present and to try to see if we can find any examples of compounds that mimic the types of building blocks we know we need for life on Earth. We don't really know how life started on Earth. We don't exactly know what the chemical environment of Earth was like before life started. So with Titan, we have this really unique opportunity. There are times in Titan's past where there could be liquid water on the surface. Impact craters can generate impact melt, and there's a potential for possible cryovolcanism to erupt some liquid water onto the surface. And so we know that there's a rich organic chemistry going on in the atmosphere. We know that's depositing to the surface. If there were times where those organics and the liquid water environments were mixing, then there may be some really interesting chemistry taking place. When you have these processes operating for hundreds of millions of years, how far can they get you down that path of chemical complexity? And can we see reactions and molecules that start to look something like what we think of as essential elements for our biochemistry for life on Earth?
In the future, looking forward as opposed to looking back and thinking about Titan as a chemical laboratory for the prebiotic Earth, I like to look forward thinking about what's going to happen when the sun evolves and warms up and the habitable zone actually moves out to where Titan is. And it will. You have all the organics, you're going to have a source of energy, all we have to do is melt the frozen water, and we're going to have a pool of organics just embedded in liquid. Titan might actually have a chance at that point to harbor life.
So when we think about ocean worlds, it's good to compare them to what we know about Earth. In total proportion, Earth is about 0.1% water. An ocean world is a body that has, in proportion, about 10 times more water than Earth does. And when we think of the TRAPPIST planets, those planets have about 50 times more water in proportion to what Earth does. Ocean Ocean worlds do appear to be common in our galaxy. As far back as the early 2000s, we had astronomers, some of them still here at NASA Goddard, that suggested that we would have ocean worlds orbiting low-mass stars. Recently, we've looked at about 52 exoplanets, and these are low-mass exoplanets, and what we found is of these 52 planets, 1 out of every 4 may be an ocean planet. And when it comes to these ocean planets, over half of them may be ice-covered ocean worlds, and so Enceladus and Europa may serve as small-scale analogs of these planets.
So there are a number of different ways to search for life on planets around other stars, but the key method is the study of the atmospheres. We can search for signs of life, biosignatures we call them, things like oxygen, water vapor, carbon dioxide, even more unusual biosignatures, things like chlorofluorocarbons or other things that are only produced by intelligent life. By looking for these key constituents of planetary atmospheres that signal life, we can discover life forms on other planets that we could never actually visit in our lifetime. So this is very analogous to how we study the atmospheres of moons and planets in our own solar system, and really makes the connection between studying the plumes of Europa and the atmospheres of planets around other stars.
What I would like to see is the definition of a habitable zone expanded. We don't want to keep thinking too narrowed about liquid on the surface, but broaden the scope and really try to embrace other worlds that might seem too far from the host star and frozen out when they really aren't frozen at all. At great depths, they harbor a warm, hydrothermal-driven, liquid water environment.
NASA researchers spend weeks, even months at a time, in remote locations around the world, collecting critical data about Earth's environment. Many studies are done from the air, using NASA's fleet of research aircraft. One such mission is Operation Icebridge, a multi-year study of polar ice conducted by the NASA Airborne Science Program. Icebridge sends NASA's P3 flying laboratory to Greenland and Alaska in the spring to study changing ice conditions in the Arctic. A second aircraft, the NASA DC-8, flies from Punta Arenas in southern Chile in the fall to measure land and sea ice over Antarctica. It takes months of planning to execute a major international mission like Icebridge. Diplomatic clearances, configuring the aircraft with scientific instruments, and finding facilities that can support the people and the airplane itself are just some of the preparations needed for Icebridge to meet its mission requirements and goals.
To deploy to someplace like Chile, we plan a good 6 months before the mission to bring everything together so that once we arrive here, we're ready to execute missions on a daily basis.
Typically a mission director, a mission manager, program manager, we get called different names, will do the site surveys for the location, liaisoning with the government, of the host government to the host airport. That's the real legwork that's done prior, is coming out and making sure that they can house and feed us and take care of the people in the hotels. You name it. There's a lot of little tiny details that can't be overstated.
The biggest logistical challenge for the project as a whole is to set up all of the lab space and the facilities so that the scientists can process their data and make their decisions about which project. Logistics is huge for something like this because we have to make sure we can all support the people in the field as well as the aircraft. So we think a lot about aircraft spares and then little details about the support equipment for the airplane.
Usually on every deployment we're going somewhere, there's at least a group that goes out and scopes it out. A lot of it's done like while we're working other missions, and they will talk with the airfield, set up and tell them what we're going to be doing, and then as they're communicating back with us with what capabilities the airfield has to support us, that way we know what to ship.
For a deployment more than 6,000 miles away in the southern hemisphere, the maintenance crew needs to carry an extensive payload to maintain the DC-8 on site and keep the mission on schedule.
Yeah, we put them right on the side there. Yeah,
More than 13,000 pounds of cargo are packed on the DC-8. Everything from spare tires, parts, and tools to basic comforts of home for the near daily 11-hour research flights over Antarctica.
On a deployment like this, we bring the equipment with us, and we also ship a lot of other things by sea in a big container so that we can keep the airplane moving. It'll come back from a mission. If there's anything wrong that needs to be repaired before the next flight, we have the maintenance crew to support it during the night and get it ready for a mission the following day.
The DC-8 flight operations team works around the clock to support Operation Icebridge, providing ground support for takeoffs and landings, operating the plane on research flights, and making sure sensitive science instruments stay powered up and heated overnight. The airfield is staffed 24 hours a day.
We have a makeup of about 28 people supporting the flight operations down here, and that consists of the pilots, flight engineers, navigators, mission directors, and then the maintenance crew that's split between mechanics and avionics technicians.
The maintenance team often works on tight deadlines to prepare the aircraft for its next deployment. Just 10 days after removing one set of science instruments from a previous mission, the DC-8 is reconfigured for Icebridge. In 3 weeks' time, the plane is transformed into a working science laboratory with a suite of radar and laser instruments and cameras installed throughout the cabin, cargo pit, and fuselage.
Yeah, the unique thing about the DC-8 is that it was modified to accept, at this point, we've got about 100 different instruments that have been integrated into this airframe. And so part of the modifications that were done early on was to make the airplane as versatile as possible. So if you were to look through the airframe, you'd see cutouts in both the bottom of the aircraft and the upper side of the aircraft. And a number of the windows were modified to carry structural loads of instruments being installed as well. So we can look in pretty much every direction there is outside this airplane as we're traveling through the sky.
Once the science instruments are installed, the flight operations team conducts a series of ground checks and instrument test flights over the California desert to make sure the DC-8 is mission ready.
Looks like maybe it's level now. All right, looks like it's a wings level and rock course.
So the reason why we picked these sites over the desert in California is because they have these dry lake beds there, and they are a very flat area that's ideally suited for our purpose. So we can put a GPS receiver on a car and kind of drive around on these flat lake beds, measure them, and then a few days later fly over the same area with the DC-8 and take a measurement from the air, compare the two measurements, and use the data from the ground to calibrate and validate the airborne measurements.
While the aircraft is prepared for the trip to Chile, the science and flight operations teams are required to undergo specialized safety training, regardless of if they've flown on the DC-8 in the past.
Well, for the DC-8, everybody who flies has to go through basically a safety briefing. We go in a little bit more detail because we do more things on our airplanes than commercial airliners do. From our pilots, they go through survival training, water and land, and depending on where they're going, some of them have been through Arctic. All of our crew members, they all have to go to altitude chamber, water survival, land survival, and what we do here is we just build on that and then try and bring anybody else that hasn't had any formal training up to speed so they have at least a working knowledge of the kind of conditions that can happen if something was to go wrong with the aircraft.
Safety equipment tailored for Icebridge is also packed on the DC-8.
Overhead compartments, we've got 20-man life rafts. There's 4 of those on board the aircraft. We have 2 what we call global survival kits, which has different survival items inside of there. For this particular deployment, we also have anti-exposure suits, which if they were to go into the water, we have enough for everybody on board the aircraft for that.
Once the aircraft and passengers are cleared to fly, it's time to pack up for the long transit flight from Armstrong Flight Research Center in California to the southern tip of Chile. The exhausted team gets an opportunity to rest on the overnight journey to Santiago, where a second flight crew is on standby to complete the journey to Punta Arenas.
To get to this part of the globe, it's about 14 hours of flying. We had pre-deployed a crew to Santiago to join the flight at that point so that the crew that flew all night could then step out of the cockpit and rest. And that allowed us to continue on that next day down to Punta Arenas, Chile, without having to stop overnight.
It's a cold and windy welcome at the Punta Arenas Airport, the mission base for Operation Icebridge. The scientists and flight crew will call this place home until the end of November.
We are setting up base stations here at the airport that record the GPS data for various instruments. We are talking to people in the weather office, at the tower, the air traffic controllers, and that typically takes about a day, getting everybody settled in here and preparing everything for the first science flight.
With 2 complete flight crews available, science flights are planned on consecutive days to collect as much data as possible over Antarctica.
On a typical Punta Arenas deployment, we have about 300 flight hours, and if we fly as much as we can, which we typically do, we kind of travel a distance in Antarctica that's equivalent to 3 or 4 times around the equator.
I think this is a glacier we're crossing.
Flight tracks are carefully designed by the Icebridge science team months in advance. Survey lines need to be precise, not only to make repeat measurements in exact locations, but also to ensure the plane keeps a safe distance from specially protected areas and animal habitats. A sophisticated guidance system on the DC-8 helps the flight crew keep the plane on track and navigate around more than 1,700 known wildlife locations on the Antarctic continent.
Some of the flights are hand-flown using moving map displays that have a flight track depicted on them. Others are guided by what's called the ATM instrument, where it actually puts out a signal that we feed into the aircraft navigation system, where it guides the airplane laterally.
So the ATM stands for Airborne Topographic Mapper. We designed a supplemental system to the ATM. Some people call it the ATM Navigator. What it does is it couples into the aircraft's own autopilot and helps it to steer the aircraft as accurate as we need it to be. We can generally steer the airplane well within 100 feet and often within 20 feet of where we want it to be. And that means that if you imagine a line that represents our desired track, more than half the time that line will lie within the cabin of the aircraft.
Antarctica's harsh and often unpredictable weather determines when and where the Icebridge team will fly each day.
I've got rising terrain, 12 o'clock, 7 miles. Tally-ho. Tally-ho, and I'm going to start climbing here.
Pilots need perfect visibility of the terrain for safety.
We'll clear it. It does get steeper as we get closer to it, so we can pitch up a little bit.
Several science instruments need a clear line of sight between the aircraft and the ground to collect proper measurements.
Meteorology is obviously a very big deal with Icebridge. It essentially governs everything that we do on any given day. We have to fly down low and near the terrain in order for our instruments to work as they're optimally designed to work. So it means we need clear skies below the altitude at which we're operating in order to do this kind of work. We know from experience which parts of Antarctica are likely to have good weather and which parts are not. So we design the missions so that each of the missions has a maximum chance of success based on the likely weather scenarios.
We come up with about twice as many mission plans as we can possibly fly in the field, and that's simply so that we have enough target areas to choose from that have good weather while we are here in the field. And then we prioritize these plans.
We have to spend a very large amount of our time while we're in the field trying to sort of ascertain what the weather is going to do. It's a bit like reading tea leaves. It's a very inexact science. We depend entirely on what the meteorologists tell us through computer models. We talk a lot to the meteorologists here at the airport. They're terrific. They give us a lot of help.
The Chilean hosts provide everything from weather expertise to daily flight lunches for the Icebridge team. Airport firefighters and emergency responders are also prepared to help in case anything goes wrong with the aircraft.
So we don't use retread tires.
No usamos llantas reutilizadas.
The DC-8 is not your typical airplane. Structural enhancements, new engines, and cutting-edge data systems make the aircraft a versatile, long-endurance platform for earth science research.
The DC-8 is uniquely capable for this kind of operation, mainly because of its long legs. It can fly for about 14 hours on a full fuel load.
We have to pretty much commute every day to Antarctica and commute back. And then we need also the capability of collect several hours of data. Typically on every flight we collect several terabytes of data all together. So we have 8 different science instruments on the aircraft, and in total it's a very complex set of measurements that we take over ice sheets, and doing it all at the same time in the same location from one airplane. It's really a tremendous resource.
It is amazing that a large airplane that was designed originally to be an airliner could be so diverse, but by its design it meets a lot of the requirements NASA had set for the type of science studies they wanted to execute using the airplane to support. This particular airplane was built in 1969, but many of the systems have been upgraded over the years to keep up with current technology. For instance, the airplane has a satellite communication system on it, which something like that didn't even exist when it was originally built. So what's nice about that is we can move data real time during the flights off the airplane to people anywhere in the world via the satellite system and then the internet, and they can send us information real time as well. We can X-chat, it's like texting back and forth to each other. We can send photographs, we can send technical data. You don't have to actually be on the flight to participate.
My view of this airplane is that it's the ideal airplane for the kind of mission we use it for, because it's built very strong, and in the old days when these were being designed and built, the airplanes were overbuilt to be on the safe side. We have a nickname for it. It's a DC-8, and the DC stands for Douglas Cable Car, because unlike the modern airplanes that use electronics and hydraulics to control the airplane in flight, this airplane is controlled with steel cables. So we do hurricane research, we fly through hurricanes, and we do a lot of different types of scientific research, and the airplane can take a lot of damage that would cripple other more modern airplanes, and this airplane still flies fine. It's like an old truck. It's solid and almost indestructible.
A wall of stickers at the mission director's console tells the story of the many missions the DC-8 has flown since it went into NASA's service in 1987. This aircraft and many others operated by the NASA Airborne Science Program fly thousands of hours every year all over the world to support a variety of earth science research missions. It takes careful coordination and detailed planning behind the scenes to make these missions possible and to gain a better understanding of how our planet is changing.
Hi, my name is Howard Hugh. I am the acting program manager for NASA's Orion program. We are very excited that we could share with you the progress of our 3 spacecraft that is going to support the Artemis missions. Orion is NASA's next generation human spacecraft, taking the first woman and the next man to the lunar surface. We are very excited to be here and share with you our progress. Now, we can't do this without the very many people that support the Orion program. And of course, we have suppliers and people who help build the spacecraft across all 50 states, including Washington, D.C. and Puerto Rico. Now, we also have our European partners who are significant contributors to the Orion program. Across 10 countries in Europe, they help also build the spacecraft parts and components that are necessary for us to fly to the moon. Let me tell you a little bit about the Artemis 1 spacecraft. Earlier this year, we just completed a very important system level test that demonstrated Orion's ability to survive and operate robustly in space. It was the environmental test at Plumbrook Station, where we simulated the space environment for vacuum and temperature. And of course, Orion passed with flying colors and demonstrated our readiness for flight. Now, we only have a few remaining assembly tasks at KSC to pull the entire vehicle together, and then shortly after that, we will be ready to hand over to our ground processing team and stacking on the Space Launch System. So very exciting time for us regarding Artemis 1. Now, Artemis 2, we're also making significant progress there. Just recently, we finished bonding over 180 tiles for the heat shield. And the heat shield is at the bottom of the crew module, which keeps the crew safe as we re-enter the atmosphere. It's a very high temperature, 5,000 degrees, so the crew needs a lot of protection, and that's what the heat shield material provides. And so very exciting news there that we were able to finish there. And of course, we're making a lot of progress pulling the entire spacecraft together for Artemis 2, doing a lot of work installing the hardware that's needed to operate the vehicle, and of course getting all the electronics and other components inside the crew module as well. So lots of great progress there, and lots of great progress over in Europe as well, as the Europeans are pulling their final pieces of the European service module that provides the power and the propulsive capability for the spacecraft. So that's coming along as well, and of course they will be delivering their part of the spacecraft, and then we will be putting that together and be ready for Artemis 2 in the future as well. And finally, for Artemis 3, we're also making great progress there. You know, the Europeans already have their primary structure in work. Thales Alenia is delivering that in late September, so that's great progress. And of course, on our own crew module, we've got the first panel built. This is the panel with the windows, so it's very exciting that we're going to have this capability delivered in the near future, and very excited that that's completed, and that's the first piece that we're going to have for Artemis 3 on the crew module. Now, I want to congratulate Lockheed and AMRO for making this possible. It's certainly very exciting. You know, we're getting close to flight for Artemis 1, and then we're making great progress on 2, and of course we've started making great progress on Artemis 3 as well. So really exciting times for the program. With that, I am going to turn over to Lockheed Martin. I will introduce Mike Hawes, who is the Vice President for Human Exploration and also the Lockheed Program Manager for Orion.
Well, thank you, Howard. As NASA's prime contractor for the Orion program and the spacecraft we're talking about, we certainly work constantly, day and night, to meet these aggressive schedules and to make sure that we're ready for the Artemis missions, as Howard described. Today we're particularly excited because we're here to highlight one of our great suppliers. So we'll be joined virtually by Mike Riley from AMRO Manufacturing, which is in El Monte, California. And AMRO manufactures the cone panels, or the sloped pieces. If you think of the Orion capsule, these sloped pieces along the top of the capsule are really critical components, and that's what the AMRO team manufactures. We're actually celebrating the completion of that first panel, so I would like to actually ask Mike Riley to talk about AMRO. Mike is the CEO of AMRO. He's actually the third generation of the Riley family to run AMRO, and they have been a fantastic partner for the Orion program. So Mike, I'll turn it over to you and ask you to explain how you machine the panels and have your team show us what it is that you do so well.
Thanks for the introduction, Mike. AMRO has been in business for over 40 years, and I'm honored to be a third-generation member of the AMRO family. AMRO has been involved in the Orion program since day one, and we are honored and excited to see what the program has evolved into. Standing next to me here, we have one of the cone panels for the Orion pressure vessel, the window panel. It's these windows that the next American astronauts will be looking at the lunar surface through, the first astronauts to do so since Apollo 17. This panel is currently complete and ready to ship to Michoud. We are also working on the second and third cone panels, which will be completed soon and also on their way to Michoud. Bola, tell us a little bit about your experience working on the Orion panels.
These panels are very complex. We understand the importance of precision and safety required. Here at AMRO, we use the latest technology to make these special parts. We also gotta make sure we make good parts so the astronauts can back home safe to see their families.
I'm here with Program Manager David Thompson. David and I are standing in between two SLS panels. David, can you tell us a little bit about the panels that we're standing in between?
Yeah, I'd love to, Mike. Over here to my left, we have an engine section core stage barrel panel for SLS. Right now you can see it's in the flat configuration. We're getting it ready for inspection, then it will head over to forming. And then over here to the right, we have a LVSA forward panel. LVSA is Launch Vehicle Stage Adapter. It's in the same flat state. It will be going over to forming after inspection. After this, you'll see a nice, great contour, and then we will get it ready for the customer.
Excellent. Thanks, David. Thanks for all your hard work to make this program a success. Now, Mr. Howard Hugh, back to you.
All right, now we'll answer some questions that we received. The first one is from the Houston Chronicle, Andrea Lenfelder. She asks, when is Artemis 3 set to launch, and what is Lockheed Martin's doing to ensure Orion is ready to meet this deadline? Let me see. I'll take the first part of the question, and then I'll hand over to Mike Haas to answer the second part. Right now, Artemis 3, we're targeting 2024 to put the first woman and the next man on the moon. Very exciting times. We're making great progress. Not only is Lockheed making great progress, but also the Europeans, as I mentioned earlier, making significant progress with the primary structure. So really great work going on there, and we'll be ready to meet those challenges and get us to the moon in 2024. So with that, I'll turn over to Mike to answer the second part.
Thanks, Howard. So let's talk about what the Lockheed Martin team is doing, particularly for Artemis 3. I mean, we've already talked about we're actually working on completing Artemis 1, building up Artemis 2, and now starting the manufacturing of Artemis 3. So we've talked about the panel manufacturing, and we'll talk a bit more about that. But we have parts coming together from our suppliers across the country. Like Howard said, we have suppliers in all 50 states and Puerto Rico. And so we are pulling all of those pieces together. We're making deliveries to our team at KSC. We're making deliveries to the European team. And we will continue through the next year. If you look at 2023 targets to have this spacecraft ready to be able to fly in 24, we have a lot that's going to be coming together just in the next year.
All right, thanks, Mike. Let's see, we've got another question. This one I think is suited for Mike Riley at AMRO to answer. Philip Sloss with NASAspaceflight.com asks, can you tell us how the cone panel is manufactured at AMRO, and what is the status of the other two cone panels for Artemis 3?
Sure thing, Howard. That's a great question, Philip. Here with me to answer that is Program Manager David Thompson.
Thank you, Mike. So how is a cone panel made? So it starts out as a flat plate weighing approximately 13,000 pounds. As you can see here, it's about 200 pounds in the form condition. This panel is a culmination of different departments here at AMRO. The first is forming. Then we go into 5-axis machining. We have CNC programming. We have laser inspection, a heat age operation. We go out to outside processing. And then finally, we have final assembly. The other two cone panels, which will be friction stir welded to this panel, are currently in production and will be completed in a couple of months. All right, we have another question. This one is, let's see if Mike Haas could answer this one. Andrea at the Houston Chronicle also wants to know, how many panels total come together on the Orion spacecraft, and how many parts, nuts, bolts are needed to assemble the entire spacecraft? So Mike, I think you got a tough one.
So obviously there are thousands of components that come together to make the Orion spacecraft. And again, I'll reference back to the crew module. Just to build the crew module, we're going to talk in the order of 200,000 parts when we talk about, you know, all of the fasteners and bonds and the tiles that cover the surface. So hundreds of thousands of parts, and that doesn't even include the European service module and the launch abort system that actually gets stacked on top of this. But I want to focus on the key pieces of the pressure vessel, as we call it, and how we have improved that over time. We're focused here with the AMRO team on the cone panels. There are 3 cone panels, but there are only 4 other pieces of the structure that all get welded together. When we started on the Orion project, we were over 30 panels that had to be welded together. And so over time, we have simplified that process down to just 7. And we've saved mass, we've saved time, we've saved cost in order to do that. And so this is the first panel that we've been talking about today. We will continue to deliver panels. AMRO will continue to deliver those panels through the course of the fall. All 7 major pieces of the pressure vessel structure will come together at the Michoud Assembly Facility in New Orleans by this fall, late this fall, and then we'll start to weld those together with the friction stir welding process that we have developed on earlier NASA programs and use today. By September of 21, then we would actually expect to deliver that pressure vessel to Florida to the team in the operations and checkout facility, and then they'll really start building up the entire spacecraft.
And finally, we have one last question from Leonard David from newspace.com. He asks, with the increasing role of entrepreneurs in space, how best can the larger space primes work with these groups? Any advice on this? Let's see, I think Mike Haas and I both could answer this question. I'll start first. You know, we are certainly working together with the commercial partners to improve not only their design, but also give them data. So we've given a range of not only requirements, data products, test data that we've generated, reports, and of course all the design aspects that are important to the commercial spaceflight programs we provided as well. And some of the examples include parachute data, which obviously provides a safe landing for the crew, aerothermal, aerodynamics database and data, all the testing that we've done across the board, the GNC guidance, navigation, control, design, and also re-entry data. So lots of significant items, over 1,000 products that we've given to these commercial partners to enable them to be successful as well. So I look at it as a partnership across all the NASA programs to help each other and learn from each other. And let's see if Mike has additional inputs.
So the question of entrepreneurial companies is a really fascinating one. We've seen so much happen in just the last few years. With the supply chain that we have in Orion, and Howard had mentioned that earlier, that we have hundreds of companies across the country that are all providing, and probably half of our suppliers are actually small businesses. So when we talk about newly started companies, entrepreneurial companies, they certainly fit in that kind of range.
All right, thank you to Dr. Haas and Mike Riley for helping me today and joining us on giving a status of Orion. Today, it's been a great day getting a discussion with you in terms of our progress and fielding some questions from the reporters, so appreciate that. And stay tuned, we've got a lot of exciting things happening in Orion. We've got a lot of great progress, like I said, across all 3 vehicles. We'll certainly talk about getting ready for launch, our what we call Path to the Pad, and supporting all the Artemis missions going forward. It's a very exciting time for us at NASA, and looking forward to you joining us on that journey. Thank you.
Tracking our next Mars landing, the science on the next station resupply mission, and the newest space station flight directors. A few of the stories to tell you about this week at NASA. At After nearly 7 months and 300 million miles, our Mars 2020 Perseverance rover and Ingenuity helicopter arrived at the Red Planet on February 18th. Perseverance will use its suite of instruments to search for signs of ancient microbial life and test technologies to help pave the way for future human exploration of Mars.
The rover exemplifies the spirit of exploration as it pulls on science, technology, and human exploration to work to advance our goals in many areas. And Perseverance, by its very name, describes the human spirit that gets us there.
You can track the home stretch of the spacecraft's journey to Mars at mars.nasa.gov/Mars2020 and watch landing day coverage on NASA TV and on our website starting at 2:15 p.m. Eastern Standard Time. The research and technology on the next Northrop Grumman Cygnus spacecraft to the International Space Station includes an experiment to study manufacturing artificial retinas in space, an investigation using worms that could help us better understand muscle weakening that astronauts experience in microgravity, a radiation detection system for use on our first Artemis mission to the moon with astronauts, and more. Launch is targeted for no earlier than February 20th from our Wallops Flight Facility. NASA's 4 newest additions to its 2021 Flight Directors class are Diane Daly, Chloe Mehring, Fiona Turret, and Brandon Lloyd. After a rigorous training program that includes technical knowledge and leadership skills, they will work in mission control at our Johnson Space Center, overseeing human spaceflight missions to, from, and aboard the International Space Station, as well as lunar missions for NASA's Artemis program. Technicians at our Kennedy Space Center are prepping our Orion spacecraft to manage oxygen flow and cabin pressure for astronauts inside the capsule on our Artemis II mission, the first flight to carry astronauts to the moon aboard Orion. The mission will help pave the way for sustainable exploration at the moon and future missions to Mars. The spacecraft for our Lucy mission received its 3rd and final scientific instrument. The mission, targeted for launch this October, will be the first to explore the Trojan asteroids, a population of small bodies that share an orbit with Jupiter. This last instrument, named LaRalph, is actually 2 instruments in one that will help Lucy determine the composition of the Trojan asteroids and provide insight into the early history of our solar system. On February 10th, we featured a virtual Black History Month event on NASA TV and the agency's website focused on the impact of African American leadership in NASA. NASA is proud to observe this and other months throughout the year, during which we celebrate diverse individuals and their contributions to our agency and to our nation. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/Twan.
Hi, I'm NASA Kennedy's Brianne Roloff, and I'm outside KSC taking you inside KSC. Kennedy Space Center's Crawlerway is undergoing a thorough conditioning campaign to prepare for Artemis I. The Crawlerway is a unique roadway with twin 40-foot lanes filled with river rock. Its job? To withstand the heavy loads as NASA's crawler transporters carry rockets from the Vehicle Assembly Building to Launch Complex 39. Teams from NASA's Exploration Ground Systems are in the process of driving a Space Shuttle-era mobile launcher platform along the path. With each pass, they will increase the weight on the vehicle. In the end, this roadway to the launch pad will be ready to bear the weight of Crawler Transporter 2, the mobile launcher, and the Space Launch System rocket topped by the Orion spacecraft. Under the Artemis program, NASA aims to land the first woman and the next man on the moon in 2024 and establish sustainable lunar exploration by the end of the decade. The 4 astronauts on NASA's SpaceX Crew 1 mission launched from Kennedy aboard a SpaceX Falcon 9 rocket on November 15, 2020. The next day, they arrived at the International Space Station aboard the Crew Dragon spacecraft they named Resilience. This past Sunday, February 7th, the crew surpassed the record for the most days in space for a crew flown on a U.S. human-rated space capsule, 84 days. The record was set in 1973 and 1974 by the Skylab 4 crew. NASA and SpaceX are targeting no earlier than Tuesday, April 20th for the launch of the SpaceX Crew 2 mission to the space station. For more Inside KSC, check us out on social media and at nasa.gov/Kennedy.
NA-186, NA-186. Juliet Oscar November calling. 96 and 96 ett Oscar November calling. NO186, it is 6 at Oscar November. You copy me, Chris? Copy you loud and clear. Okay, I'm going to patch them through. Please, 1 minute.
This is Owen. How has seeing Earth from its orbit affected you, in your frame of reference when moving around the ISS, or in your perspective of humanity as a whole? Over.
Hi, Owen. That's a great question. Seeing Earth from up here it's a beautiful thing. It's just this peaceful place with no borders there, and you just see this wonderful colors of blues and greens and browns and white clouds and snow-capped mountains. And it really gives you an appreciation for Earth as a spaceship for 7 billion people, just like our spaceship is keeping us alive, and how we need to take care of Earth because it takes care of us. Over.
This is Spencer. What happens if you vomit in the space station? How do you clean it up? Over.
Well, hi Spencer. Fortunately, we are prepared for vomiting in space, and we bring special bags that if we're feeling the urge to go, we use these bags. Occasionally, on the launch, it can surprise you, and but we have bags in the launch vehicle as well. If you didn't make it in the bag, it would be a real mess, and it would go everywhere. It would take quite a bit of time to clean up. Over.
This is Lucas. How has the COVID-19 pandemic affected you while you're in space? Over.
Hi, Lucas. The pandemic has affected us because it's affecting our families. Our daily life here on the space station is largely the same with and without the pandemic. We are safe, and we are executing our job and keeping the space station running and functioning and keeping ourselves healthy with our daily routine. But we're concerned for our friends and family and loved ones because they're in Russia and in the United States having to deal with it just like you are. Over.
This is Allie. What will be your first meal when you get back to Earth? Over.
Hi, Allie. I like to eat, and so I'm looking forward to any food that somebody makes. But one thing we don't have is an oven here, so something that comes out of the oven and you smell those smells and you eat a nice hot meal, that sounds terrific to me. Over.
This is Sawyer. What does it feel like when the rocket lifts off? Over.
Sawyer, when the rocket lifts off, it's this tremendous feeling like somebody's pushing you in your back and shoving you faster and faster and higher into the sky. And there's a few periods of time where our engines change, called staging, and there's some bumpiness and a little bit of shaking in the spacecraft during those periods. But the rest of the 9 minutes is just like a giant force is throwing you into the sky. Over.
This is Jordan. What does the space station smell like? Over.
Jordan, the space station has not too different smells than you'd have in a home down there. We try to keep ourselves clean. We try to keep the space station clean. In fact, tomorrow is Saturday, and that's our cleaning day, and we do our best to keep it neat and tidy. But occasionally there's smells where we have to change fluid. A lot of times that has to do with our bodily functions in the toilet, and they can be smelly there. But for the most part, the space station, to me, it smells just like a normal home. Over.
This is Eric. Was training to be an astronaut harder or easier than training to be a Navy SEAL? Over.
Well, Eric, they were totally different. The training to be a Navy SEAL initially was very hard for 6 months. Training to be an astronaut or a cosmonaut is a long process, and it takes many years of hard work. So, and it's more academic, more having to do with your brain. In SEAL training, we had some academics, but largely it was a physical thing. So 2 entirely different programs. Over.
This is Owen. What experiment that you've done had the most unexpected results? What was the expected and actual outcome of said experiment? Over.
Wow, Owen, that's a very detailed question. We have lots of experiments going on up here, but one that when I first arrived, we were growing some plants, and I thought that they would grow more than they did.
over the course of several weeks, they were just a small sprout, which surprised me because pictures I had never seen growth in space before on my previous missions. So I'm looking forward to trying that again and getting better results. Over.
This is Spencer. How successful is your 3D printer on the station? Over.
Spencer, we have the 3D printer has been here since I think 2015, a few years, and we've printed many parts. We don't have it deployed and active all the time, but when we need to, we can print what we need if it meets the criteria. It's a very effective way of having spare parts in space. Over.
This is Lucas. You're a model rocket building club. Did you ever build model rockets when you were young? Over.
Lucas, I wish I did, but I never had a club or a mentor in my area that was involved with model rockets, so I never really launched a model rocket as a young person, but I think it's great that you guys do. Over.
This is Allie. What does microgravity feel like on your body? Over.
Allie, microgravity is more a feel of how to move around. Your body, in my opinion, feels kind of the same. Everything you do on Earth with your body, eating, going to the bathroom, sleeping, your hair growing, all that stuff is very normal, I think. But moving around in microgravity is not normal, and it takes some practice to get used to how to do it effectively. Over.
This is Eric. Does the Earth look any clearer or less polluted now compared to when you flew in 2009 and with Canadian Chris Hadfield in 2013? Over.
I actually flew with another Canadian, your Governor General, Julie Payette, in 2009. So this is my first mission in space without a Canadian crewmate. But the Earth does not look any different with our eyes than the previous times. And my crewmate and friend Anatoly has been in space several times, and we both have tried to see any differences, and we can't really tell with our eyes. Over.
This is Sawyer. Do you play any games while you are on the ISS? Over.
Well, Sawyer, we're pretty busy people up here. We have lots of work to do during the day, and by the time nighttime comes around, we just have the energy to eat and clean up from our day and prepare for the next day. Maybe make a phone call or something, or answer an email, but we don't have a lot of time to play any games. Probably the closest thing to a game is seeing how straight you can fly without crashing into a wall and how far you can go like this. Over.
Well, I tell you what, for all the folks on the phone, let's go ahead and give Commander Chris Cassidy and the crew on NA-1SS a big round of applause anyway. Sending my greetings along to all of you in traditional amateur radio terms. 7 3s, best wishes, and thank you for participating in this activity. Thank you, everybody. This is just excellent.
Today we're at the Kennedy Space Center where we are doing some really amazing things. In just a few days we're going to launch the Boeing Starliner. With the completion of this test, we will be one step closer to launching American astronauts on American rockets from American soil for the first time since the retirement of the space shuttles in 2011.
Well, good morning and welcome to the Kennedy Space Center, America's premier multi-user spaceport. It is absolutely great here today, getting ready for Boeing's commercial crew launch of the Starliner. I can't say enough good things about what we're doing here at KSC. I think it's pretty amazing when you look out at all that's going on. And today we've got our NASA Administrator Jim Bridenstine and this awesome Boeing commercial crew cadre.
I remember it wasn't too long ago it was announced that the space shuttles were going to retire. The Constellation program was going to be canceled. And of course here at the Space Coast in Central Florida, there was a lot of concerns and a lot of families were hurting. But Bob, because of your leadership and the great things you've done, you've transformed this facility into a multi-user spaceport where we've got commercial activities happening side by side with government activities. These are very exciting times for the Kennedy Space Center, very exciting times for Central Florida.
How are you, sir?
Hey, good to see you.
Thanks for being here.
Katie?
Good to see you again, sir.
Good to see you always. How are you?
Good.
Excellent.
Welcome.
Hey, Jim, how are you doing?
Great to see you.
Awesome, thank you.
Welcome to the Starliner High Bay where the spaceships are born.
It's pretty amazing, isn't it?
Yeah.
Tell me about these. What are we looking at here?
Let me start over here. That is a spacecraft that just flew our pad abort test.
Yep. Yeah.
And with that, we proved that the guidance system talks to the thrusters and the come home system all works great. So we're confident to go press onto orbit.
So that's that vehicle.
That's the one.
That's the very one.
And we have a little tradition. On a spacecraft going to space, you can't do anything too funky. This one came home and the team has signed it.
Oh, wow.
They've said, that's our work.
Okay.
And I'm wondering if you would do us the honor of representing the NASA teammates.
I would love to.
Come on up and sign it.
All right,
Would
let's
you?
do it.
This was a test vehicle. Can I show you the first one to carry people?
Absolutely.
Let's go talk to Chris Ferguson. He's going to fly in her.
Okay. Hey, Chris.
How are you doing?
Good to see you.
It's good to see you.
Absolutely.
So this is number 2 of 3. These capsules are mostly autonomous, which means they sort of launch and they're able to find the International Space Station and dock with it with little or no assistance from an astronaut. However, there is the system in place in case the astronaut needs to take over, where they can guide it and manually dock it if need be.
Okay.
With an autonomous vehicle, we are largely a monitor, right, to make sure things go off as they're supposed to, and that an action, if it was intended, is in fact completed. And the way we manage that is we actually watch the script execute right on the screen.
So, Chris, you personally are going to fly on this vehicle, and maybe multiple times into the future. I mean, who knows? And this is historic. You as a Boeing astronaut are really blazing a trail.
I think that this is the beginning of something that we'll see a lot more of. You know, early on, we had military pilots work hand in hand with the government test pilots to develop airplanes, and I think what you're seeing now is just an extension of that.
As a nation, as an agency, we need to see a lot more commercial astronauts and a lot more commercial activities in space. Ultimately, because that's how the future is going to be. We need to see lines of effort that include advanced manufacturing and industrialized biomedicine in space, with a lot of the capital coming not from just the American taxpayer, but capital coming from private industry, improving the lives of humans here on Earth. And that's what the commercial industry is all about, and that's why we need commercial astronauts. So the vehicle that we're in right now is called the Astrovan. Tell me what does that mean? What is that all about?
This is the second generation of Astrovan, and this is what we'll use to take the NASA astronauts from crew quarters, which is in sort of the industrial office area, about 7 miles or so out to the launch pad. Okay. So it takes about 15 minutes to get there. It's we always used to say it's one of the longest and loneliest rides you'll ever take in an Airstream trailer. And it was interesting along the way. You drop off various people, and then you realize the only people left on the van when you got to the launch pad was the crew. So we always used to joke that the smart ones got off.
So Tori, we're at Slick 41. Tell us, what is Slick 41 and what do we have behind us?
So Slick 41 is the home of the mighty Atlas rocket. This will be our 81st launch of this rocket. So this giant manifold here is part of our acoustic suppression system. It's going to spray water, unmistakable when you see the launch go off. You'll see all that water. Most people think that's for fire, but really the interesting thing is it's not. It's for sound. Because when the rocket clears that launch pad, the sound coming out of those rocket motors and rocket engine is so loud, if it reflected back off this pad, it would damage the spacecraft. In fact, if you could stand here and somehow survive the fire, the sound alone would kill you.
Oh, wow.
And so all of that water present on the pad absorbs the acoustic energy and protects our payload.
Well, make sure that water works. Can you do that?
I will absolutely double check it. So those big white cylinders you see on the side are solid rocket motors. They give us extra impulse coming up off the pad. That's a lot of propellant, and it's going to generate each one of those almost 400,000 pounds of thrust. In the center, that big tube in the middle, the bronze colored one, that's our main propellant tank for the center core. We can step up here. So that's the real McCoy, all 109,000 pounds of solid propellant. And that's a heck of a view.
It's pretty awesome.
Yeah, 190 feet straight up.
Mr. Administrator, welcome to the 12th floor.
Thank you. It's good to be here.
Sir, good to see you.
Good to see you guys. I'll tell you, it looks tall from the ground, but when you're up here, it feels a lot taller than it looks from the ground, especially with these winds. Well, I'll tell you, you can really feel the wind when you're up here, and I can imagine maybe tomorrow the wind won't be so high, but certainly I can imagine when you go across this. I know it's an access arm, but it looks like a very narrow catwalk, if you ask me.
Well, we'll be coming out here in our spacesuits.
Yeah.
And we're going to be, even though we're steely, aviators, we're still going to have a lot of emotions. This is our last moments on planet Earth before we go launch into space.
Yeah.
And the winds are actually a blessing. Because in space station, there is no wind, right?
Right.
And so everything's the same all the time. And then here we're getting like a kiss from Mother Earth as we get ready. So we walk across here, we walk down this access arm. We can feel the positive energy from all the people that worked so hard on this mission. And then we go in and close those doors. We're just feeling proud. We're feeling a little bit scared, a little bit anxious, but we're like totally trusting our training. We're totally trusting Team NASA, Team Boeing, and the United Launch Alliance.
So of course you can see your Starliner sitting there on top, and that's where Spanky and I and Fergie, when we climb in through the crew access arm right into the side hatch, we go to Starliner. On the top of that is the IVA hatch, and that's what's going to dock with the International Space Station. Beneath Starliner, you can see the service module. That's where it has a lot of our life support system, our prop, the engines while we're orbiting and maneuvering in space. And then below that, you can see this amazing Atlas fiber rocket.
Well, I'll tell you, what you guys are doing is going to inspire the nation, but not just our nation, also people all around the world that are going to be watching this. So thank you so much for what you do.
Thanks for the opportunity.
Thank you.
Thank you, sir. We'll do well.
All right.
Sonny, what are we doing here?
So we're at Spacecraft Launch Complex 41, standing in the shadow of the Atlas V with the Starliner on top, with the crew access arm connected to it, ready actually for people to eventually get on board. We got Rosie, the mannequin inside that is instrumented, and so we're going to get some data to see what our ride's going to be like when Josh and I actually get to fly on this thing, probably at the end of next year.
Great. And Josh, what's your role in this?
To not mess anything up is the goal today. This is the capsule that Sonny and I are going to have a chance to fly in, along with two others. And so we're following the whole process from beginning to end. From launch tomorrow morning to docking the next day and to landing a week and a half later. For me, it's just a situation where I find myself pinching myself. It's just, it's incredible to see this happen. We're living science fiction. It's really happening right here.
We've actually done a lot of engineering work with the Boeing team to work on the software, so when the humans are interacting, they've got that situational awareness of all the automation that's processing in the spacecraft and how we would recognize if there was an issue or a problem and how we would interact with it.
We're looking at where our future is. We have a $400 billion space economy. What you're doing is leading the way for that space economy, lowering the cost of space travel and providing more access to more humans on Earth to get to space. It's about expanding the human condition by finding new knowledge. And I'm just so proud to be with you, but that's why we're here. So I thank you for what you're doing.
This is a new era in human spaceflight. And there's a number of reasons why this day is so important. We are on the cusp of launching once again American astronauts on American rockets from American soil for the first time since 2011, the retirement of the space shuttle. So this is a big day.
How many of you have seen a rocket launch before? Can I get a show of hands? Oh man, you got, okay, how many have not? Let me put it that way. This is the group I want to talk to. All right? Anytime a rocket ship leaves planet Earth, it is an experience. I don't care what's on it. And you see it, you feel it, you experience it. It's emotional.
Welcome this morning to NASA's Kennedy Space Center in Florida.
Starliner is nearly ready for our uncrewed orbital flight test. You can see it over our shoulders, lit up on the launch pad. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff. The rise of Starliner, a new era of human spaceflight. Is now traveling at over 5 times the speed of sound. And we have BECO booster engine cutoff, standing by for stage separation. And we have good indication of stage separation.
We had a great launch this morning, and the Starliner is now in orbit around the Earth, and that's because of the great work that you here at Boeing have done with your partners at NASA. That's important, and it needs to be recognized. And I know, I see that look around, I see a lot of people that are concerned and worried about the fact that the insertion burn did not go according to plan. And it's of course a concern to me as well. It's a concern to all of us. But here's why we test. Because we're going to learn things. And from what we learn, we're going to make changes and we will move forward. That's what we do. And so this is a good day. It's a good day.
We train extensively for this type of contingency. And had we been on board, there could have been actions that we could have taken. This vehicle is a new level of automation that we've never seen before. And so what we're really doing is we're testing that automation, and that's why you have test pilots on board, especially for these early missions. That's our job. That's what we're trained to do. We are looking forward to flying on Starliner. We don't have any safety concerns. everything on the ascent, all the systems that would keep us safe have functioned properly on the launch and currently on the vehicle. We're looking forward to all the test data, and we're looking forward to landing at White Sands.
Good morning from Starliner Mission Control in Houston. It's December 22nd, 2019, and we think this will be a day to remember.
We have chosen the longest night of the year to bring Starliner home. Happy winter solstice to everyone. Starliner flight control teams have been working around the clock to get Starliner set up for a safe landing, and today is the day. The entire team here in the room is quietly watching, making sure all the systems continue to look good.
And we see three main chutes. We see the red, white, and blue as Starliner descends. Base heat shield has jettisoned. That is the base heat shield falling away as planned. Airbags are inflating.
That is the last of the milestones, so now all that's left is for Starliner to float down to the surface of the desert.
And Starliner touches down in the desert in New Mexico. An historic landing in White Sands, New Mexico concludes the first flight test of Boeing's Starliner spacecraft. The first time an American-made, human-rated capsule has landed on land.
Congratulations, Starliner.
Congratulations, indeed.
This is my first spacecraft landing. It was incredible to see. We're so excited for the Boeing and NASA team and the recovery forces today. Just did an incredible job.
Yeah, we got a lot of data on the launch, the orbital portion of the flight.
Being able to just watch the entire sequence from the ground on down was just fantastic. Really clean landing.
We had a beautiful, amazing team all out here ready to support. Everybody was pumped. Everybody was cheering. It was spectacular. I mean, she's back. She's home.
We are really, first and foremost, pleased with how this team came together. Flying a different trajectory, different aero shape. You can only test that at scale. That went terrific. Return is something that you can't really test. You got to put your heat shield on and go through the heat regime. Today we just had, it couldn't really have gone any better. The ground crews, Chris, Nicole, Mike, they're telling us there's hardly any charring, perfectly level on our airbags, and that bodes really well for reusability. From an overall perspective, we are just as pleased as we could be with the design.
I would say the team did just a tremendous job. What you find sometimes is when you execute a flight differently than planned and a mission test flight differently than planned, that team comes together in a unique way. And the NASA team, the NASA engineers, the flight control team, the Boeing team working side by side to solve problems in real time, to come up with innovative solutions, to keep decisions ahead of them, and then to end up like today where we had a successful deorbit burn and entry and landing. If I look back at this year from a commercial crew perspective as a program, you know, we've had a tremendous year. With the holidays in front of them, they just did a tremendous job, and so my hat's off.
So number one, congratulations. I know the last 48 hours have not been easy. So when you think about a mission like this or a test flight like this, when we think about this, launch, of course, is a big challenge that has to be overcome. That happened. Flying the spacecraft and making sure that the systems work, that happened. Entry, descent, and landing happened. We're going to get a lot of data, we're going to get a lot of information, but a lot of really, really good things happen on this test flight. It is also true that when things go wrong, that's when you learn how the teams work. I'm telling you, that was a thing of beauty. And everything that I've been told from the people that were in the room, decisions were made quickly, things happened that were not planned, and because of that, this test flight was actually very successful in so many ways. So thank you for all of your service to the country and all of your service to NASA. So thank you.
Well, pilot call signs are kind of the nickname that you end up getting with your squadron or the group of flyers that you fly with.
You can have a lot of different ranks flying together. Instead of having to call someone sir or Lieutenant Colonel so-and-so, they can call them their call sign.
How you can get a call sign is one of two ways. It can either be a natural fit to your last name or your first name or combination thereof. Or the other way you can get a call sign is by doing something really dumb.
Mine have never necessarily stuck. I've had several throughout the years. One of the reasons I don't really have a call sign that sticks is because I go by my middle name, and it is relatively unique unless you're in Sweden or Norway. So because of that, everybody thinks it's a call sign, but it's really my name.
My call sign's Ringo. It's just basically a play on my last name of Ringelberg. It's easier than saying Ringelberg, so it's kind of one that sort of stuck with me. And it wasn't because I screwed anything up.
I showed up to lead-in fighter training in the Air Force at Holloman Air Force Base, and I walked up to the duty desk to report in, and one of the instructors there took a look at my last name, got on the PA and said, all available pilots report to the duty desk. They came up with Clue, making me clueless.
My call sign is Trasher. When I was a kid, that was a nickname. I got into the military and became an Air Force pilot. That nickname came back as a nickname, but it wasn't ever really earned, and I had a couple of other call signs along the way. But one particular incident, I was flying B-1 bombers up in South Dakota. Now, a B-1 bomber has 4 great big engines that put out a lot of thrust. It's not something you want to stand behind. And as we were taxiing out for a flight one day, I had a problem with the aircraft and had to stop. And while I had stopped, the young airman who had been marshaling me out of my parking spot thought he was finished, and so he began to walk off. He errantly walked behind the airplane, which was okay at the time as I was stopped with the power and idle, but as I got my problem fixed and started to roll forward again, I pushed up the power, literally picked him up off his feet and blew him down the concrete ramp about 100 yards. Fortunately, he was okay and just had some road rash and cuts and bruises and tore up his uniform, so I had to buy him a case of beer and a new uniform, and after that my call sign was cemented in as Trasher and remains that to this day.
My call sign is Gucci. It's not the coolest or the most macho call sign that a guy would look for, so I had no choice in it and I haven't been able to get rid of it. I was flying KC-10 tankers and I applied for the high altitude U-2 program. When I arrived there, the first question that everybody had for me was, why would you leave a nice comfortable job like that, nice big airplane that has perfect air conditioning at 72 degrees, coffee makers, ovens, refrigerators, nice comfortable seat, to come put a spacesuit on and live in a cramped little capsule. So the KC-10 guys were nicknamed the Gucci Boys by the rest of the Air Force because they only went to big airports around the world, 5-star hotels, things like that, because you couldn't put that big airplane just anywhere. And so they said, hey, why would a Gucci boy want to come to this kind of lifestyle? And that's when it kind of stuck. There is, rumors out there that have run around historically that maybe I paid too much attention to my clothes or my hair or the Maserati or stuff like that, but that really has nothing to do with the call sign and the way it was awarded. So unfortunately, you get stuck with it. I'd like to have something more cool like Maverick or Sharpshooter or something, but it doesn't work that way. I got Gucci, so it's all about leather shoes and handbags, and I can't change that.
I'm a brand new combat wingman in the F-15 in Japan. It's my first war exercise, so it's like day one as a brand new wingman. We're gonna take off and go fly a night mission, and right before takeoff we have to get our orders from secure radio to headquarters, and my flight lead checks me in on the secure radio and I can't figure out how to make it work because I've never seen it before. I'm looking down at this panel that has XYZ, ABC, and I don't know what to do. There's no on-off button, so I do my best and am not on the radio frequency. He gets the orders for us, we take off together, fly our flight, come back in and land. Once again, I have a few moments to look down at this radio. I still can't get it to work, so once again, I'm not on the radio with him, with headquarters. My flight lead saved that story until it was my naming night, and because that radio is called a KY-58, they said, KY, Jelly, is your call sign, so I earned it that day for being dumb.
Flying cars, drones delivering pizzas, and a highway in the sky are scenes from science fiction, but they're also visions of our very real future.
Because we also moved this in and then that in.
At NASA Langley Research Center, NASA engineers are laying the foundation for safe autonomous flight in the national airspace through a project called Pathfinder. The goal of Pathfinder is to take separate urban traffic management projects and combine them into a single autonomous vehicle. Then have that vehicle fly and communicate with other autonomous vehicles in the airspace.
Going back a couple years, we did a lot of on-vehicle testing, so we were testing things like Icarus, which is an autonomous sense and avoid, or maybe an autonomous flight management system for UASs, as well as Safe to Ditch, which is an autonomous safe landing or autonomous crash management system for UASs.
Combined, these systems will greatly decrease the risk of unmanned systems flying near manned aircraft, as well as safety risks for people below. To test this, researchers created incursions, where one drone flies too close to another, and then examining 3 different means of separation.
One is just manual, where the UTM operator has to get engaged and see that there's an incursion coming and then issue a command to the ownership vehicle to maneuver out of the way. Another form of air traffic separation we looked at in Pathfinder was called geofencing. And the 3rd level was autonomous sense and avoid. And that engages another area of Icarus.
Icarus, or Independent Configurable Architecture for Reliable Operations of Unmanned Systems, is a major piece to this autonomous flight.
You need to be able to make decisions to avoid other intruders in the airspace, stay clear from no-fly zones, or if you're inside a no-fly zone, the UAV should know how to get out of it, and to reroute itself around obstacles and no-fly areas. So some of these functionalities are essential to operate autonomously without human intervention, and so that's where Icarus comes in, and it provides those capabilities for UAVs.
As researchers conduct flight tests in the field, another piece of the Pathfinder puzzle is taking place in a separate location.
Helicopters beginning turn to the east.
Similar to an air traffic control tower on a standard runway, NASA Langley's Air Traffic Operations Lab is monitoring and making control decisions of active UAV flights.
These operators are observing their own vehicles, so their own small drone, and they're also observing vehicles that are operating near their vehicle. So the goal is to make sure that they maintain separation from all other vehicles.
Originally, these volunteer operators were going to be monitoring from the field. But after a unique communications link was created to connect the ATOL with the vehicles on the range, participants can now monitor the vehicles and traffic from afar.
This was sort of a first step for us. Ideally, in the future, we'd like to expand on this capability because it has a lot of potential. We have a lot of capabilities here in the ATOL for human factors research, and out at the certain range, they have a lot of capabilities for live flights. And by creating this link, we're really opening up the door to a lot of future research.
As Project Pathfinder nears completion, the team has moved from flights on the range to cross-center flights, taking off from the roof of a central building and then autonomously flying out to the range.
It's exhilarating, really, to watch a system that you worked on. You've developed the algorithms, and then to see it perform out there, it's really a joyful experience.
It was a great team. Everybody was really putting in a lot of effort to bring this all together. So that was really something I'll remember going forward from this project.
Hold up 50 amps. 200 meters to waypoint set. 100 meters to copter turns north.
An idea born in unsettled times.
We are going forward.
America, the United States, is first in space.
Becomes a feat of engineering excellence. The most complex machine ever built to bring humans to and from space.
Ride your roll, Discovery.
And eventually construct the next stop on the road to space exploration.
We are on a true spaceship now.
As 30 years of flight draw to a close, its legacy is one of unsurpassed achievement, tragedy overcome, and opportunity met. NASA Space Shuttle. Space Shuttle Endeavour is rolling out to Launch Pad 39A at NASA's Kennedy Space Center in Florida. In 24 missions, flown over 20 years, Endeavour has logged more than 103 million miles in space. The last of NASA's shuttles to be built, Endeavour prepares for her final flight, STS-134.
I marvel at when I see the space shuttle up close and personal. Behind the panels where we have hardware, plumbing, black boxes, electronic devices, and that sort of thing. The workmanship that I see in this is astounding. And that points right at the people that do this. When you integrate all that together, it results in what I think has been a marvelous program with the space shuttle.
Well before any shuttle reaches the launch pad, however, a staggering amount of work is required. The parts, plans, and people necessary to make each launch span the entire nation. One single goal is the focus: the safety of the orbiter and her crew.
You've got all these people, all these folks that are in their 20s, some of them in their 30s, and they are, no kidding, in charge of some part of the space shuttle, some part of the space station, or some part of the plan. And every one of those people absolutely believes that they are the one that makes the difference on getting those astronauts back down to the ground alive.
At NASA's Mission Assembly Facility in New Orleans, production begins on the shuttle's external fuel tank. The last of 136 produced here since 1973. Each one 154 feet tall and 27.6 feet around, is capable of handling 535,000 gallons of liquid hydrogen and oxygen, enough to fill 13,375 average household bathtubs. 3 versions of the external tank were created during the program in an effort to reduce the tank's overall weight and allow for heavier shuttle payloads. Around the same time, in Clearfield, Utah, technicians at ATK Launch Systems start work on the shuttle system's solid rocket motors, or boosters.
Fire.
Together, these SRBs produce nearly 6 million pounds of thrust, about 83% of the thrust needed to push the orbiter into space. The remaining 17% is furnished by the shuttle's 3 main engines, fueled by the external tank. Unlike the orange external tank that is used only once, the boosters detach themselves and parachute into the Atlantic Ocean. They are then retrieved, refurbished, and reused on later missions. The shuttle mission's crew is assigned.
Folks on there that are like my brothers and sisters. I mean, we really do get close after a year of training for a flight and having flown in space together. And there's a special bond that comes with that.
Right up until launch, a shuttle crew will train in a variety of critical regimens, some basic, others specific to their mission. Simulators, safety and contingency, science experiments, and underwater in the world's largest indoor pool. STS-134 astronauts floating in actual spacesuits, trained to work during extravehicular activities, or EVAs. The Neutral Buoyancy Lab, or NBL, at NASA's Johnson Space Center in Houston, is the best simulation of microgravity on Earth and ideal for practicing spacewalks.
One of the most amazing facilities that we work in is the NBL, the Neutral Buoyancy Lab, and the divers and the guys who help us run the robotic arm are all there to ensure that our spacewalks are flawless. Their efforts in that pool have helped us and made us able to have this program.
Every step of a spacewalk, every step of EVA is so critical, and even though we see it every day, that one little safety tether could be life or death.
For every hour that they spend in orbit, they'll spend 5 to 6 hours training for that same task. So we've built up from the suit engineers and suit technicians who help them get into the suit. Now we've got trainers who help them learn how to use the suit and learn how to understand the suit. And then we've got divers who support them while they're in the pool. The closer they get to actually flying in the suit, the team of people who help them tends to grow. Maybe not exponentially, but it's certainly getting bigger.
A 12-person crew has kept a week-long vigil, while the barge, carrying the ET, made the 900-mile trek from Louisiana to Florida's central east coast. The iconic orange external tank finally arrives at the Kennedy Space Center. 1 month later, the ET is mated to the solid rocket boosters to form the backbone of the stack. Now, all that's missing is the spacecraft itself. When an orbiter returns from a mission, processing for the next flight begins almost immediately. It's a task requiring no less than 650,000 hours of labor. This includes the removal of its 3 liquid fuel engines and their replacement by 3 from a previous mission. They've been refurbished, inspected, and tested at the Stennis Space Center. With most of its flight preparations complete, Endeavour is towed in what is called the rollover, a short roll over a quarter-mile distance on a 36-wheeled vehicle from the Orbiter Processing Facility, the OPF, to the VAB. Here it undergoes its flight configuration. The rollout. Looking now much like it will at liftoff, the space shuttle is carried to the launch pad atop the 6 million-pound crawler transporter at a blazing pace of less than a mile an hour. Not exactly warp speed.
At our peak carrying full load, we get right around 38 feet per gallon.
Not too bad for an original 1965 hybrid vehicle with low miles. The 3.4-mile journey takes up to 6 hours. Just enough time to appreciate the route's picturesque surroundings. Kennedy Space Center is situated on a national wildlife refuge. Bald eagles, osprey, and vultures are just a few of the scores of bird species regularly spotted in local skies. Both land and sea are home to a wide variety of creatures, including manatees, dolphins, and of course, the ever-present alligator. Visitors are always urged to watch their step. Now on the launch pad, the orbiter is ready to take on its main payload. Testing assures that the multi-ton cargo is secured and safely stowed in the payload bay before the technicians certify the orbiter is ready for launch. Flying T-38 aircraft from Ellington Field in Houston, the crew members arrive at Kennedy's shuttle landing facility.
But finally the day comes when you're there and you're getting ready to launch. And you go into launch countdown and it's like going up the hill on that roller coaster. It's full of expectation and you're both thrilled and terrified at the same time because anything could go wrong, but when it goes right, it's a thing of beauty.
If there are no issues or concerns, technicians begin fueling the external tank with volatile liquid hydrogen and oxygen.
the predominant emotion is pride. There's a tremendous sense of pride in all that not only that you do, but that your teammates do, that people in this very firing room do, and folks all across the country.
This is shuttle launch control, T-minus 9 minutes.
At the T-minus 9 minute hold, the launch director leads one final poll.
We finally come out of the hold at T-minus 9 minutes. I sit back and I watch my data, but I know that there are souls on board that ship whose lives are depending on the launch team to make the right decisions.
And we can see on through just
I don't think about that consciously. The decision-making authority and responsibility, I know it's there, but I do think consciously about the crews and the people we're about to put on top of a controlled explosion and get to orbit.
This is the NTD conducting the launch status check. All stations verify ready to resume count and go for launch. OTC go. TVC go. ETC's go. LPS is go. Houston flight is go.
After nearly 3 years, hundreds of thousands of hours logged by engineers, technicians, scientists, seamstresses, electricians, and other program workers across the globe.
We have main engine start. 2, 1. Booster ignition.
The shuttle makes its way skyward. At liftoff, 6.6 million pounds of thrust begin hurtling the vehicle and crew at speeds that'll reach 17,500 miles per hour. The shuttle is like no other machine ever built. For its launch to succeed, more than 1 million parts must move together perfectly. How this engineering marvel came to be is an amazing story that begins in the early 1970s. The Vietnam War is divisive and costly. The economy is sliding into recession. And with the race to the moon already won, the Apollo program is canceled. A new mission is sought for NASA to send humans into space. But Mars, for many the next logical step on the path of exploration, is dismissed as too costly, a destination for a country preoccupied with events back on Earth. Instead, on January 5th, 1972, another destination is selected, low Earth orbit. As early as the mid-1960s, NASA had concluded that the technology was available to build and fly a reusable spacecraft.
President Nixon really liked the idea and told the NASA administrator, go do it. And the NASA administrator got a call from OMB the next morning, someone there, and said, hey, what the president really meant to say was, you're going to get this much money, and so do as best you can with the space transportation system. And our choice, logically, was you have to have a vehicle first, and so that was the birth of the space shuttle as the first in the 3-part space transportation system.
Many designs were considered. Often, they combined the best features of different concepts.
At that time, they were looking at having jet engines on the shuttle for landing and for transporting it across the country.
The idea of the lifting bodies was to bring astronauts home to conventional runway landing. Previously, all of our spacecraft, which were capsules, came down in the ocean. Someone came up with the idea of a vehicle that could land like an airplane.
The key thing was to understand aerodynamic stability across the hypersonic, supersonic, subsonic, and landing speed type of environments that a single vehicle has to fly safely. That was the key thing that was learned from those, and you'll see it reflected in the shape of the space shuttle.
One was the use of a lifting body, an aircraft with no conventional wings. Only its fuselage would keep the aircraft airborne and guide it safely back to Earth.
They were known as the flying bathtubs. For the first test, the M2F1 was towed behind a car, souped-up Pontiac. Whitey Whitesides drove that Pontiac across the lake bed at about 120 miles per hour, dragging this flying bathtub behind it.
As well as groundbreaking, their tests could also prove ground shaking. The X-24B, a lifting body with wings, was the first such craft to land on an actual runway, as all shuttles would eventually do.
Early on, the space shuttle was going to have jet engines to return for horizontal landing, much like an airliner. The X-15 had proven fairly specifically that they could make horizontal landings very accurately, unpowered, flying a steep glide slope, that they could do a horizontal, unpowered landing with the shuttle.
As they tried to narrow its size, shape, and weight, engineers also considered how this new orbiter would be propelled safely out of the reach of Earth's gravity. At the Marshall Space Flight Center in Huntsville, home of the rockets that had sent every Mercury, Gemini, and Apollo astronaut into space.
All engine running. Liftoff. We have a liftoff.
Design teams would devise the partially reusable propulsion system that would finally be adopted.
The main engines were always something we paid very close attention to. Lots of moving parts, lots of high energy in very tight places, and very cold liquid on one side of a very small wall and very hot on the other side. When that thing finally lit off, for me, it just showed the power of a space shuttle main engine, and then there's 3 on the back of an orbiter, and then there's the 2 solid rocket motors. That was probably the spark that got me so interested in the space shuttle program in general, and what it took to actually get one engine to light, much less 3 and 2 boosters to take the shuttle to orbit.
As for the orbiter, spiraling costs forced NASA to abandon equipping it with its own jet engines and escape pod.
Originally, it was going to be an air-breathing airplane that would fly to space as a rocket and then come back to Earth. The orbital maneuvering system pods that sit on the back now were to be where deployable air-breathing engines would come out, and it would be able to fly from its intended point of landing to another place if the weather were bad or something like that.
NASA's new shuttle would essentially glide its way back to Earth. Producing the components of this new space transportation system fell to familiar names in the space industry. Prime contractor Rockwell North American, now Boeing, had built the Apollo Command Service Module. Morton Thiokol, now ATK, would build the solid rocket boosters, and Martin Marietta, now Lockheed Martin, would construct the ET. Responsibility for producing the space shuttle's main engines went to Rocketdyne, now Pratt Whitney.
There was a lot of teamwork that was going on. It was bringing people from all across the country, from Kennedy, from Johnson, from Marshall. So many people involved that had to work together. Now, at the beginning, there was a lot of anxiety that we weren't going to work together. But when people got to know each other and could trust each other, that's when the work began.
It was an amazing vehicle, and in a lot of ways way ahead of its time. To have a reusable spacecraft that could carry such tremendous amounts of cargo to space was unprecedented.
September 1976, more than 4.5 years after President Nixon signed off on its development, America's new spacecraft, Constitution, gets its first close-up before the cameras. The orbiter itself was well received by the public, but impassioned fans of a particular long-canceled television series called Star Trek wanted it called something else. They staged a successful write-in campaign, and the orbiter was renamed for the Starship, featured on the show. Thus, NASA's new shuttle would be the Enterprise, boldly going as no spacecraft had ever gone before. Whatever its name, this bird still needed to prove it could fly. In an age before computer simulations, balsa wood models and wind tunnel testing was the only means to test the airliner-sized glider.
We put together a very aggressive flight test profile that consisted of data points continuously all the way down. There was not a matter of 10 seconds went by without another, either pitch doublet or a rudder kick or an angle of attack sweep. The things that really turn on a test pilot to fly them as accurately as possible.
August 12, 1977. On a crystal clear California morning, high above the Mojave Desert, two NASA test pilots ready for Enterprise's first flight. The plan was for Fred Hayes, Jr. and Gordon Fullerton to lift the orbiter off a modified 747, then land on a dry lake bed 15,000 feet below.
The thing that we were most concerned about was if we were going to be able to get to a launch speed, if Fitz Fulton was going to be able to put the 747 into a slight dive so that we would have enough lift on the Enterprise to, when we did push the separation button, blow the bolts, to lift away from the airplane without hitting Fitz's tail. And of course, both of us were interested in that happening.
The pilots on the 747, Fitz Fulton and Tom McMurtry, sit and wait for the command to release and steer their massive aircraft out from under Enterprise.
There were still questions about was it going to actually happen as we expected from those simulations and the analysis and everything. There's a very loud thump when the shuttle separates. There was always a question, was the shuttle going to slide back and hit the tail of the 747? But we couldn't see that, but we could, after a few seconds, we could tell it didn't hit us. And so the chase called clear.
Once we reached the 240 knots and Fitz called on speed, I think he really pushed some of the sensors he was looking at in order to let us get to there, and we appreciated that. But once we heard Fitz say on speed, I pushed the separation button and we just broke free. We had about 1.5 Gs of lift.
Honestly, that was probably the most exciting moment in the approach and landing test, to feel and be there when the shuttle separated from the 747.
By all accounts, this first freefall test is a success. 5 weeks later, Enterprise is brought to 22,000 feet for her second freefall test. Pilots Joe Engle and Dick Truly have only 2 minutes to capture flight and maneuvering data before landing the aircraft again without any engines.
It was a real team effort, and the challenge was for Dick Truly and I to fly that profile and fly those data points, those maneuvers, as precisely as possible to give them the best data possible. It was a test pilot's dream.
A total of 16 taxi, captive, and drop tests confirmed the soundness of the craft's design and green-lighted production of the first space-worthy orbiter. Columbia, NASA's first orbiter, is fittingly named after the first American vessel to circumnavigate the globe. However, Columbia quickly becomes a daunting challenge for NASA. Its complex makeup had engineers struggling constantly to reduce Columbia's weight and simplify construction. Especially frustrating was keeping the orbiter's ceramic tiles attached to its fuselage. More than 25,000 of them fit together to protect Columbia from the searing 3,000-degree heat of re-entry.
We were having a lot of problems with the thermal protection system of the tiles. The way we were trying to glue them on, they wouldn't stay on. And we had to come up with a way of making sure that they'd stay on. And we had some really great people that worked that, and that's why it took such a long time. I had hoped it was not going to take that long, since John and I were named as a crew, so we had a lot more time to train than what we'd both initially planned.
The requirement was to be able to handle temperatures like 2,500 degrees F that occur on the surface of the TPS, and that's 5 times what your oven is at home that you bake cookies under at max. The other problem is weight, because after all, this is an airplane. So you can't have a metallic system on it that weighs tons. It has to be extremely lightweight. And in fact, the shuttle tiles are about 90% air, and that gives the combination of being able to be temperature resistant and yet at the same time light.
Each orbiter has a unique number of protective tiles. Challenger was built with the most, 31,000, 1,088, while Atlantis has the fewest, a mere 24,177.
Over at Palmdale, they had put on their first effort of putting the tiles on to protect the aluminum from the heating they were going to get on reentry. And some of those tiles, when they put them on in the daytime, next morning the tiles were on the hangar floor. And so that was real scary that we could lose some tiles while they were on orbit and really have a problem with the heat coming back on reentry.
Columbia had a lot of tiles missing yet, needed quite a bit of work before we could deliver it to the Cape, and we scrounged throughout the city of Lancaster for RTV, which was the material we used to glue the tiles on with.
More glue did keep the tiles in place. However, water was literally ripping them apart.
It turns out, in the instant we hit rain, the tiles almost exploded.
The tiles fabrication process was modified, and the problem overcome. Other shuttle design features proved less problematic and more groundbreaking. A computerized digital flight control system, now common in commercial and military aircraft, was developed for the orbiter.
In flying the space shuttle, you were so aware that you weren't necessarily talking to the shuttle, you were talking to a computer who in turn was going to talk to the shuttle.
Barriers of race and gender were falling everywhere, and America's core of shuttle astronauts would become more reflective of the nation it served.
There's been a lot that the shuttle era has done to bring space flight into the domain of the average person. We know it's not just crew-cut white test pilots anymore. It's essentially the United Nations that flies on the space shuttles. It's people of every description that look very much like the rest of us.
The astronaut selection process reflected a changing nation and a changing NASA.
At the time, all the astronauts were military test pilots and there were no females, so it was kind of like one of those dreams that you hope will happen someday, but you didn't really think would.
The NASA astronaut class of 1978, the largest in the agency's history, came from all walks of American life. Physicists, meteorologists, fighter pilots, scientists, and for the first time, women and African Americans.
When I came into the astronaut program in '78, there were 3 African Americans that came in at the same time, and it was the first time that NASA had hired African Americans. We had Fred Gregory, who was a test pilot, and then Ron McNair, who was a mission specialist, and I came in as a mission specialist. So all 3 of us were excited about flying in space, and all 3 of us recognized that we were really going to open up the envelope for other African Americans to fly in space.
While the new class of NASA astronauts trained for subsequent shuttle flights, Columbia was undergoing preparations for the program's maiden voyage, STS-1. Veteran astronaut John Young, one of the 12 men to set foot on the moon, is in command. His pilot is first-time flyer Bob Crippen.
To be sitting on board up there with my buddy John Young and get to experience the whole thing from ascent and being on orbit to flying re-entry, it was one of the high points of my career.
Together they would travel over 1 million miles and circle the Earth 36 times.
The launch finally occurred. We'd been waiting and postponing, and when it finally lifted off and we knew it was going and achieved orbit, we were all in anxious anticipation for what was going to happen next.
Launched like a rocket 2 days earlier, Columbia lands as a glider on the dry lake bed of Edwards Air Force Base in California.
Watching out the window, watching the sea and the clouds rush by, it actually gave a sense of speed, more so than when we were up in orbit, being much higher. I think they were all very relieved because there had been some concern because we had lost some time on the bottom or not. Flew down over the San Joaquin Valley. We do a big turnaround to land on the lake bed for that first flight. I remember when John went into a bank, a big left bank, I look down at the lake bed, and there's thousands of people out there. And John, look at all those folks with Ted come out to see us land.
Joe Engle was chased, and hear his voice coming in on final, talking to John Young and Crip in the airplane that they were right on glide slope, coming in for a landing, and then have that landing, and then have John Young do his Young dance. He was just so elated. It was such a magnificent flying machine to him at that time.
The first time I really saw a real shuttle was Columbia, when it was out on the lake bed after the landing, and I'm walking around it. I couldn't believe they sent that big a mass up in the air.
People really thought this was all impossible. So what we have done and shown and demonstrated through the shuttle program is we've shown that we can take the impossible and make it possible.
Thousands of spectators line up along the landing strip to greet the shuttle and its two-man crew.
Anyone who was associated with the program or there just to see the shuttle return, I think felt a lot of pride in our country and our space program. And so those emotions were, finally released, and you said, wow, the flight was done safely. They're back home. The shuttle really does work. It's a great program. It's got a great future ahead of it.
Hey, this thing works, and we got it back all in one piece, which is what we wanted to do.
While Columbia's return was spectacular, it would renew NASA engineers' worries about the shuttle's thermal protection system. During the post-landing inspection, 148 of the orbiter's tiles were found shattered, and 16 more were missing due to the effects of an overpressure wave. While that and other issues were addressed, the 50-ton Columbia would be placed atop the specially configured 747 and ferried back to Florida and processing for its next mission.
It's a massive enterprise. It's over 8 stories tall, sitting on the ground, and you never get over that site. It's really awesome.
After the shuttle lands, there's a processing procedure for the shuttle. Post-flighting it, checking the tires, checking the struts, get the correct measurements. And then when the shuttle is ready to mate with the 747, we would tow underneath, and then they would lower the space shuttle down on the supports on top of the aircraft. We would take off.
On takeoffs from the extra-long runways of Edwards Air Force Base, the shuttle carrier aircraft's crew of 4 would soon grow accustomed to the smell of burning rubber. That's the intense heat generated by their plane's spinning tires as they carried 2 massive aircraft at more than 100 miles an hour. The average range of a 747 is about 5,000 miles, but due to its weight, configuration, and special flight requirements, the SCA can travel only 1,000 miles at a time. A full turn in the jet can take several zip codes.
32.5. Switching now, thank you.
Cruising at more than 250 miles per hour, the jumbo jet burns 40,000 pounds of fuel per hour. That's 130 pounds per mile, or the length of a football field per gallon. No wonder it has to make several stops before reaching Florida's east coast.
We would get a spacecraft back, go over it again, be sure that we could reuse it, repair it where we had to do. It had never been done before. And so I think that's one of the marvelous things about the space shuttle was we found a way to turn this spacecraft around and use it again.
Before the end of 1982, Columbia would fly 4 more missions.
Liftoff of America's space shuttle,
including STS-5, the first with a crew of more than 2 astronauts. Challenger, the second orbiter in the shuttle fleet, made her maiden flight on April 4th, 1983.
and liftoff of the orbiter Challenger and the 6th flight of the space shuttle.
STS-6 deployed a communications satellite and featured the first spacewalk of the shuttle era. Just 2 months later, Shuttle Challenger was back in orbit, this time with the first American woman in space. Physicist Dr. Sally Ride was a member of Commander Bob Crippen's STS-7 group that deployed Canadian and Indonesian satellites during the 6-day mission. Challenger was readied for flight in less than 2 months, another massive first. Shuttling the first African American to space, and Air Force combat pilot Guy Bluford.
For me, it was an exciting moment because it was something that I had been training for 15 to 16 months, and so I was looking forward to the experience of flying in space.
We are in an era of brotherhood.
We have liftoff of mission 41D, the first flight of the orbiter Discovery.
From 1984 to 86, the newest orbiter Discovery would fly a record 6 missions.
And liftoff of mission 51D and the 7-member crew of Discovery.
Carrying into space satellites, international astronauts, even a U.S. senator and a congressman. 1 year after Discovery's debut, Atlantis flew her first mission.
Liftoff of Atlantis. A new orbiter joins the shuttle fleet and it has cleared the tower.
STS-51J. It was also one of 7 classified missions the space shuttle would fly for the Department of Defense. By the end of 1985, the space shuttle program had completed 23 missions, including 9 that year alone. Each successful flight had the unintended consequence of convincing some that spaceflight, once considered among humankind's most inherently dangerous endeavors, had become routine. That notion would soon be tragically dispelled.
Well, I am so excited to be here.
Amid much fanfare, Krista McAuliffe, an elementary school instructor from Concord, New Hampshire, had been chosen from among 11,000 applicants to be NASA's first teacher in space.
I would like to humanize the space age by giving a perspective from a non-astronaut, because I think the students will look at that and say, this is an ordinary person. This ordinary person is contributing to history, and if they can make that connection, then they're going to get excited about history, they're going to get excited about the future, they're going to get excited about space.
The American public's interest in its space program was renewed by her participation and was eager to see her off. Commanding the flight was Dick Scobie. His pilot was Michael Smith. Serving as Challenger's mission specialists are Judy Resnick, Ellison Onizuka, and Ron McNair. Joining McAuliffe as a payload specialist was Greg Jarvis. From the start, STS-51L was plagued by delays, mostly due to unseasonably cold temperatures in Florida. Rather than give pause for thought, the delays only tried the nation's patience. Everyone, it seemed, was itching to go. January 28th, the ground temperature at Launch Pad 39B was a frigid 36 degrees. Ice could be seen on the launch vehicle. Despite concerns voiced by some, shuttle managers reluctantly decided to press ahead for a late morning liftoff.
6, we have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Challenger, go at throttle up. Challenger, go at throttle up.
At 11:39 Eastern, twice the speed of sound, the Challenger's fuselage breaks apart from the inside out. America's space program suffers its first fatalities in flight.
God, no.
All 7 Challenger crew members perish.
Okay, everybody, stay off the telephones. Make sure you maintain all your data. Start pulling it together.
We come together today to mourn the loss of 7 brave Americans, to share the grief that we all feel, and perhaps in that sharing to find the strength to bear our sorrow and the courage to look for the seeds of hope.
The investigation, headed by former Secretary of State William Rogers, would fault a solid rocket booster O-ring, rendered defective by the bitter cold. But the Commission's findings also addressed the human factor, the role played by shuttle program managers in sending Challenger aloft that day. The shuttle program came to a halt. It took more than 2.5 years of arduous engineering analysis and painful soul searching before a retooled and reborn shuttle would return to flight.
Challenger was tough because it not only represented a breakdown in communications, but it represented everything that's wrong or wrong about an agency like we are, where segments of the agency weren't talking to each other and didn't know everything that we should know.
We thought we knew where all the risks were and had them pretty well contained. The solid rocket boosters that caused the accident, obviously there was something that had slipped through. So we went back throughout the complete vehicle, all the systems, and did a complete review and trying to find any other things that we may have missed that may be lurking there.
When things are really starting to look smooth and you're starting to get maybe overconfident in a way, then it's time for you to step back, think about what you're doing, go back and look, do some additional testing, and see if there's something that you really hadn't anticipated that is going on with your system.
During a lot of that time, we got a lot of criticism that maybe the agency had lost its edge. There were folks inside the agency that started losing their confidence, thinking maybe we can't do this anymore. 2.5 years later, when we flew and then landed that flight, it showed that no, we really can overcome really, really large problems, really tough technical problems today, just like we could 10 years ago, 20 years ago, or 50 years ago. That was an important milestone.
Liftoff. Americans return to space as Discovery clears the tower.
On September 29, 1988, 975 days after the loss of Challenger and her crew, the orbiter Discovery returned 6 veteran astronauts to space to deploy a tracking and data relay satellite important to a number of NASA missions. STS-26 proved a comeback milestone for the space shuttle and initiated a tradition that survives with the program today.
During the flight, we had roses show up in the Mission Control Center. 6 roses, 5 red, 1 white. And there was a card attached to it, and it simply said, "Congratulations, return to flight, we wish you well." And it was signed Mark, Terry, and Mackenzie Shelton. Didn't know who they were, but after the flight, we through the Foro company, we tracked them down so we could send them some pictures and something to thank them for sending the roses to Mission Control. So the next flight, roses show up again. And again, it's 5 roses for the members of the crew and 1 rose for those who have lost their lives in this endeavor. And so this family, they have become part of our family, and they haven't missed a flight since. Every flight since that time and to date, and I suspect they're going to go right with us to the end of the shuttle program.
STS-26 ended on October 3, 1988, at Edwards Air Force Base, California.
Standing by for nose gear and touchdown.
With Discovery's safe landing on runway 17, the triumphant crew was greeted warmly by Vice President George Bush on behalf of a proud and grateful nation.
There's something special about a return to flight that makes you have some trepidation because it's still fresh in your mind that you're frail and you can make mistakes and you're human.
In the spring of 1990, the $1.5 billion Hubble Space Telescope was loaded into Space Shuttle Discovery's payload bay, and on April 24th was sent aloft to be deployed to Earth orbit on STS-31.
Capcom, we have a go for release. Discovery, go for Hubble release. Okay, we have a go for release.
As envisioned, Hubble would return never-before-seen images detailing our universe as it was millions upon millions of years before. Soon it would become clear that Hubble pictures were not.
Several days later, if not a couple of weeks, we found out after we were back on Earth that it had a problem with its vision. And most of us were just devastated, that here we had this marvelous instrument that we had put on orbit and it was going to be useless. It turned out that it wasn't useless at all because even with its flaw, it was still a much better telescope than anything that we had, on Earth.
A shuttle mission dedicated to the telescope's repair was planned. In essence, Hubble's nearsightedness would be corrected with a new pair of glasses.
Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
We finally flew STS-61, which was the first Hubble servicing mission. Absolutely incredible mission.
Clearly we have a dynamic situation.
You cannot take the 84-inch mirror out of the telescope. It's part of structure, too big, it's there. So by putting in one box called CoStar,
we're able to correct the aberrating light for 5 other instruments.
Of all the space shuttle missions we've flown, it was without a doubt the most ambitious flight, but the one that I think demonstrated NASA's can-do attitude, its technological skill, its technical capability, and the spirit of its people.
2 teams of astronauts made a record 5 back-to-back spacewalks to refurbish Hubble and realize her potential to awe and astound. While Hubble's servicing missions were very important, the true gift of a maneuverable shuttle was soon realized in a very different rescue mission.
Booster ignition and liftoff of the maiden voyage of Endeavour on a satellite rescue mission.
Months earlier, in May of 1992, the 7 astronauts of STS-49 overcame initial setbacks to pluck the $180 million Intelsat 6 communication satellite from an unusable orbit.
It was going to be a very simple rendezvous, get close, bring the satellite down close and grapple it with the remote manipulator system. Everything that could go wrong went wrong.
We got up there to capture it. The bar, we tapped the satellite with the bar, and the satellite started moving out of control.
Get me in. Pitch me over. Into the arm. Watch the end of the arm.
That's a singularity again.
You're going to have to get out of there.
It can be very difficult catching something like a tumbling satellite in space. The slightest touch or mistouch by the astronaut with the equipment, and you can send that satellite tumbling.
Here, make sure that when you want me to yaw right, you say yaw right. Okay. Any other time right is just right. Yeah, that's what I'm doing. Okay. We're moving.
And so it was very touch and go on that mission, actually.
Commander Dan Brandenstein and pilot Kevin Chilton are preparing for the upcoming terminal initiate burn.
After several days of failed attempts with Endeavour's remote arm, Commander Dan Brandenstein literally tries a new approach.
Yeah, real easy, guys. Real easy. Don't bring us any closer, Dan. Okay, I'm stopping it.
At Endeavour's helm, Brandenstein delicately maneuvers the orbiter up to the 4.5-ton Intelsat 6.
The satellite is rolling out of control in 3 different axes at once, and you could actually fly the shuttle and fly this maneuver around and keep it aligned with it.
Right here. 3 people grabbed 18,000 pounds.
Aware that any miscue could endanger not only the satellite but also the ride home, spacewalkers Pierre Thuot, Tom Akers, and Rick Heeb reach out and secure the satellite by hand.
Okay. Wait. Let's do it. Got it. Easy. Give it time. All got a good grip? Yes, sir. Houston, I think we got a satellite.
Yeah, nice job, guys.
Intelsat 6 is released from the cargo bay with a new mini-rocket motor for a gentle push to its proper orbit, where it remains today, fully functional. And as the shuttle program matured, so it seemed did relationships between the world's spacefaring nations. On STS-47, the 50th Space Shuttle mission saw the orbiter Endeavour back in space on September 12, 1992. The mission was a cooperative Spacelab venture between Japan and the United States that brought the first Japanese astronaut into orbit as a member of the 7-person shuttle crew.
The Space Shuttle has launched people from different nations around this world that used to feel they could never, ever work together. And it has ushered us from the Cold War to this really cooperative space program that we have with our international partners, including the former Soviet Union.
Regardless of what language you speak and love space. And that's pretty cool. We have a lot in common with engineers and scientists around the world, and that's kind of fun to work in a program like this.
On February 3rd, 1995, Eileen Collins, the first woman to pilot a shuttle, was at the helm as Discovery gave the U.S. its first up-close look at the Mir space station. Collins flew the shuttle through a series of intricate maneuvers, approaching within 37 feet of the Russian spacecraft, and later performing a fly-around by hand.
And liftoff of the Space Shuttle Atlantis on a mission that will herald a new day of international cooperation in space.
4 months later, on June 27, 1995, Shuttle Atlantis would lift off from the Kennedy Space Center to begin STS-71, the U.S. space program's 100th human space mission. It would take 2 more days before Atlantis caught up with and performed the first shuttle docking with the Mir space station.
Houston, Atlantis, we have captured.
Orbiting 220 miles above the Earth, a most unique and historic celebration took place. As the Mir space station welcomed its first American guests, cosmonauts and astronauts together broke figurative bread, tortillas and fruit to be exact, in a renewed spirit of cooperation. Together, Shuttle and Mir formed the largest flying spacecraft the world had yet to see. It tipped the scales at 250 metric tons, more than 500,000 pounds. Between 1994 and 98, the Shuttle Mir program would involve 11 shuttle missions, including in 1996 STS-76, which began a continuous U.S. presence aboard the Russian space station with a visit by Atlantis. Barely fluent in Russian, astronaut Shannon Lucid, a biochemist, embarked upon a mission that would dramatically enhance our understanding of life in space. When she finally landed at Edwards Air Force Base on Shuttle Atlantis, she held the female space endurance record for spending 188 days in orbit. A hero's welcome was in store.
I'm here to say welcome home to Shannon Lucid.
By the time Shuttle Mir ended with STS-91, 7 American astronauts had completed extended stays aboard the Russian space station.
Tatiana Mativa, who I became very good friends with, and I remember us sitting in Red Square having dinner together with a full moon, and remembering when I was a child all those parades, those May Day parades with the tanks going by, and here we were sitting there having a nice dinner under the full moon and with a lot of friendship. So it just goes to show how space can unite people, and that's I think one of the biggest benefits.
8 cosmonauts had flown to Mir on the U.S. shuttle, and NASA astronaut Norm Thagard had become the first American to fly there or anywhere aboard a Soyuz spacecraft. In 2001, 15 years after its commissioning, Mir would be abandoned to break up and burn in Earth's atmosphere. By then, the process of building upon Mir's legacy of international cooperation in space had already begun. Whereas STS-61 had helped establish the Hubble Space Telescope as an icon of American ingenuity, STS-95 would update the hero's credentials of one John Glenn. On October 29, 1998, almost 37 years after becoming the first American to orbit the Earth as an original Mercury 7 astronaut, Glenn, now a 77-year-old former U.S. Senator, made his return to space. In contrast to his first flight, a 3-orbit, 4.5-hour foray inside the snug Friendship 7 capsule,
The liftoff of Discovery with a crew of 6 astronaut heroes and 1 American legend.
STS-95 would take 8 days and circle the Earth 134 times.
My main reason for being on that shuttle flight was to do research on aging. I was 77, we went up, and you know, NASA has charted some 52 different changes that occur in the human body when you go into space for a period of time. And several of those are very similar to what happens to the natural process of aging right here on Earth. Body's immune system changes. You get less resistant to disease and infection. Body's ability to absorb protein back into the muscles changes for the young people up there and for elderly here on Earth. The objective was to take those things that are the same and see if we couldn't find any differences between my experience up there and the younger people I would fly with the idea of finding in the human body what turns these different systems on and off. If we could do that, we might be able to make it possible for people to stay in space longer without harmful effects, and maybe cut out some of the frailties of old age right here on Earth. I really was happy to be assigned to that flight.
In an interesting twist of fate, astronaut Glenn not only inspired both the young and old around the globe, but also a fresh political science and economics graduate, Lori Garver, the 18th Deputy Administrator of NASA.
Having the ability at NASA to fly him again in space after his first flight was something we, I think, gave the nation, and it really helped explain what we were doing on the space shuttle. John Glenn was very, very focused on doing those experiments for both, I think, the older generation, but he was also an inspiration to people growing up.
Discovery carried a variety of payloads and research experiments. Arguably, the one most valuable was Glenn himself. Not only did he provide first-time data on what spaceflight might do to the body of a septuagenarian, Glenn also renewed the interest of the nation and the world in America's space shuttle program. While the program had and continued to successfully deploy and service science probes and satellites, as well as conduct on-orbit research, the space shuttle undertook a new long-range task perfectly suited to her specialized capabilities.
You've got a spacecraft that can carry at least 7 people into orbit, and with those 7 people, you can do a huge amount of work. One mission, you can do multiple EVAs, you've got multiple crew members, you've got a huge payload, just all kinds of capabilities to be able to construct and build bigger things in orbit.
Less than 2 weeks after Glenn's return to Earth, a Russian Proton rocket departs the Baikonur Cosmodrome in Kazakhstan, carrying the Zarya module, the first component of the new International Space Station.
Liftoff of the Proton rocket and the Zarya control module. The International Space Station is underway.
2 weeks after that, Space Shuttle Endeavour follows up with delivery of America's Unity module, the second piece of this largest space station puzzle ever to be constructed.
Houston Endeavour, we have capture of Zarya.
Not until July 2000 will the Russian Zvezda module be added, finally allowing for 2 Russian cosmonauts and their American Expedition 1 commander, Bill Shepard, to journey aboard a Soyuz spacecraft to the International Space Station and begin humankind's continuous extraterrestrial presence.
Across the world, people are very, very interested in and delighted by the International Space Station and the science that has taken place there.
Since only an orbiter's payload bay could hold the station's largest components, the multi-year, multi-mission building, outfitting, and servicing of the ISS with cargo and crew would become primarily a job for the shuttle. Amid these dynamic station building missions, one seemingly simple and relatively uncomplicated flight would prove problematic and threaten the very future of America's human spaceflight program. Since 1988, the Space Shuttle had completed 15 years of successful missions. Each was unique, each had its own specific goals and tasks, and each had its own dedicated crew of astronauts who'd trained exhaustively to meet and carry them out. Yet each of those 87 flights did have 2 things in common: a safe launch,
liftoff of the Space Shuttle Discovery,
and a safe landing.
Nose gear touchdown.
From the start, STS-107 seemed to be a mission out of sorts. By the time Columbia was finally ready to fly on January 16th, 2003, its planned 16-day mission had been delayed no fewer than 18 times. All those delays had ultimately positioned the STS-107 as a sort of black sheep on the Space Shuttle program's launch schedule. Columbia's crew commander Rick Husband, pilot Willie McCool, and mission specialists Michael Anderson, Kalpna Chawla, Dave Brown, Laurel Clark, and Israeli astronaut Ilan Ramon would not go to the International Space Station. Their flight would require nothing more risky than orbiting the Earth.
Booster ignition and liftoff of Space Shuttle Columbia with a multitude of national and international space research experiments.
82 seconds after launch, what was later described as a suitcase-sized chunk of frozen foam insulation breaks off Columbia's external tank and strikes the leading edge of the orbiter's left wing.
Roger, roll, Columbia.
A routine same-day video review of the launch would reveal nothing unusual. However, higher resolution tracking camera film processed overnight and reviewed on flight day 2 by the mission's ascent team showed otherwise.
You saw this little thing float toward the leading edge of the wing and like, it was like a snowball hitting something and then just being pulverized. But when you saw it hit, we just winced. Because we knew, the vehicle's going 500 miles an hour or better. It was inconceivable in hindsight that you could have that kind of impact at the speed that the vehicle was going and assume that there was no damage. And that's what we allowed ourselves to feel comfortable that we were right and we were dead wrong.
Due to limitations in the visual clarity, the exact point of impact and extent of any damage could not be determined. If the foam strike had compromised Columbia's integrity, little, if anything, could be done to repair the orbiter in space. 1 week after launch, Mission Control emails the crew informing them of the debris strike. Save for a relatively minor problem with a leaky refrigeration unit, STS-107 had been without further incident. As scheduled, the order is given on the morning of February 1st for the Columbia crew to begin the landing procedure and come home to Florida. Traveling in excess of 12,000 miles per hour, the orbiter's belly begins to glow red as it descends into Earth's atmosphere.
FYI, I've just lost 4 separate temperature transducers on the left side of the vehicle, hydraulic return temperatures.
As reentry started and as the ground track went across the states, the ground track, of course, changes color. You can tell where the shuttle is over what part of the country it is.
No onboard.
Well, that display stopped updating. In other words, that display froze in a certain position. Well, sometimes you have loss of data, you have some problem with the system on the ground where you'll have those kind of outages temporarily. Well, this lasted a bit longer. Then the call went up to the crew. A call went up and no response. Well, I don't know, I just began to feel uneasy.
Columbia, Houston, UHF, comm check.
At speeds above Mach 20, the stress becomes too much for the orbiter.
We do not have any valid data at this time.
The suitcase-sized chunk of foam had indeed punched a bowling ball-sized hole in the leading edge of Columbia's left wing. Within seconds, internal temperatures spike, signaling the cascade of structural disintegration. Only 16 minutes from home, Space Shuttle Columbia breaks apart in the skies over East Texas. All 7 crew members are lost.
GC flight. Flight GC, lock the doors. Copy.
And at that moment, I knew we lost him.
The grief is heavy. Our nation shares in your sorrow and in your pride. And today we remember not only one moment of tragedy, but 7 lives of great purpose and achievement.
Within days, hundreds of professionals from federal and state agencies across the country arrive in East Texas. They are joined by local volunteers to help NASA recover and catalog debris from Columbia in the hopes of, literally, piecing together an answer to the accident's cause.
This is one of the many obstacles investigators are up against.
It was really heartwarming and very emotional for me to see all of these people from around the country come in to the Piney Woods of East Texas and spend days and weeks there marching out through the woods looking for bits and pieces of the orbiter and so forth. If anybody ever wonders about the strength of the backbone of this country, then they ought to have the privilege, like I do, to meet these people who have come here to do this. It shows you the fabric of what this country is made of.
Determined to return to flight, stronger and safer, the grounded shuttle program had taken a fresh look at itself.
During my watch, we lost the Columbia crew, and clearly as a flight director back in Challenger, we lost that crew. I think about those every day. Every day I come to work. I need to be very vigilant. I need to pay attention, and I need the people that work for us in this business to pay attention to what they're doing, because this is hard stuff that we do. It's very dangerous. We have not figured out a way to do a beam me up Scotty. Right now it takes a lot of hydrocarbons moving at very high speeds through fuel pumps at very high temperatures, high pressures to get into space, and it takes a tremendous amount of effort to get out of space back in the atmosphere and get home.
I was sent out to David Brown's parents' home. I'll never forget this moment when Judge Brown looked at me and said, "Leland, my son is gone. There is nothing you can do to bring him back. But the biggest tragedy would be if you don't continue to fly and carry on his legacy."
Each of the remaining 3 orbiters was pulled apart and refurbished. New capabilities were devised for the crew and mission controllers to assess and repair damage while on orbit. Processes and procedures were also re-examined and reinvigorated. Crew safety would never again be taken for granted. Nearly 2.5 years would pass before the nation would see another orbiter poised for launch from the Kennedy Space Center.
By the time that we fly the flight, it's something that it feels like we have flown many times. So if things don't go well, it becomes very, very natural for us to know at certain points during the mission, if this doesn't go well or if this significant system breaks or we have this type of emergency, what's the most important thing we need to do now, because we've been rehearsing it. And it makes it look really easy. You don't really get the full effect of how much real preparation, how much real studying went into making it look that easy.
Of all the changes accompanying the shuttle's return to flight, none was more significant than the one announced in early 2004 at NASA headquarters by President Bush.
Our first goal is to complete the International Space Station by 2010. We will finish what we have started. We will meet our obligations to our 15 international partners on this project. The shuttle's chief purpose over the next several years will be to help finish assembly of the International Space Station. In 2010, the Space Shuttle, after nearly 30 years of duty, will be retired from service.
Even though each shuttle was designed to fly 100 missions, the Columbia Accident Investigation Board called the shuttle an aging spacecraft, with the odds of losing another orbiter and crew increasing with each subsequent flight. NASA's human spaceflight program was faced with several basic challenges, including coming up with a successor to the shuttle fleet. However, with an impending cancellation of the shuttle program looming, shuttle managers recommitted themselves to the paramount task of safely completing the International Space Station. It would become the program's mantra, to be repeated over and over again, not only to the media, but also for every worker in the shuttle program. No launch schedule was too tight, and no mission too important to be rushed.
We ought to treat every flight, in a sense, as a return to flight. This is truly a test program. We go back, we make sure everything is right, we double check, and then we go commit in a flight readiness review that we're actually ready to go fly.
On July 26, 2005, Discovery gets the shuttle program flying again.
This is Shuttle Launch Control at T-minus 3 hours as our pilot, flight engineer. We're now into the suit-up room.
LRD is go. SRO. SRO is go. So on behalf of the many millions of people who believe so deeply in what we do, good luck, Godspeed, and have a little fun up there.
Thanks to you, to the launch team, and to everybody in the shuttle program. The crew is go for launch.
T-minus 10 seconds. Go for main engine start. 7, 6, 5. 3 engines up and burning. 3, 2, 1. And liftoff of Space Shuttle Discovery, beginning America's new journey. And the vehicle has cleared the tower.
Among the many changes instituted, the new R-bar pitch maneuver or backflip.
Station Discovery initiating RPM in 3, 2, 1, mark.
Will be used by each mission to the International Space Station. At arrival, the end-over-end flip allows the station crew to visually document the condition of the shuttle's belly and nose. Discovery and the STS-114 crew safely began the final phase of the shuttle program's historic journey with a smooth pre-dawn landing on August 9th, 2005 at the Edwards Air Force Base, California.
Stevie Ray, Soichi, Andy, Vegas, Charlie, Wendy, and Eileen, welcome home, friends.
With this practically rebuilt space transportation system, each remaining shuttle mission would be safer than the one before, and its final flight, the safest.
It's almost like we've had kind of 3 different space shuttle programs. First 10 years, we're off learning how to fly the thing, deploying satellites and flying laboratories in the back. Next 10 years, we're doing more of that, and we're going out on more and more spacewalks, and we fly up to the Mir space station. And in the last 10 years, we use it to build about a 1 million-pound space station in orbit, which wouldn't have been possible without shuttle. It's a heck of a machine.
When you look at the Hubble Space Telescope, that would not have been possible without shuttle. And you look at the International Space Station, which certainly would not have been possible without shuttle. Every launch is an emotional experience. Watching what this nation has done, what NASA has done with the NASA contractor team, it's awesome. It's wonderful.
We didn't spend a dime in space. Not one single penny has been spent in space. Every single penny that went into the space shuttle program over its 30-plus years was spent right here on Earth. One, creating jobs, growing our economy, creating technological development of which we never dreamed, advancing science and technology, even advancing the field of aeronautics.
It just impresses me what people can do. What people can do. It's a big machine. It's a nice machine. It's a fantastic engineering marvel, in my opinion, the whole space shuttle. But what's the real marvel is the people behind it that make it go.
Having a space shuttle enabled us to be able to complete our science and do some really great things to advance the area of metallurgy.
Without the space shuttle, an experiment like this one could not have been conducted. The shuttle is very important for us to learn and be able to conduct long period experiments.
Out of the 50 states, 48 of them have vendors that provide parts or equipment to the space shuttle program. So it's a vast cross-section of America that makes the American space program what it is.
Change is inevitable. As much as people don't like change, it's the only thing that's constant in our lives. And we have to change, we have to transition from shuttle to a new future, which we're going to define, which can be even better. A future that allows us to explore beyond our home planet, to seek our destiny, to learn what we couldn't possibly learn if we were stuck in low Earth orbit.
And since its return to flight, the shuttle program has been almost singularly focused on completing construction of the space station.
I think back of all the challenges and all the things that had to work right, You know, a lot of these interfaces never came together before. All the shuttle flights, the 20-plus shuttle flights that went into assembly, all the Soyuz flights, the Progress flights. To see this station come together in assembly is a true testimony to the international partnership. This is probably the most amazing research facility ever constructed in space, and it's constructed internationally, and it operates every day, 24 hours a day, doing world-class research internationally, and there is no more amazing facility than what we have in orbit.
Through and possibly beyond 2020, the ISS will serve as the world's first full-time research laboratory in microgravity. Among zero-G experiments already conducted aboard the station, several have led to promising breakthroughs in the research and treatment of cancer. Many other on-orbit science findings have the potential to significantly improve the quality of life back on Earth. In May 2009, Atlantis and its STS-125 crew took to space not to visit the ISS, but to return to the Hubble Space Telescope for its final servicing mission. On 5 spacewalks, Atlantis astronauts repaired and upgraded the Hubble telescope to significantly improve its capacity to explore the depths of the universe until at least 2014.
I think of all the fingerprints that are all over this thing.
It's a phenomenal piece of machinery. It's a phenomenal airplane.
And it really is an engineering marvel.
The space shuttle will go down in history as one of the great flying machines that America has produced.
The space shuttle, you know, at this time was a vehicle for bringing people together from all around the planet and having us work in harmony for the betterment of humankind.
We may not have understood when we first built it what all we'd be able to accomplish with it. And after many years, we've realized just how useful it has been.
It's been a learning experience on how to operate and live in space.
What can you say about the space shuttle? It has changed everything.
Well, the shuttle, from my perspective, is one of the great things that this nation has done.
It was a lot of pride.
Like I said, it's inspiring to come to work every single day to work on this program.
I'd go tomorrow if I had the opportunity.
Liftoff of the Challenger from Columbia. Discovery, and the shuttle has been landed.
For more than 30 years, the fleet and thousands of Americans dedicated to its safety and success have toiled in exhilarating triumph, heartbreaking tragedy, and most often, quiet obscurity. Their contributions have extended beyond the bounds of space. Among others, shuttle-derived technologies have been used in developing an artificial heart and limbs, three-dimensional biotechnology, a light for treating tumors in children, and improving crime prevention and wildfire detection. From crawler driver to payload specialist, from scuba diver to pilot, from scientist to engineer, they and many like them throughout the nation share a commitment to sending humankind safely into space. That dedication, as much as any other acclaim, will be the legacy of America's space shuttle.
I think will be remembered in thousands of years, you know, as perhaps the most incredible technological feat of humans of our time.
As is the order of life, an ending for the space shuttle becomes a beginning for a space-bound successor. Soon, America will again send astronauts into orbit and beyond to do what NASA does best: explore.
innovation, safety. The Aeronautics Test Program at Dryden Flight Research Center. Flight Loads Laboratory. Research Aircraft Integration Facility. Western Aeronautical Test Range. Support Aircraft. The Aeronautics Test Program at Dryden Flight Research Center. NASA Dryden's Aeronautics Test Program, Flight Operations and Test Infrastructure Project offers government agencies, corporations, and institutions an extensive range of state-of-the-art support aircraft, communication and telemetry, simulation, and structures research capabilities. NASA's Aeronautics Test Program assets located at Dryden Flight Research Center, advancing technology and science through flight. Flight Loads Laboratory. Given its vast physical resources and highly experienced technical staff, the Flight Loads Laboratory is a unique national resource constructed to support flight research and tests of aircraft structures dating back to the X-15 Hypersonic Research Program. At NASA Dryden's Flight Loads Laboratory, a comprehensive set of structural test capabilities can be achieved, including thermal, mechanical, structural dynamic, and mass properties testing of large-scale structures performed independently or simultaneously. To support testing capabilities, the Flight Loads Laboratory utilizes both conventional and advanced instrumentation technology. The Flight Loads Laboratory utilizes a wide array of test systems, including radiant heating, hydraulic load control, a soft support system, and a variety of measurement systems to support ground and flight research. Tests conducted in the Flight Loads Laboratory utilize the most advanced structural instrumentation capabilities available, including state-of-the-art sensors and measurement systems, advanced sensor integration techniques, and systems for sensor characterization and validation. With its expert staff, distinctive capabilities, and flight line access, the Flight Loads Laboratory provides unique test solutions, all under one roof, that meet customer requirements, from subsonic through hypersonic flight. Research Aircraft Integration Facility. Another one-of-a-kind resource offered by Dryden Flight Research Center's Aeronautics Test Program is the flight simulation capability, located in the Research Aircraft Integration Facility, known as the RAFE. Designed to house project and facility management, vehicle maintenance, and engineering personnel, the RAFE can support a wide variety of advanced, highly integrated research aircraft through all phases of a research program, from concept to flight.
Okay, we'll drive all the way to hold and get some gas. Copy.
Among its more rare capabilities, the RAFE offers high-fidelity, real-time, and batch flight simulation, closed-loop, hardware-in-the-loop, pilot-in-the-loop, and vehicle-in-the-loop verification and validation testing. The RAFE offers 11 different simulation labs with the ability to customize for specific research aircraft and unmanned vehicles. The co-location of project and facility management, vehicle maintenance, and engineering personnel allows the RAFE to support advanced aeronautical and space-based research throughout all phases of the research program within a single facility. Western Aeronautical Test Range. Located at Dryden Flight Research Center and part of the Edwards Air Force Base Complex, the ATP's Western Aeronautical Test Range, or WATR, supports flight research operations and low Earth orbiting missions, supplying a comprehensive set of resources for the control and monitoring of flight activities and utilizing the most advanced tracking and data acquisition technology available, the water's ability to acquire and communicate information to flight and ground crews in real time is incomparable. Fixed and mobile telemetry antennas receive real-time data and video signals from research vehicles and relay the data to engineers in the mission control. The water even has mobile capabilities to allow for rapid deployment and remote testing for support outside of local airspace boundaries, like a rendezvous at the International Space Station in which the water plays a critical role in emergency situations. The water is also the primary communication support when the space shuttle lands at Edwards Air Force Base. Support aircraft. Dryden Flight Research Center's fleet of support aircraft play a number of vital roles in successful aeronautics research, flight, and ground operations. The aircraft provide safety chase support for research flights, mission video, and photography support, and can be utilized as adaptable research platforms if needed during modification and maintenance of research aircraft. While performing safety chase support, pilots maintain constant visual and radio contact with research test vehicles. Chase pilots monitor external flight-critical safety items, clear other aircraft operations, and can provide additional real-time feedback to the test pilot and control room personnel. Another vital component in the ATP's support aircraft program is the utilization of photography and video. Live video is captured plane to plane and transmitted to control rooms, allowing project engineers to watch the mission from the most optimal point of view in real time. Each of these support aircraft has unique performance capabilities, allowing the fleet to meet support requirements across the entire envelope of flight research operation speed, duration, and altitude ranges. This diversity also allows the aircraft to be utilized to meet pilot proficiency requirements on multiple platforms, ensuring Dryden maintains the most highly qualified, versatile, and experienced research test pilots possible. These pilots also support the unique flight operation activities of various Earth science research and deployment campaigns stretching around the world. The Aeronautics Test Program at Dryden Flight Research Center, advancing aeronautics research through flight. With NASA's Aeronautics Test Program flight operations and test infrastructure project, you not only get access to Dryden's world-class facilities and infrastructure, you become part of NASA's tradition of success and innovation. Dryden Flight Research Center, to fly what others only imagine.
Station, this is Houston. Are you ready for the event?
Houston, this is Station. We are ready for the event.
Centers for Disease Control, this is Mission Control Houston. Please call station for a voice check.
Station, this is Dr. Inger Damon with the CDC. How do you hear me?
Inger, this is Kate. I've got you loud and clear.
Hey, Kate, how are you?
So, Kate and Shannon, it's great to meet you, and greetings from Earth. So I guess to start, to open this conversation a little bit about the three of us. And so Shannon, this is my first time meeting you, but Dr. Shannon Walker is a physicist who never lost sight of her life goal. After watching the Apollo 11 moon landing on television as a child, she started her professional career as a robotics flight controller for Johnson Space Center before being selected by NASA to be an astronaut in 2004. Dr. Kate Rubins spent a significant amount of her life in a spacesuit, whether in a BSL-4 lab suit and now in space. Before becoming an astronaut in 2009, she was a scientist studying viral diseases and immunology, was a guest researcher here at CDC early in the 21st century, and I'm Ingrid Damon, Director of the Division of High Consequence Pathogens and Pathology at CDC, and it is so very 21st century to be chatting with you who are on the International Space Station. So welcome. So I guess the first question, Kate, since I know you the best, and you and I both worked in the BSL-4 labs here at CDC on aspects of the smallpox research agenda, a lot of people may not see the parallels between the work that happens at CDC and becoming an astronaut, but you made that transition from the lab bench to the space station. And can you tell us about the route that you took, which has certainly been a complex one, working in microbiology at CDC, starting your own lab at the Whitehead, joining NASA, and now here at the space station.
Hey, Inger, thanks. First of all, I want to say welcome to the International Space Station. You're up here along with the CDC, and it's wonderful to have you join us. So, yeah, it doesn't seem at first like there's a lot of parallels between lab work and being an astronaut and being in space. But, you know, we could probably grab you from the CDC and fly you tomorrow. The work that you guys do is actually pretty similar to a lot of the training that we do. So we call them spacesuits, right, when we're working in the Biosafety Level 4 laboratory, and then we actually do wear spacesuits up here. They're pretty big. They're white. The ones up here have a little bit more mass. They're about 300 pounds, but there's a lot of parallels. So working on things that are high consequence, working in situations where you have to take care of yourself and your teammates. There's consequences to your action, and also working in an environment where lives depend on you. I think everybody at CDC is really, really, really familiar with that feeling that their work has lives dependent on them.
So, well, that's, I think, a great lead into, I think, current events of where we are now. And I think everybody knows the past year has been unprecedented with the COVID-19 pandemic. And so, Shannon, can you tell us about the precautions that you both had to take before launching during the middle of this pandemic?
Yeah, it got very complicated very fast when the pandemic hit and we were in the middle of training. And so first we had to figure out how to accomplish training amidst the pandemic. And so we all took a step back. We figured out what training we could do remotely and what training absolutely had to be done in person. When we did training in person, everybody, of course, was wearing masks. We kept our distance to the extent possible. But of course, when you're training for a space flight, you and your crew have to be in the spacecraft together training. So we always wore masks when we were inside our spacecraft. Closer to flight, we all went into quarantine. In fact, our families went into quarantine with us. So we spent about 3 weeks in quarantine before we headed off to Florida in quarantine there as well. So we made sure that everybody was healthy before we launched because we did not want to bring anything up to the space station with us.
Most of your time on the space station involves conducting research. And some of the work that you've done during your first mission aboard the International Space Station has involved engineering heart tissues, sequencing DNA. So, Kate, you're the first person to sequence DNA in space, and exploring the mechanisms of bone density and muscle mass loss. Can you guys tell us what kinds of research that you're working on now?
Yeah, we're continuing a lot of the biological research. So I happen to be lucky this mission to get the next flight of the cardiovascular experiment. And this was a more complex tissue mix. So we're actually looking at three-dimensional tissue engineering up here. And in addition to the cardiomyocytes, we added in fibroblasts and endothelial cells. So we're able to model the heart tissue better. We're continuing the sequencing. We're multiplexing now. We just started multiplexing about 8 different swab samples that we've taken around the space station. I've already told them we need to get this into 96 well plates and scale this up to high throughput. So I'd like to do 100, 1,000 samples. It is more complex up here to do things like molecular biology, and so some of the time we are just inventing how to do lab work. We recently found that you can use a Sharps container as a disposal for pipette tips, and this works great on Earth. Of course, the pipette tips go to the bottom of the Sharps container. Up here, we actually have this kind of static cling that will keep them in the Sharps container instead of floating out. So sometimes we're engineering some very basic and rudimentary things. Sometimes we're studying complex particle physics with the Cold Atom Lab, which Shannon can probably explain a lot better than I could. There's an amazing amount of other kinds of research, not biological, things like combustion research, fluid behavior up here is just completely changed. So there's about 200 experiments on any given mission, and it's pretty fun to be able to do them all.
Well, I imagine that fluid behavior must make sequencing a real challenge, especially when you're getting to 96 well plates. So are there new aspects of research that you're embarking on because of the COVID-19 pandemic? I know you mentioned some of the higher throughput sequencing that you're thinking about doing.
Yeah, so we're not specifically studying any pathogens of consequence up here above BSL-2. That's all that we're rated for. We have had some impacts because of COVID. For example, in our research teams on the ground, like everybody else, they've had to move to mostly remote work, and then when they have to be in person, doing masks and distancing. And so there were some delays for a while, but it's actually been incredible to watch the teams at NASA still be on a launch schedule. So it wasn't just the Soyuz launch. They then launched Crew 1 was the first operational flight of the SpaceX vehicle, and we've had cargo vehicles come up with literally tons of supplies and experiments, and those are packed and manifested by ground teams that are having to figure out how to do all this. So there's been some impacts to research in terms of operations, but overall everybody's really done an incredible job of keeping this space station supplied and running.
So how long will you both be on the space station this time?
Both of us are up here for about a 6-month stint. We actually, I guess Kate knows her landing date. I'm not quite sure about mine. She's been up here about a month longer than my crew has been from the SpaceX Dragon vehicle, so I figure 6 months-ish.
So I think, here on Terra Firma, I think and I think with COVID, we certainly are beginning to see new things about the SARS coronavirus 2 pathogen. But I think, for the most part, as we begin to understand pathogens, they behave in a typical way. What have you been learning up there about how microbes act in space? And is there information that you're beginning to get from some of the sequencing?
Yeah, that's a great question, and actually it's one of the experiments that I've been working on this week. So we're working on a comprehensive map, sequence-based map of the space station. We're taking about 1,000 samples total, and so I'm very carefully swabbing all of the modules. Everybody floats by and says, "Kate, are you still swabbing?" And I'm like, "Yep." 1,000 samples is a lot. We're really trying. We've done some early microbiome studies where we do a smaller number of samples, but with this this one we're interested in a really comprehensive three-dimensional map. We do know some information about the way that microbes change in space, and there's not just the behavior of the microbes in terms of their gene expression, what products they're producing, but also who's up here. So if you think of the microbial community as a census, we're trying to take a census of which microbes are on space station, which maybe we carry up here and find it a favorable environment, which we don't even bring up here because we don't have a lot of things like soil coming up here. So we want to know who's up here, and we want to know how they're changing. In terms of viruses, we actually have done very few studies. We do know that astronauts are a little bit immunosuppressed, and we can get things like VZV reactivations. This is a virus that causes chickenpox and shingles later in adults. We've seen that before in astronauts. But we don't have a lot of information about basic virology up here, and I think this would be pretty fascinating to study.
Well, I'm sure there's a lot of folks at CDC who'd be interested in trying to go up and help out with some of that work. But so I guess to go back to bacteria, so my division at CDC works on a number of rare bacteria, one of which is called Elisabethingia, and it's named after the CDC scientist who first identified it, whose name was Elizabeth King. Folks may be interested to know that one species of Elisabethingia was first identified in space, actually, in the condensation water on the space station Mir, which Russia had in orbit from 1986 and 2001. Does it surprise you? I mean, again, you sort of alluded to this in thinking about the microbiome and what it looks like there and how it's influenced by who's on the space station, but does it surprise you that we might find the same or different bacteria in space?
Yeah, I think it's incredibly interesting to see what it's like in a completely artificial environment, and so you can probably see a little bit in the background here. We're surrounded by four walls of pretty technological things. So we don't have, for example, houses that we're going to. We have no dirt that we're interacting with. We don't have anything that you would see in the natural world, and so this is a completely man-made artificial environment, and so it's pretty interesting to try to understand which pathogens would survive up here, which surfaces they would colonize, who would grow well. For the most part, we don't have a lot of pathogenic bacteria up here. We do culture-based methods for a long time, and we're really starting to get into the sequencing now. But it is interesting to understand how microbes might adapt to this new environmental niche in space, and I think a lot of the sequence-based technology will uncover things that we just haven't picked up. We've been here for 20 years on the International Space Station, but culture-based methods may not be picking up kinds of interesting things that we see up here. And so doing these comprehensive surveys is probably going to discover a lot of new things. If you have folks that need to isolate and grow up some cultures, we sure could use the help.
So there's been now some promising research collaborations between CDC and NASA, and the technologies that you guys are working on are helping to enhance data on environmental hazards that we're beginning to accumulate. And there's real interest in the sampling of the interior of the living spaces for antimicrobial resistant organisms. What other sorts of collaborations between CDC and NASA do you think can benefit from both of our current work, other than culturing viruses in space?
Yeah, so a lot of what CDC does is really a huge strength is the epidemiology work, and it'll interest you to know that we actually do quite a bit of that at NASA. And so we've got a very particular subset. We're looking at astronaut health, and we're looking at long-term effects of space travel. But I think that the expertise at CDC with the epidemiology aspect and this very kind of unique cohort could definitely benefit from a collaboration. And then I think also things like the wet lab work in terms of understanding how to process samples, how to identify samples, how we could increase the efficiency and the throughput on the International Space Station. I know at CDC you guys process thousands, hundreds of thousands, millions of samples, and so you understand how to do that kind of work, and we understand how to adapt that to the space environment. And then also computationally, so we're very interested here in trying to figure out eventually when we go to Mars, and then also for the lunar surface, how are we going to be identifying organisms? Does that database reside on Earth? Does that reside up here? Understanding the flow of information and how we can take a look at these things computationally, and that's also really a CDC area of expertise that is done very well.
Yeah, and a big area of recent focus as well, just thinking about that computational work. So Shannon, you look like you have something to add. No, okay. So I guess I'm going to move on to some questions submitted from people across the agency, so our rapid fire questions. So the first one is, can you see the Milky Way from space?
Absolutely you can, and it is even more spectacular in space since you don't have an atmosphere to get in the way. The number of stars you can see is stunning.
Oh, amazing. So question to both of you. Who inspired each of you to go to space?
Well, I think you already told my story. It was the early moon landing that inspired me.
I'm not sure where I got the inspiration to go to space. I just always wanted to be an astronaut. My parents definitely encouraged that, and they let me go to space camp, but I did have to work for it. So I had to mow the lawn, and I earned $3 an hour. So I'm going to credit them with a lot of inspiration for hard work, and it's sometimes good when you have to put some skin in the game for your dreams.
So, well, when growing up, I had to clean the bathrooms. So, and I think I got about $3 an hour. So the next question, what was the first thing that you ate in space? And Shannon, I understand that you like to cook. So have you experimented with cooking in space? Any success stories to share?
Yeah, we do have some experimenting that goes on up here. I think at Thanksgiving, we didn't get our expected food supplies for Thanksgiving, so we had to improvise. But we did have some what is it? Some cornbread dressing. We had a can of crab meat, and we had some sauce that I made, or that we had. So I sort of put together some deconstructed crab cakes for our Thanksgiving dinner. So that was fun. And then the other day, we actually got to harvest some of the plants that we're growing, and so we made some improvised salads that were pretty good.
So what's the condition of how loud is it in the working environment aboard the space station?
Yeah, acoustically, it's actually it's an incredibly loud environment. We have a lot of folks that monitor our hearing protection up here, and we actually evaluate each payload for what it's contributing to the acoustic spectrum. And I think it's about 50 decibels in our crew quarters, which is the quietest place on space station. It can get up to like 85 when somebody's running on the treadmill. We limit that noise protection. We do have hearing protection up here, but it's actually I think that's a really interesting area of research, because we're surrounded by pumps and fans. So we live in the middle of our life support equipment. So those kind of maintenance floors on all of your buildings, that's where we sleep and we eat and we do our work here. And so monitoring that acoustic level, understanding if it's a hazard to human health, it's a really big deal in space because we're in this environment for so long.
So do you wear like the little earplugs like what we wore in the BSL-4 lab?
We do wear those to sleep if we can, but then on the other hand, we also have to be able to hear any alarms if we get a caution or a warning alarm that goes off in the middle of the night that signals a space station problem. So you want to block the noise, but you also want to be able to hear the speakers and the caution and alarm. So if CDC's got any interesting technology for acoustic monitoring and or noise prevention in the background, we'll take that too.
Okay. Yeah, maybe you need some more strobe lights like we have in the BSL-4 lab. So I think we are being asked to wrap this question So I'm going to ask you one more question, which is also from folks in the agency. The world has been dealing with social distancing measures over the past year due to COVID-19, and certainly you have an interesting perspective on that being on the space station. And what has the experience living on the space station taught you about maintaining mental health under isolating environments?
Yeah, we actually get that question a lot, and I know some of our crewmates have given talks to address this. I mean, the important thing is to try and stay connected somehow to your friends and family, and we do that similarly to the way people are doing it on the ground. We have phone calls that we can make from the station down to our family, and we are able to do video conferences every once in a while. So that's how we contact the people on the ground, and then we realize that the people we're with, of course, are our space family, so we get to spend time together, which is really nice.
So hopefully you don't have too many arguments with your space family. But no, we really appreciate your spending the time talking to us. I see some head shaking there. And it's been just a great pleasure to have the opportunity to talk with you guys on the space station. So thanks so much for the opportunity. Good luck with everything that you're doing, and we really appreciate the time you spent with us.
Thank you, Inger. Thank you so much to all the Centers for Disease Control. You guys are doing an incredible job to keep our United States safe. And from the International Space Station, we really appreciate it. Thank you.
Station, this is Houston ACR. That concludes the event. Thank you.
Thank you to all participants from the CDC. Station, we are now resuming operational audit communications.
whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
Welcome back to Earth from Space. In this week's edition, Copernicus Sentinel-1 takes us over the Falkland Islands in the South Atlantic Ocean. The Falkland Islands lie around 500 kilometers northeast of the southern tip of South America and comprise two main islands, West Falkland and East Falkland, as well as hundreds of other smaller islands and islets, which form a total land area approximately 5 times the size of Luxembourg. The two main islands are separated by the Falkland Sound, a channel that averages 20 kilometers in width. This multi-temporal image combines two radar acquisitions from Copernicus Sentinel-1, taken 1 month apart, to show changes over time. The first image was captured in December 2019, while the second was taken in January 2020. Here, the main changes between acquisitions occurred in the open ocean, with the bright red colors showing wavy waters in December 2019. The landscape of the Falkland Islands comprises mountain ranges, flat plains, rugged coastline, and cliffs. Hills run across the northern parts of the two main islands, with the highest point being Mount Usborne on East Falkland. Two inlets, Berkeley Sound and Port William, visible in the far right, run far into the land and provide anchorage for shipping. The majority of the population of the islands live in Stoneleigh on East Falkland. The islands are covered with grasslands, which are widely used as pasture land for sheep and cattle, and are also an important habitat and breeding grounds for birds, seals, and penguins. Copernicus Sentinel-1 provides a continuous sampling of the seas, offering information on wind and waves. This is useful for understanding interactions between waves and currents and to improve efficiency for shipping and wave energy applications, potentially producing economic benefits.
Welcome back to Earth from Space. In this week's episode, the many colourful curves and folds of the Flinders Ranges in South Australia are featured in this false colour image captured by the Copernicus Sentinel-2 mission. The Flinders are the largest mountain range in South Australia. They stretch for over 400 kilometres across the Australian outback, from Port Pirie to Lake Callabonna. The first humans to inhabit the ranges were the Adnya Mithina people, who have inhabited the area for tens of thousands of years. The Flinders Mountains are a classic example of a folded mountain range, which are formed when two or more of Earth's tectonic plates collide, folding and pushing layers of land into mountain ranges. The formation of the Flinders Range began around 800 million years ago, when an ancient sea deposited sediments into the Adelaide Geosyncline Basin. Millions of years later, the sediments were folded into mountains, which have since eroded. However, the folded rocks remained and were uplifted to create the landscape as we see it today. The area pictured here shows the Volcothonagamon Ranges National Park in the northern Flinders Ranges. The rugged park's main attractions include deep gorges, chasms, and an oppressive wilderness. Numerous creeks appear like veins across the entire image, while the straight white lines visible in the bottom right are dirt roads. The flora of the Flinders Ranges are largely species who have adapted to a semi-arid environment, including sugar gum trees, cypress pine, and mallee. Since the eradication of dingoes in the area, the number of red kangaroos, western grey kangaroos, and wallaroos in the mountains has increased. This image was captured by the Copernicus Sentinel-2 mission, a two-satellite mission to supply the coverage and data delivery needed for Europe's Copernicus program. The image was processed by selecting spectral bands that could be used for classifying geological features. Welcome back to Earth from Space. Utah's Great Salt Lake and its surroundings are featured in this false color image captured by the Copernicus Sentinel-2 mission. The Great Salt Lake is the largest saltwater lake in the Western Hemisphere and one of the most saline inland bodies of water in the world. It is also the largest of the lake remnants of the prehistoric freshwater Lake Bonneville that once covered much of western Utah. The lake is fed by the Bear, Weber, and Jordan rivers, which together deposit around 1 million tons of minerals in the lake each year. As it is endorheic, meaning without an outlet, the water evaporates, which leads to a very high salt concentration. It greatly fluctuates in size depending on the rates of evaporation and the flow of the waters that feed it. The distinct color differences in the lake are caused by the Lucin Cutoff, an east-west causeway built to create a shorter route. The railroad line is visible as a sharp line cutting across the top part of the lake. This acts as a dam, preventing the waters to mix, leading to the North Basin having a much higher salinity than the southern, freshwater side of the lake. As the lake's main tributaries enter from the south, the water level of the southern section is slightly higher than that of the northern part. Several small islands, the largest of which are Antelope and Fremont, lie in the southern part of the lake. The lake's varying shoreline consists of beaches, marshes, and mudflats. The bright turquoise colors are evaporation ponds, from which various salts are collected in commercial operations. Although it is commonly referred to as America's Dead Sea, the lake is nevertheless an important habitat for millions of native and migratory birds. The lake's basin is defined by the foothills of the snow-capped Wasatch Range to the east, and by the Great Salt Lake Desert, a remnant of the bed of Lake Bonneville to the west. This part of the desert is known as the Bonneville Salt Flats and is used as an automobile raceway, as the flat and smooth salt beds make the area ideally suited for speed trials. Utah's capital, Salt Lake City, is visible on the bottom right of the image. This image was processed in a way that included the near-infrared channel, which makes vegetation appear in red, while rocks and bare soil appear in brown. Copernicus Sentinel-2 was a two-satellite mission. The mission's frequent revisits over the same area and high spatial resolution allowed changes in inland water bodies to be closely monitored.
In this week's edition of Earth from Space, Copernicus Sentinel-1 takes us over the busy maritime traffic in the Bay of Naples, in southern Italy. The two identical Copernicus Sentinel-1 satellites carry radar instruments to provide an all-weather, day and night supply of imagery of Earth's surface. Here, 3 years of Sentinel-1 data over the same area, equal to hundreds of images, have been compressed into a single image. The sea surface reflects the radar signal away from the satellite and makes water appear dark. This contrasts with metal objects, in this case the ships in the bay, which appear as bright dots in the dark waters of the Tyrrhenian Sea. Boats crossing the bay in 2017 appear in blue, those from 2018 in green, and those from 2019 can be seen in red. Many large vessels depart from the port of Naples, one of the largest Italian seaports. From here, and the smaller port of Pozzuoli in the left, small leisure boats and ferries set sail to the nearby islands. Ischia, renowned for its thermal springs, and Procida are visible in the left, in front of Pozzuoli, while the beautiful island of Capri is visible further south. Numerous boats are anchored off the island of Capri. The island lies opposite the Sorrento Peninsula, to which it was joined in prehistoric times. Two indentations can be seen in its cliff-lined coast, the Marina Grande on the north shore and the Marina Piccola on the south shore. Other vessels are docked off the coast of Sorrento, as well as off the Amalfi coast in the right. The Bay of Naples is famous for its scenic beauty, including the steep volcanic hills surrounding it. The still active Mount Vesuvius can be seen just inland from the bay as a circular shape. Cities such as Naples, as well as the other surrounding towns, are visible in white owing to the strong reflection of the radar signal. Welcome back to Earth from Space. This week, Copernicus Sentinel-2 takes us over part of the Andes Mountains in southern Peru. The Andes are considered the longest continental mountain range in the world. They extend around 7,000 kilometers through 7 South American countries, from Venezuela in the north all the way to Chile in the south. The mountain range is the result of the Nazca and Antarctic tectonic plates moving under the South American plate in a geological process called subduction. Wind and water erosion are also a major factor for the shaping of the landscape. In this image, parts of the Ica, Ayacucho and Arequipa regions in Peru are featured. This false color image was processed in a way that makes vegetation appear blue, while irrigated vegetation and agriculture is visible in bright blue. Streams of water flowing from the high altitudes and through the valleys provide water for irrigation to the nearby agricultural fields. The small town of Puquio, with an elevation of over 3,000 meters, can be seen in the top right of the image, surrounded by vegetation. Directly to the left of Puquio lies the Pampa Galeras National Reserve. This reserve protects the habitat of the threatened vicuña, a wild camelid that lives in the high alpine areas of the Andes. The clouds in the bottom left of the image are an example of marine stratocumulus. These low-lying clouds are caused by cooler waters in the Pacific Ocean being pulled up to the surface, cooling the air above it and causing water vapor to condense into water droplets and eventually clouds. Marine stratocumulus clouds often develop off of Peru, with prevailing winds pushing the clouds inland. As the clouds are low, they are easily blocked by coastal mountains and hills, such as the Andes. Under the small cloud in the upper left of the image lies the city of Nazca. Northwest of Nazca, the famous site of the Nazca Lines can be found. The Nazca Lines are a group of geoglyphs, or drawings, etched into the surface of the arid plain. The figures depict various plants, animals, and many other shapes, and extend over an area of around 500 square kilometers. Copernicus Sentinel-2 is a 2-satellite mission. Each satellite carries a high-resolution camera that images Earth's surface in 13 spectral bands. The mission is mostly used to track changes in the way land is being used and to monitor the health of vegetation.
Welcome back to Earth from Space. In this week's edition, the Copernicus Sentinel-2 mission takes us over part of the Great Rift Valley in Kenya. The valley is part of the Gregory Rift, an eastern branch of the East African Rift, which is being caused by the separation of the Somali Plate from the Nubian Plate. major tectonic and volcanic activity have shaped the distinctive landscape of the Great Rift Valley, which runs through Kenya from north to south. The dramatic landscape contains the Cherangani Hills and forests to the west, a chain of volcanoes, of which some are still active, escarpments, and jewel-like lakes. Lake Baringo, one of the most northern of the Kenyan Rift Valley lakes, is visible at the top. With a surface area of around 130 square kilometers and an elevation of around 970 meters, the lake has an average depth of around 5 meters and is one of the 2 freshwater lakes in the Rift Valley. The lake has no visible outlet. Its waters are thought to seep into lavas at its northern end, where the rocky shore contrasts with the alluvial flat on its southern border. Baringo is dotted with several small islands. Its largest is visible in the center of the lake and is called Old Kokwe, also known as the meeting place. It is an extinct volcano with several hot springs. A great variety of birds inhabit Lake Baringo, which is also home to hippopotamuses and crocodiles. South of Lake Baringo lies Lake Bogoria, a saline, alkaline lake. The long and narrow lake has an area of around 30 square kilometers and is around 10 meters deep. Lake Bogoria provides refuge for the lesser flamingo, with a population of around 1 to 1.5 million, and also supports more than 300 waterbird species. The lake is famous for geysers and hot springs along the banks of the lake, some of which can erupt up to 5 meters high. The lake's stable water level makes it highly important during times of drought. Copernicus Sentinel-2 is a 2-satellite mission to supply the coverage and data delivery needed for Europe's Copernicus program. The mission's frequent revisits over the same area and high spatial resolution allow changes in inland water bodies to be closely monitored.
In this week's edition of Earth from Space, Copernicus Sentinel-2 takes us over Barcelona, the second largest city in Spain. On the northeast coast of the Iberian Peninsula, Barcelona occupies a low plateau along the Mediterranean coastal plain. The city and its red roofs contrast with the forested hills and the sea that surround it. The famous Avinguda Diagonal is one of Barcelona's broadest avenues and cuts the city diagonally in 2, hence its name. The circular Plaza de les Glores Catalanes was meant to be the city center in the original urban plan, but nowadays is used largely as a roundabout. The Garraf Massif Mountains are visible on the left side of the image, with their cliffs reaching the Mediterranean coast. The highest point on the coastal side is La Morella, almost 600 meters above sea level. The Llobregat River can be seen entering the image in the top left. The river rises in the eastern Pyrenees and flows southeast before emptying into the Mediterranean Sea. Before reaching the sea, the river forms a small delta, which used to provide a large extension of fertile land, but is now largely urbanized. Barcelona El Prat Airport can be seen to the left of the river. Along the coast, the port of Barcelona is visible, one of Europe's top 10 largest container ports. Barcelona is home to the Universitat Politècnica de Catalunya, the largest engineering university in Catalonia. In 2017, the university won ESA Small Satellite Challenge and the top prize at the Copernicus Masters competition with its Federated Satellite Systems project. The FSS-CAT mission consists of 2 small satellites, CubeSats, each about the size of a shoebox, and will use state-of-the-art dual microwave and multispectral optical sensors. FISAT-1, an enhancement of the mission carried on one of the 2 CubeSats, is set to launch soon from Europe's spaceport in Kourou. FISAT-1 will be the first experiment to demonstrate how artificial intelligence can be used for Earth observation. It will filter out less than perfect images so that only usable data are returned to Earth. This will allow for the efficient handling of data so that users will have access to timely information, ultimately benefiting society at large.
Welcome back to Earth from Space. This week, the Copernicus Sentinel-2 mission takes us over part of Channel Country, a pastoral region located mostly in southwest Queensland, Australia. The name derives from the many intertwined rivers and channels that cut across the 155,000 square kilometre region during times of high water. The landscape is mostly arid and includes flat alluvial terrain that is drained by the Georgina, Thompson, Diamantina, and Barcoo rivers. This desert region usually becomes lush with greenery after periods of flooding, and the land is used for cattle grazing. In late March 2019, Tropical Cyclone Trevor hit northwest Queensland and produced heavy rain as it moved inland. Major flood levels were recorded across the Channel Country catchments. This false color image, captured shortly after the cyclone hit on the 5th of April 2019, was processed in a way that included the near-infrared channel, which makes vegetation appear bright red. Mud and sediments in the waters of the Georgina and Diamantina rivers and the other smaller channels can be seen in cyan. Desert, bare soil, and rocks are visible in shades of green. Flooded waters then usually empty into the Lake Eyre Basin, one of the driest areas in Australia. In the bottom left of the image, the Lake Macadie area is visible. Covering an area of around 900 square kilometres, the area comprises 3 freshwater lakes, Lake Macadie, Lake Mipia, and Lake Coolaboo, and the nearby floodplains. The region is a designated important bird and biodiversity area by BirdLife International, as it has supported over 300,000 waterbirds. Copernicus Sentinel-2 is a 2-satellite mission to supply the coverage and data delivery needed for Europe's Copernicus program. The mission's frequent revisits over the same area and high spatial resolution allow changes in inland water bodies to be closely monitored.
Welcome back to ESA's Earth from Space program. This week, the Copernicus Sentinel-2 mission takes us over part of Abu Dhabi, one of the 7 Emirates that constitute the United Arab Emirates. Covering an area of approximately 67,000 square kilometers, the Emirate of Abu Dhabi is the largest emirate in the United Arab Emirates, accounting for around 87% of the total land area of the Federation. Abu Dhabi has around 200 islands lying along its 700-kilometer-long coastline. The city of Abu Dhabi, after which the emirate is named, is located on an island in the Persian Gulf and is the capital and the second most populous city of the United Arab Emirates, after Dubai. The city is directly connected to the mainland by 3 bridges: Makta, Musafa, and Sheikh Zayed. Just east of the city lies the Mangrove National Park, visible as a dark green patch of land. The protected area is around 20 square kilometers and includes mangrove forests, salt marshes, mudflats, and is home to more than 60 bird species. The waters surrounding Abu Dhabi are said to hold the world's largest population of Indo-Pacific humpback dolphins. The lighter aqua colors are shallow waters, which contrast with the dark-colored waters of the Gulf. The iconic red roof of Ferrari World can be seen in the center right of the image. The Ferrari-themed park is located on Yas Island and is said to be the world's largest indoor theme park. Abu Dhabi International Airport is visible southeast of the park. Sentinel-2 is a 2-satellite mission to supply the coverage and data delivery needed for Europe's Copernicus program. The mission's frequent revisits over the same area and high spatial resolution allow changes in water bodies to be closely monitored.
Welcome back to Earth from Space. This week, the Copernicus Sentinel-2 mission takes us over part of Chile's Atacama Desert. Bound on the west by the Pacific and on the east by the Andes, the Atacama is considered one of the driest places on Earth. There are some parts of the desert where rainfall has never been recorded. In this image, a specific area in the Tarapacá region in northern Chile is featured, where some of the largest caliche deposits can be found. It is here where nitrates, lithium, potassium, and iodine are mined. Iodine, for example, is extracted in a process called heap leaching, which is widely used in modern large-scale mining operations. Leach piles are visible as rectangular shapes dotted around the image, although the exact reason for the different shades of color is uncertain. Some leach piles could appear lighter or darker owing to the varying water content or soil type concentration. The geometric shapes on the right are large evaporation ponds. Brine is pumped to the surface through a network of wells into the shallow ponds. The dry and windy climate enhances the evaporation of the water and leaves concentrated salts behind for the extraction of lithium, which is used in the manufacturing of batteries. Bright turquoise colors of the evaporation ponds are in stark contrast with the surrounding desert landscape, making them easily identifiable from space. Distinctive black lines visible in the image are roads that connect to the various construction sites. Copernicus Sentinel-2 is a 2-satellite mission to supply the coverage and data delivery needed for Europe's Copernicus program. This false color image was processed by selecting several spectral bands that can be used for classifying geological features.
Welcome back to Earth from Space. This week, Copernicus Sentinel-2 takes us over San Francisco Bay in the US state of California. San Francisco Bay, almost 100 kilometers in length, is a shallow estuary surrounded by the San Francisco Bay Area, an extensive metropolitan region that is dominated by large cities such as San Francisco, Oakland, and San Jose. The densely populated urban areas around the bay contrast strongly with the surrounding green forest and park areas. In the upper right, we can see the delta of the Sacramento and San Joaquin rivers, with the brown, sediment-filled water flowing down into San Pablo Bay. Here, the murky waters mix before flowing into the larger bay area, which is connected to the Pacific Ocean via the Golden Gate Strait. A large sediment plume can be seen traveling westward into the Pacific in the left of the image. The Golden Gate Bridge, around 2.7 kilometers long, is visible crossing the opening of the bay into the Pacific Ocean between Marin County and the city of San Francisco. Treasure, Angel, and Alcatraz Islands can be seen sticking out of the waters of the bay, with several bridges connecting its east and west shores. Several boats are also visible. The bright green and yellow colors in the bottom right are salt ponds and are part of the Don Edwards National Wildlife Refuge. Covering an area of around 120 square kilometers, the refuge contains salt marsh, mudflat, and vernal pool habitats for millions of migratory birds and endangered species. Sentinel-2 is a 2-satellite mission to supply the coverage and data delivery needed for Europe's Copernicus program. The mission's frequent revisits over the same area and high spatial resolution allow changes in water bodies to be closely monitored.
of such a journey. A long, impossible dream. But soon, the dream will come true. In this 6th decade of the 20th century, the first men will land and walk upon the surface of the moon. The journey to the moon is not an isolated event. It is the result of a decade of research and discovery in space exploration. At NASA research centers, scientists, engineers, and technicians developed and tested new families of scientific satellites, unmanned spacecraft, which would extend man's senses where he could not yet see, or hear, or touch. Spacecraft which took scientific equipment and experiments into the unknown darkness and sent back the light of new knowledge. From these satellites, man has learned the nature of microscopic particles in space. He has measured air density at great altitudes, discovered how electrons deflect radio waves in the ionosphere, and where radiation belts encircle our planet. He has determined the true shape of the Earth and mapped it more precisely, made new measurements of solar energy, and sent telescopes into the night for a first clear look at the stars. Some were joint efforts to add to man's knowledge, the combined scientific quest of other nations and the launch technology of our own. The early scientific satellites carried only instruments into space. Later, they would carry life, plants and animals, ranging from microorganisms to primates. These biosatellites told us how weightlessness, radiation, velocity, and pressure affected life in the new environment called space. As man learned more about the Earth and near space, he sought to know about his neighbors in the solar system. Probes were hurled through interplanetary space to the neighborhood of Venus and Mars. Nearing Venus, our spacecraft reported the atmosphere to be very dense, the surface hot enough to melt lead. These investigations told scientists that on Venus there is little likelihood of life as we know it. NASA also sent deep space probes sailing across uncharted seas, more than 360 million miles, to look for a brief but wondrous moment at our nearest planetary neighbor, Mars. We learned that Mars is probably more like the Moon than Earth, pockmarked with craters, with little or no magnetic field or gravity. As important as the return of scientific information was the new confidence gained in our technological maturity, that man could design and control such complex operations across millions of miles of interplanetary space. Over the past decade, scientists also developed complex new instruments to probe the intimate secrets of the long, mysterious moon. Television cameras took us live and close up to the lunar surface. planet 250,000 miles away. Other spacecraft circled the moon, photographing its yawning craters and soaring peaks, mapping more than 95% of its entire surface. These studies prove that man could land and walk upon the lunar soil. In this first decade of the space age, the science and technology which was used to explore outer space was also applied to practical benefits here on Earth. Down-to-Earth satellites provide a constant watch on the world's weather, serve as beacons for navigation by ship or plane, send voice and picture from any point on Earth to any other. In 10 years, we have come from a few experimental weather satellites to an operational system capable of night and day observations around the world. Today, satellites take portraits of storms that span half a continent and transmit them to meteorologists in many nations. They have detected hurricanes and typhoons and given valuable hours of warning to those who live and work in their pathways. Man has also learned to communicate by satellite. First with a great balloon that served as a reflector in the sky for earthbound transmitters. For most of the past decade, it provided millions around the world with their first glimpse of a man-made star zooming across the sky. Other satellites followed that could perform increasingly complicated communication tasks. Today, the technology proved out by these first families of satellites has been put to commercial use in an operational system which is available not only to television networks and businesses, but to people everywhere. All the world has been united to witness historic moments. Communication satellites have provided a valuable bridge to scientists working at distant points in the world. But space research was not the only mission of NASA. The first A in the name of this new organization stands for aeronautics. An airplane without wings, the lifting body. Someday, such a vehicle may be used to bring man back from space through the fiery re-entry of the Earth's atmosphere to a landing on the runway of tomorrow's airport. In 10 years, the field of aeronautics has kept pace with man's desire to fly ever higher, faster, and farther. Research has gone forward in jet noise, sonic boom, and aircraft safety. Hypersonic aircraft have been designed and built to fly to the dark edges of space. But the journey to the edge of space was not far enough. Man needed bigger rockets with greater power, the ability to cross the threshold of space for himself. In the 1960s, manned space travel became a reality. Many men here on Earth helped ready the systems which would take a few men across that frontier. Star sailors on a formidable sea conditioned themselves for the new phenomena of space. Then the first American to enter space.
3, 2, 1, ignition.
Many astronauts would follow on longer voyages into space. John Glenn, first American to orbit the Earth. The experience of each added more knowledge to the textbook for all of those who would come after them.
AMR telemetry. Telemetry quality. Mercury cap 3, 2. Roger, the clock is operating. We're underway. Roger, we're programming and roll okay. What we long about here? Stand by for 20 seconds. Roger. Mark.
From these first flights came important information about the men, their spacecraft, and the facilities and personnel who supported them. Man could withstand the force of gravity many times his own weight. Man could live for extended periods, weightless in the vacuum of space. Spacecraft in orbit, make scientific measurements, take photographs of the space around him and the Earth below.
76, Houston is standing by. Roger, understand. Station keeping at 120 feet.
Man could locate other spacecraft hundreds of miles across the ocean of space.
79, Hawaii. How are you? I've got a weird-looking machine here. What do you look like? The jaws are sludgy. The alligator's jaw is open and it looks like they're fully extended. Roger. Okay, we have a rigid light. Okay, Gemini 8, it looks good here from the ground. We're showing cone rigid. Everything looks good from the docking. Gina was very stable. At the present time, we're having no...
Man could rendezvous and dock with spacecraft sent into orbit ahead of him.
Gina very stable and no noticeable oscillation. Okay, we're going to cycle our stop-on switch. Roger. With light, we are down.
Perform complex scientific and technological experiments in space. Man could walk and work outside his spacecraft. Taken man hundreds of miles above Earth. Yet he dreamed of more distant and demanding voyages. Expeditions which would require bigger rockets and more sophisticated spacecraft. Larger crews and longer times. And so, man began his preparations for the moon, and the nation was ready to meet the challenge. Behind the spaceman have stood thousands of engineers, scientists, and technicians, all part of the team dedicated to building and testing the many components which contributed to the dream. America called upon its industry and its institutions, placed new demands and offered new challenges to the establishments of our time. Education contributed ideas and experiments, scientific expertise, and manpower. Industry solved thousands of insoluble problems, found new methods and new materials when they were needed, achieved new heights in quality control and rates of performance. Sometimes there were failures and accidents that claimed men's lives. The astronaut pilot of this research vehicle landed safely. Corrected the faults and continued the work to be done. Youth witnesses the culmination of a dream. Here in this building at the Kennedy Space Center, the mighty Saturn V rocket is ready. This is the vehicle which will thrust 3 Americans toward the moon in the greatest voyage of this century. The great adventure begins here at 1 mile per hour. A giant slowly and ponderously inching its way toward the pad, carrying with it the plans and performances of multitudes of people. A series of test flights with the Saturn V rocket was essential to man's landing on the moon.
18, 17, 16, 15, 14, 13, 12, 11, 10, 9. Ignition sequence start. 5, 4, we have ignition.
schedule began with Apollo 8. 3 days and 238,000 miles away from Earth, the pioneers of Apollo 8 came face to face with the lunar landscape.
In the beginning, God created the heaven and the earth. And the earth was without form and void, and darkness was upon the face of the deep. And the Spirit of God moved upon the face of the waters. And God said, "Let there be light." And there was light.
These men were the first to orbit the moon, to go where man had never gone before, to see sights which man had never beheld.
The white day, and the darkness he called night, and the evening and the morning was the first day. And God said, "Let there be a firmament in the midst of the waters, and let it divide the waters from the waters." And God made the firmament, and divided the waters.
It was Christmas back on Earth, but this was the time when both the Earth and the moon were in the right places, and this was the opportune moment.
And the evening and the morning was the second day. And God said, "Let the waters under the heaven be gathered together into one place, and let the dry land appear." And it was so. And God called the dry land earth, and the gathering together of the waters called he seas. And God saw that it was good. And from the crew of Apollo 8, we close with good night, good luck, a Merry Christmas, and God bless all of you on the good earth.
Later came the second manned mission in the Saturn V rocket, the Earth orbital flight of Apollo 9, to test further the men and the new machine called the Lunar Module. Despite illness and anxious moments, the mission was successful. The command and lunar modules could separate across the vastness of space and could come safely together again. The next act in the prologue to lunar landing was Apollo 10. Entered the lunar module and took it down to within 50,000 feet of the lunar surface. The final and most critical tests were completed successfully. The Sea of Tranquility now awaits the arrival of the first men from Earth.
Monitor descent.
Descent.
Medium monitor select switch to supercritical position.
Supercritical.
3 men will make the journey. Astronauts Neil Armstrong, Edwin Aldrin, and Michael Collins. They will share some of the experiences of those who preceded them. The launching, Earth orbit, rendezvous and docking, lunar orbit, separation of the command and lunar modules. Astronaut Collins will remain aboard the command module in lunar orbit. Astronauts Armstrong and Aldrin will land on the moon. Here on Earth, they have rehearsed the activities they will perform. man's journey into space has just begun.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish. But in a very real sense, it will not be one man going to the moon. We make this judgment affirmatively, it will be an entire nation.
We all want to go back to the moon. Getting us back to the moon in this generation sparks a whole new generation of explorers. Hi, my name is Dr. Kay Renee Horton, and I am boots on the ground for SLS. We actually weld our liquid hydrogen tanks and our liquid oxygen tanks on this. It is the largest weld tool in the world. It's the only one of its kind. It stands 170 feet tall and it has a diameter of about 27.6 feet. So as a quality engineer, we make sure that they're actually meeting the requirements they're supposed to meet. They do a phased array ultrasound, which goes in and checks to make sure we don't have any defects in the weld. To get up and to pull up the news article and they're talking about what you do at work is amazing for me. I really love detective novels, and so I'm an avid reader, and I actually write children's books in my spare time. My children's books are about Dr. H exploring the universe. Each day I walk into the factory, I know that I'm putting my footprints in history, and that's a pretty big deal for me.
The little red light is on.
You're rolling.
All right.
There you go. Mark it. And 1.
You know, most kids, you start thinking at an early age, as soon as you look in the sky at night, you see stars, and you think, what would it be like to be up there? And no matter where we grow up, everybody looks up at the sky and says, what else is out there? I started saying I wanted to be an astronaut when I was 5 years old, according to my mom.
It was the beginning of our astronauts making their way up to the moon. I remember coming back like, what is this? You know, how do I go do this? This looks like fun.
I looked at what NASA was doing. I was like, I want to be an astronaut. So in a nutshell, that's kind of what happened.
I got into the Navy test pilot school and they started to apply to NASA.
There's like 6,000 people that applied for, 15 slots. And I interviewed 4 times over 12 years.
I applied multiple times over 13 years and interviewed 5 times before I was selected.
Well, I did submit 7 applications along the way, but I got rejected by NASA 7 times, but the 8th time.
And the 4th time, I got a phone call that said, if you're still interested in being an astronaut, we'd like you to come to Houston.
finally, it's launch day.
Launching to space, of course, was a momentous experience.
You see that this rocket is a living, breathing beast. The thing is alive and it wants to go.
It suddenly feels like it's real.
First thing, you know, you're strapped into the space shuttle on the launch pad,
and I can say sitting in the rocket, getting ready for launch, you're anxious and you're excited.
Firing chain is armed.
And waiting for countdown, focusing on doing your checklist, focusing on your procedure.
10, 9, 8, go.
At the moment of launch, you're quite prepared.
3, 2, 1, and 0 and lift off. Space shuttle Atlantis.
America has launched.
It lights off and you feel the rumble, and then you start to move, and that constant smooth acceleration pulling you back in the seat.
and you feel like you're just in a car wreck because the solid rocket boosters light off and they give you a kick in the backside like you were just rear-ended at a stop sign, literally.
There's just nothing subtle or nice about it.
There was the vibration, the pressure, the acceleration, the pressure in your seat.
I distinctly remember the point when I stopped and thought, I did it. I'm here. My goal was to be an astronaut, and now I'm in space.
As a kid, you maybe fantasize about spreading your arms and flying among the clouds and that kind of stuff. That's what we're doing. Floating is very cool.
It's fun to watch new astronauts show up in space too, because they creep around. We would joke like space mice, very timid, very controlled.
Being weightless the first few days is horrible. I mean, it's really neat to see something floating in front of you. It's really horrible to feel like you're going to throw up all the time. And then as you start to get into it, you start to realize that the human's an incredibly adaptive machine, and weightlessness is really, really well suited for us.
You know, pretty soon you're going into a hatchway and you come through and you kind of push off on both sides and you go zipping down the middle and you're turning right at the end. So you reach out, grab a handrail, and
But it also brings out your inner 5-year-old, or I say that it is the source of all stupid astronaut tricks.
It's as fun as you think it would be, only better. I think I told my wife that I thought it was a burrito of awesomeness smothered in awesome sauce, because I don't have a very big vocabulary, so I tried to use the biggest, most impactful words I could.
Everybody's a superhero. You're not floating, you're flying.
So the International Space Station, being only 250 miles above Earth, we call it the kind of the proving ground for a lot of science. It is a national orbiting laboratory for the United States, and we do have hundreds of science experiments going on at any time.
We're doing this amazing science up there. It is also absolutely the most wonderful observatory. And certainly for an Earth-facing observatory, the cupola module, this big bay window, that we have facing Earth, is the place to be.
I got visited by 3 space shuttles. Several of the crew members never looked outside the cupola before. I would bring them one at a time to the cupola. Tell them to close their eyes, open up all the windows, the shutters on the windows, and then tell them to open up their eyes.
Cerebrally, I knew that this was going to be a life-changing experience. I knew that the view was going to be amazing.
And I will never forget that sight. The thin blue line of the atmosphere, the curve of the horizon, and that's when it became real. Really, at a gut level, I'm actually in space. We are on orbit. This is not a sim.
This is my eyes looking through glass at Earth from space. It was almost overwhelming.
And so I think it's kind of overload for your brain and processing all of that at once, because it just isn't used to that.
It's really hard to describe something like that, because it's not just cerebral, it's emotional, it's kind of all encompassing. My heart was racing. You couldn't wipe the smile off of my face. It was really amazing.
I just was, feeling something as I was staring at this view of the whole thing. And it moved me to tears unknowingly. So.
And that instant when you're overwhelmed with that vista, when your eyes see nothing but the beauty of the earth, every single crew member that I brought in there for that exposure cried. It is heart-stopping. It is soul-pounding. It is breathtaking.
I mean, it was ridiculous. I'd never imagined in my entire life getting to see something that beautiful. It was so foreign for the human mind to look at that, to see the earth highlighted that way.
Well, I don't think anything prepares you for how crystal clear it is. I knew the colors, but they just seemed different to me. They seemed more vibrant, more translucent.
I've never seen those colors here on Earth. These pearlescent yellows and peaches that form when you're looking at a body of water with the sun angle. It's just amazing.
I just took a pencil and I drew like 15 curved lines, and I just wrote light blue, darker blue, pink, purple, dark purple, all the way down to the surface of the earth at sunset, because the scale of looking at a sun refracting through the atmosphere, it blew me away, okay? And no picture captures that. There's no high enough dynamic range of a photo to capture what the human can see.
How in the world am I going to describe this? There's no words. There's no picture I could take to do it justice. There's no watercolors that I could put on paper to come close to the vividness, the ever-changing picture that I see staring at this planet.
And I think that's the challenge of really trying to express just what ran through my mind when I'd look out there, because my mind would just race.
It's like a work of art out the window there, and it surprises you every time you look at it. One of the most impressive things was watching thunderstorms, storm activity moving around the planet.
You can see its path propagating around, and you have these big flashes all over the place.
This one storm covering all the U.S. and lightning flashing off all over, nonstop.
It's like watching neurons firing in a brain. These tentacles of light that are just connecting and traveling. Yeah, it might be starting over Florida, but it's like moving across the ocean to Africa as far as you can see. And that was, I remember floating there just thinking about, oh my gosh, everything is connected.
We got to see some interesting things up there. One was Hurricane Dorian, a Category 5 hurricane with such a well-formed eye. When you look down at it, flying over in the station, it doesn't even look like it's moving, but you know the power that's at the center of that storm, and what havoc that storm is wreaking on everybody on the ground.
You look at it in terror, really, because you know all the people that are endangered underneath, but just the immensity of power that Mother Nature brings.
A hurricane, a thunderstorm, everywhere you look, there is the environment doing something crazy. So we're coming up over Brazil, about to go across into the Atlantic Ocean, and looking out on the horizon, I saw looked kind of brown. I'd never seen that really from the space station, and I instantly, what did I think? Human interaction pollution, for sure. It's just awful looking, it's terrible. But as we went over the Atlantic, it kind of got thicker and thicker and thicker. It was a sandstorm in the Sahara Desert, blowing this huge plume of sand up into the atmosphere, crossing the Atlantic Ocean and coming down in Brazil. I mean, that is crazy. If that doesn't change the way you think about the planet, absolutely nothing will.
What struck me was when we looked at natural disasters, you see a flood, and you really can't pick out where they are on Earth, but when you see it from space, you realize that the effects of these natural disasters really hit everybody equally, and it really gives you this perspective that, first of all, we're all in this together, and that the world is very small.
What has always struck me every time I went there is how beautiful the Earth is, how fragile it looks, how alive it obviously is with the clouds, the water. It's like it's breathing.
When you first look at Earth, you may say, wow, that's a continent. And then you look at it again the next day and you say, wow, there are mountain ranges. And then you look at it again the next day and it's like, oh, I can see synclines and anticlines in the geologic structure. You could see the Nile River and the Nile Delta so clearly, the Red Sea, and for me that was just amazing to look down. You could see the Jordan River, the Sea of Galilee, the Dead Sea, and I was just thinking, this is where all this took place.
The color palette is hard to compare. I mean, all these reds and oranges, and so the dunes all over in Central Africa and in Saudi Arabia, you have these so many different textures.
And you can almost pick out where you are over the Earth because Australia's tans are different than African tans.
Every piece of the Earth has its own tone, if you want. So you become very acquainted with the Earth from a big picture point of view.
And you saw just the beauty of the landscape and the mountains and the deserts, and you start to think of how they were formed. You realize just how special the place we are is, and you feel that connection.
So when you look at the Earth from that vantage point, I know others have said this, you don't see the borders. You don't see political borders. You hardly see geographical borders.
We're so used to looking at maps or globes. In low Earth orbit, you don't see a globe. And from no distance do you see the different colors for countries so that it makes them easy to distinguish.
I was looking for all the little pink and green countries when I was looking at Earth. Where's Uganda? It's supposed to be pink on the atlas.
You don't see those geopolitical boundaries, all of the man-made boundaries that we've imposed upon ourselves as humans. You don't see any of that from space.
It's just you and your team, and you're trying to make an impact on us evolving into something more. You forget about the politics. You forget about daily life that plagues us here on the ground, that colors our perceptions because you're insulated from it.
Then you just feel this sense of commonality more, and something that unites us all, and just that we're all human.
Flying over Africa in the daytime with intense sunlight so much of the time, you don't really see much detail. It's so bright. But at night, when it's illuminated by starlight or moonlight, you really see a lot, and it's just fascinating.
And you don't quite see the same texture, but you see mankind's influence on the planet.
You get these beautiful, twinkly city lights.
And they represent human sprawl, which isn't necessarily bad, but it is incredibly beautiful from space.
I love looking at the atmosphere at night when you have that air glow, and sometimes it was a bit green, and then you have the aurora dancing around.
And we were flying into this astonishing aurora, this rippling, pulsing river of green that's down below us, the red that is stretching up to our altitude. It's like, it was just breathtaking.
Auroras, the presence of humans at night, it's obvious with the lights. But is the death around the Earth that's startling? How this beautiful, shining oasis of life is there naked in the middle of pitch black death, a vacuum of space.
Definitely look up and see the stars like you have never seen them before. I mean, the Milky Way is just stunning.
There's many things in the cosmos to gaze at it. For example, the Magellanic Clouds. Those show up really bright and vivid because you don't have atmospheric scattering. You can see Andromeda, the spiral galaxy of Andromeda.
Of course, the lights don't flicker. They're steady because they're not coming through the dust and coming through the atmosphere. And then as you really adjust, you start to sense the very subtle colors that are in the stars. A little bit of reddish, a little bit of bluish, blue-white.
Just all the colors in the light come out, you know, in that depth of space as well.
I could all of a sudden detect depth. Now, I couldn't tell you how much, but it's light years, right? And it's like, whoa, I can somehow tell that that star is closer than that star. And that was something that knocked my socks off. And I thought, nobody told me about this.
I don't think I had thought before going up there about how many stars you see, you know, the density of stars.
You see so many stars, it becomes hard to pick out constellations. People ask if there's aliens, and I'm like, of course there are aliens. Look at all those stars. There's got to be.
It's just so vast and infinite that I don't know what else to say about that.
I remember using like the 800 millimeter lens and just really zooming into places. And you know, you still can't see people walking around or anything, but you see impacts of things. And you realize that a lot of times we have to pull way back. You know, you have to pull way back and see the big picture of it.
You realize just how small you are, because you at times struggle to find evidence of human activity down there. You can go over massive swaths of the earth and not see a trace of any human impact. Or you can go over other swaths and you can see dramatic impact.
Frequently, in the summertime, there's a lot of fires in Africa. You see all of those plumes of smoke heading west across the Atlantic.
You fly over South America and you see, you know, widespread deforestation, and you know the impact that that has. You can almost get a sense of the balance of, you know, how nature is trying to balance all the inputs and the outputs and have a stable system, and you can see our effect on it.
To me, it started to make me understand that everything is connected. What is happening in the ocean over here can affect what is happening on land over here. It's just all one being, thing, and it's all interconnected.
You can see combat. I mean, we were two countries were at war, and you could very easily see missiles being shot. They just look like little tiny traces of light. You can see all that stuff. So to me, I didn't see one unified human civilization. You certainly see one unified planet cruising around the sun, and that is a unique perspective.
But during my time on the space station, I had the chance to do a spacewalk, put on a spacesuit and go outside. And that's a very special experience for any astronaut.
You're inside the space station or the shuttle, and now you put on a suit and go outside. It's like there is an elevation and risk when you do that, but it is a bit thrilling.
Spacewalks always seem to be very busy and task-focused events where I got to do this and I got to move over here and do this, and
then you just have to not think about where you are. Just concentrate on getting the job done. What's the big picture?
Rarely did you have a minute where you could just say, just take a minute and enjoy the view. But you know, there were those minutes every once in a while. And the view from outside the spacecraft, you know, with that full panoramic vision through your helmet visor was just incredible.
It's a very disturbing view, looking down about 240 miles at the Earth going by at, 17,000 miles an hour. It's like, oh boy.
I just watched the Earth going by below me, and I only had this, thin visor separating me from a very unsurvivable atmosphere. And my feet were dangling. I remember, not just through my visor, but looking down and you just see feet and then earth, and and you're holding on to the space station, and I mean, it was just incredible. Everything looked so large.
The colors are even more vibrant, and I think also just mentally, psychologically realizing that, you know, there's nothing between the vacuum of space except for this spacesuit and your visor.
I remember thinking that coming out, like that the world would just open up around me. And the view for some reason seems bigger than what you have when you're looking through the windows of a spacecraft.
I mean, it wasn't like Earth is over there. It wasn't small. It was like it took up your entire, you know, visor and all as far as you could see, and just watching it come over Earth and just how large Earth was compared to from our perspective.
But oh my gosh, you see Earth and you see your glowing station around you, and you realize, okay, I gotta stop looking at this stuff because it becomes a distraction to the work that you're doing out there.
So I always kid those astronauts that don't do the spacewalks. You know, I said the view from inside here through this flat window is pretty good. You know, the view from outside is just amazing.
And the great thing about living on Space Station, I loved every minute of it. I had a countdown going, but it was, oh no, I only have 2 months left.
All right, one last look at the Earth. This is some good news. The Earth is still beautiful. An Earth in crisis is still an Earth worth returning to.
Life seems extremely busy, and you know, the days start flying by, and before you know it, it's over.
As it drew to a close, I think I was more feeling as though, did you do enough to capture this so that you can share it when you get home? And so that you can light those fires in people as you go around and talk about this and try to, you know, ignite the passion in kids just like I had ignited for me as a kid.
Back on the ground, and somebody else is doing the job up there now. It makes you feel like, you know, this is a really big thing that we're a part of, and just, you know, I'm fortunate to play my part.
It is the fact that going to space and seeing the Earth from that vantage point has a life-changing effect on most of us.
It takes a lot of energy to describe what it's like up there, because there's so much of your emotion built into it.
I think the best way to describe it is that your viewpoint changes, that you can look at the same thing, but it changes the lens through which you see it.
And that acute concrete realization that we belong to Earth and not vice versa, it's kind of a mental shift to see that we just nowhere else we could go.
I think if you're not a conservationist before you go to space, you're at least partly a conservationist when you come back, because when you see how thin that atmosphere is, that protective layer that we have here, you think, wow, we really have to take care of this because it does look so fragile from space.
I think I felt that need to protect it even before leaving it, but it definitely does resonate even more loudly now, having seen it myself, and how stunning and beautiful it is. All of those unique ecosystems, everything's connected, the land masses and the ocean masses and the atmosphere, and we are all in it together. We are all down there. And so I think that's the most important thing that I would encourage people to think about, that perspective.
I think you get a sense of preservation of I don't want this to go away, and I don't want to be the only one to see this. And there are so many people that need to see it, but only a handful will in this lifetime.
You know, I remember coming back from all my missions with that sense that, you know, we're all connected, we're all people. And I thought about why is it that we do have conflicts? What is that separates us from one another?
If you could get 7 billion people to go up there and look down for just even 30 seconds, you would change them, all of them, forever. They wouldn't all come back and be friends. They wouldn't all come back and tear down border walls and things like that. But you would change all of them, and you would change them all for the better, and they would have a different view of the planet.
I think if people that can lift their eyes up and see the bigger picture, whether it's from orbit or even just understanding the different sides, maybe spending more time listening, you know, rather than shouting.
And that's what I want people to find. I absolutely found that in the experience I had in space, in the simple facts of us living on a planet and all being Earthlings, and the only border that matters is that thin blue line.
Throughout history, humans have been described as many different things. But one of the most intriguing and apt definitions came from Aristotle, when he defined humans as a rational animal. According to this definition, human rationality and problem solving is what separates us from all other animals. Of course, we can look back at history and see notable examples of human problem solving, from the construction of the Great Pyramids, the precise engineering of Roman aqueducts, the Industrial Revolution, and millions of other examples. It is clear to see that when faced with new problems, we can overcome the status quo and develop new and exciting paths forward. That problem-solving spirit can also clearly be seen today in our modern world. New technology and ideas are changing our planet daily, but with each new change, generally new problems arise that need to be solved as well. Although there are many different organizations that solve modern problems, one that has stood out for decades and continues to be a leader is NASA. Since its first day of existence in 1958 through today, the brilliant men and women of NASA have time and time again solved some of the world's most difficult challenges. One of the key areas NASA continues to shine is in development and testing in the field of aeronautics. Although NASA rightly gets credit for expanding our horizons in space, The reality for the public is that relatively few people are directly affected by space travel. Ironically, the work in the aeronautics field that NASA has pioneered for decades and that affects millions of people daily is less well known. From the beginning, NASA engineers and researchers have led the way in virtually every aeronautic development, from advanced wing designs through the hypersonic frontier and onward into the era of composite structures, electronic flight controls, and energy-efficient flight. And since 2011, NASA researchers from around the country have been working on NASA's Unmanned Aircraft Systems Integration in the National Airspace System, or UAS in the NAS project. This project was a new type of undertaking that worked to identify, develop, and test the technologies and procedures that will make it possible for unmanned aircraft systems to have routine access to airspace occupied by human-piloted aircraft. NASA's innovative work in this field has led to many of the breakthrough technologies that will undoubtedly change the way aircraft currently move through our skies. But after years of study, team members are closing the books on the UAS and the NAS project that has provided so much new information about how future aircraft will fly. Today on NASA X, we will explore the work performed by the UAS and the NAS team. We will look back at some of the complex systems and procedures that have been developed for the UAS and the NAS project, and see how NASA and industry have successfully worked together to improve manned and unmanned flight as we know it. Finally, we will bid farewell to the team that is changing the way we all fly, and look to the future to see what's next on the horizon for the UAS community. NASA is clearly one of the world leaders when it comes to science, engineering, and research. But surprisingly, many people in the public really can't tell you much about the agency. If asked to describe where NASA is located, for example, many would be hard-pressed to say anything more than in Houston or Florida. Many also just see it as a giant nebulous government agency that works on engineering and research projects. But other than astronauts, no particular person or place is necessarily strongly associated with NASA today. The fact is that NASA is comprised of a consortium of research centers, test and assembly facilities located around the country, all working diligently to solve complex technological problems. Each center specializes in different areas such as spaceflight or aeronautics. But within the UAS and the NAS project, centers across the country have been utilized to contribute to this groundbreaking research. In particular, 4 aeronautics-focused NASA centers supported the UAS and the NAS project: Ames Research Center and Armstrong Flight Research Center, both in California, Langley Research Center in Virginia, and Glenn Research Center in Ohio. Lastly, the entire project was managed by NASA's Aeronautics Research Mission Directorate at NASA headquarters in Washington, D.C. Since the start, the goal of this unified team was to provide vital research findings through simulations and flight tests to support the development and validation of detect and avoid and command and control technologies necessary for integrating UAS into the NAS.
When we got involved in this, we knew that some of the key areas that you need to focus on is how to stay well clear from other aircraft, particularly when you're in uncontrolled airspace. So low altitude, classy airspace where there's a lot of general aviation traffic. So you're not under direct control of an air traffic controller. Everything just came together. Communications and the wonderful work that we've done at Glenn Research Center relative to space communications, so we had terrific technology there that could apply to this arena as well. So those 2 long poles were detect and avoid. How do you, when there's not somebody sitting in that aircraft, how do you see other aircraft that maybe their transponder's not working or they don't have ADS-B? And then how do you communicate and communicate effectively with air traffic control? on your intent or maybe changes to your flight plan that you have to get cleared. So how do you do that? And how do you not put an additional burden on the NAS, on air traffic control and how we're operating the NAS? So you're just another vehicle. So we have the technology to do that. We have a research kind of culture that we know how to do that research and not just provide them opinions, but hard factual data on what different types of technologies and how they work, what that would mean in different kinds of scenarios. And we had a cadre of incredibly smart women and men researchers who know how to do this work. And everybody that could possibly think about delivering some service or some product to a household or between businesses now has an interest in the work that we've been doing.
That interest moved into full-scale testing and evaluation to determine how to best integrate unmanned vehicles into the national airspace and how to come up with standards moving forward.
So the overall goal of the project is to enable or assist the enabling of the safe integration of unmanned aircraft into the national airspace. To this end, we're assisting industry and the UAS community in developing standards. We're performing simulations, analysis, and flight tests that inform the development of these standards, primarily in the areas of detect and avoid and command and control.
When NASA first undertook this challenge, they realized they would have to bring in a team of engineers from the aforementioned NASA field centers, along with highly skilled teams from industry and academia, in an effort to unlock the keys for UAS integration into the national airspace. Normally, more than 44,000 flights safely take off and land here in the U.S., totaling more than 16 million flights per year. With the inclusion of millions of new types of unmanned aircraft, this integration needs to be seamless, keeping the flying public safe while also allowing these new vehicles to perform their assigned tasks. Looking at the challenges from the start, researchers knew that some elements would need to be considered from the ground and the sky. First was to improve the electronics on board the UASs and the electronics on the ground. Much of that command and control work began here at NASA Glenn Research Center.
UAS NAS C2 subproject is really investigating the communications links between the pilot on the ground and an unmanned aircraft. There's quite a bit of information that needs to go back and forth. We often call it a pipeline. When you bring the pilot to the ground, all the information that he would normally see in the aircraft has to now be digitized and sent down through this secure link. What we've done here at NASA Glenn is to investigate the COM link. We have a long history in radio communications here, and so we started from scratch essentially to develop a radio. One of my tasks is to test those radios, both in the laboratory, and then we put them into real aircraft, piloted aircraft, and run them through a series of tests.
Although this project is all about unmanned aircraft, as Kurt mentioned, the tests here at NASA Glenn were conducted with piloted aircraft. The workhorse of the testing was this Cold War era S-3 Viking. This aircraft was chosen due to its resiliency to carry extra weight, to fly on one engine in the event of an emergency, and because of its robust electronics capabilities. But in today's modern world, one would think that the researchers at NASA would simply create computer simulations and not fly an aircraft.
With this project, we're actually investigating multipath with our communication systems. Basically, the signal bouncing off other entities. So we flew this aircraft over areas of rising terrain, over mountainous areas, over land to sea interface, if you will. And that's one of the ones that our model wasn't matching. We didn't realize the impact of sailboat masts and some of the other things on the water and what it would do to the signal. And so we were able to validate those simulations and show, hey, our model's not quite that accurate. We'd have never picked that up until this technology had been implemented had we not flown it.
These test flights are precise and technical in order to obtain the best results possible.
You'll see a series of waypoints that are listed as LP 1 through 16, and those are at different ranges from the ground station. They're all at a fixed altitude, and what we're doing is gradually moving the aircraft away from the transmitter so that we can see how many, when we start to pick up these signal errors. So he'll fly this test. It'll take a couple of hours. We will then collect the data, process that, and then come up with a test flight plan, perhaps a revised one or a different one for the following day. What that's doing is the signal is leaving our tower, which is about our antenna is about 50 feet off the ground on a tower. Down in this situation, this is in southern Ohio, where it's fairly rolling hills, and we want those rolling hills because those help to reflect our signal. So by going to different altitudes, our signal will clear the mountains and the terrain that's below. Once we get up high enough, it'll be a straight shot, no terrain obstructions, and we know that that's a safe altitude for this aircraft to fly.
Back at the other three centers, teams were working hand in hand to better understand how these UASs would travel in the national airspace by using NASA-developed software in combination with flight tests. Much of this work is centered squarely on technology called detect and avoid.
When you are a pilot in an aircraft, a human pilot in an aircraft flying, there are certain aviation regulations that you have to comply with. And those regulations require that the pilot be able to see and remain clear and avoid other aircraft so that there are no collisions. Makes sense, right? So what detect and avoid is since the pilot for an unmanned aircraft is either remote off the aircraft or not there at all in the case of an autonomous aircraft, there is no human eyeball to go see other aircraft. So the technology needs to be developed to use other means such as radars or cameras to be able to detect where other aircraft are flying in the proximity of your aircraft, your unmanned aircraft, and then be able to somehow, like a pilot would, avoid those other aircraft. And the way that's done is through developing some mathematical algorithms to be able to direct the aircraft to a location that would be safe. And so that's the kind of research that NASA wanted to focus on, because that was the most critical aspect of how to safely integrate unmanned aircraft into the national airspace that industry writ large could not really understand. They didn't know how to do that. They knew what it was like to be a pilot, but they didn't know how to turn that into some sort of certifiable technology. And so NASA spent the time UAS and the NAS project was in existence to be able to develop the technologies by which to address the challenge of detect and avoid.
Detect and avoid has three major components, technical areas. One is guidance and control, which develops the algorithms that we use to tell us what our options are to avoid other aircraft once they're detected using airborne radar or ground-based radar. We have modeling and simulation where we run fast time simulations. We can run millions of trials, and to be able to really pare down what we bring into the human-in-the-loop simulations, which are really the purview of the Human Systems Integration Group, and that's the lab that we're in here. So when we run subjects here, we have already pared down a lot of the solutions, and we're looking at how real pilots interact with a fairly realistic airspace and some of the solution spaces that we have developed in the other technical areas.
One of the primary safety concerns with integrating these new systems is the inability of remote operators to see and avoid other aircraft. On all flights with pilots on board, the FAA requires the crew to be aware of all other surrounding aircraft, either visually or using onboard instrumentation. In addition to instruments, the pilot physically looks out of the window in order to avoid other aircraft. Because unmanned aircraft literally do not have a pilot on board, NASA and its partners have developed concepts and designs allowing safe operation within the national airspace. In order to better understand how all the systems work together, the NASA team flew a series of tests out of NASA Armstrong in California. The objectives of these flights included data collection to inform the development of minimum operational performance standards, or MOPS, for detect and avoid alerting guidance.
The third phase was what we called full mission. And so what this involved was a naive UAS pilot coming into our research ground control station and flying a simulated mission with everything that you could expect to have on a real UAS mission, except in this case some of the aircraft were virtual. We had a live intruder, and we had real pilots talking over the radio and an air traffic controller talking over the radio. It seemed like it was a real mission, and we were actually able to gather a lot of metrics that you would normally gather in a lab, but in this case a real atmospheric flight, and that's what we call live, virtual, and constructive. So we had the live component, which is the live UAS and the live intruder, the constructive, which were traffic simulated aircraft that were moving in the airspace, and then virtual, which were actually people who were flying simulated aircraft and talking over the radio. And all those things combined to create a really immersive test environment.
So there's a significant amount of research going on across government and industry in the area of unmanned aircraft, everything from small drones to large unmanned aircraft. Detect and avoid capability is critical to all types of unmanned aircraft. And another natural extension of the work that we've done is to move towards automation of the operation of UA, especially when lost link occurs.
NASA is also doing flight demonstrations called the Systems Integration and Operationalization Demonstration Activity, or SIO. The SIO flight demonstrations partners will use various sized unmanned aircraft for these tests.
NASA's partnered with the FAA under SIO. We're also partnered with 3 different companies: Bell, General Atomics, and American Aerospace. And each of these companies has a different concept of operations and different unmanned aircraft that they are attempting to certify for operations in the National Airspace System.
It's clear that automation and new breakthroughs will continue to push this research forward. Over the course of this testing, NASA and the FAA have gathered an enormous amount of data, allowing safe integration for unmanned aircraft into the national airspace. As unmanned aircraft are becoming much more ubiquitous in our world, safety, reliability, and proven research must coexist to continue this unique integration. NASA and its partners have thoroughly evaluated every aspect of this proven technology, laying the groundwork for companies to develop exciting new vehicles based on the data that has been generated.
For me personally, this is just a really exciting area. Realizing that this is a really fast-growing area. Aviation has had kind of a slow and steady evolution. It's been good. It's been relevant. It's been introduced in a very methodical and safe way. And suddenly you have this introduction of UAS into the mix, where you've got a lot of, my words would be non-aviation type entities that are wanting to come into this market. So to create some standards around which they can develop their aircraft, around which they can develop their use cases so that they really can seamlessly integrate in the national airspace, it's a pretty exciting area to be involved in. And it's a fun area because a lot of these companies have really great ideas. They're not traditional from the standpoint of being an established airframer or established engine company, but they have great ideas, and realizing that we'll be able to enable that kind of next wave of emerging companies and ultimately emerging products that come from that. It's pretty exciting. So it makes me want to get up in the morning and come to work.
I've been on all sides of the research, and it's very rewarding to be a part of the team. They work long hours, and overall, we're all striving for the same goal, which is to get these large unmanned aircraft safely and smoothly integrated into the national airspace. And it's been a lot of work, but I don't think anybody on the team would say it hasn't been worth it. It's been a pleasure to be a part of the team, and you really can't say enough great things about the project.
The last thing I would mention is that This was just the results of a project with a specific goal that we had within NASA Aeronautics, but it's certainly not the end. I mean, integrating UAS into the national airspace is an evolving thing. There are many more challenges. There are many more use cases that the industry is going to come up with. And so we're sensitive to that, and we're keeping an eye on that so that we can really align our research with those areas that are emerging, and hopefully so that we can enable those to come into fruition for the benefit of the American public. And so as we stand up new projects, you know, we'll leverage our experience with UAS and the NAS project, but we'll do it into new areas, whether it's autonomy or other areas of research that will really enable a lot of these use cases and bring about some pretty exciting new markets for the country.
Every day, new use case scenarios and research opportunities arise based around the hard work accomplished by this incredible workforce. Only time will tell how these new technologies and innovations will shape our world. But however the outcome, this team can be proud. Their hard work and efforts have opened doors to radical changes in aircraft design and efficiency for future generations.
It's particularly fitting on this day that we're able to bring you this program from our exhibit about the space station, the International Space Station, the Space Shuttle, and future human spaceflight. Because we're delighted to have as our speaker today Victor Glover, who is a NASA astronaut. He comes to us from a background at the Navy where he was a pilot of F-18s, a naval aviator. They don't just have pilots, they have aviators. And who is now a part of the 2013 class of astronauts, an elite group of 8 who have been picked to really train for the next steps in human spaceflight, which is very much what we are about here at the museum and specifically here in this gallery. So I'm delighted to welcome to the stage Victor Glover.
Thank you, Margaret.
Thank you.
Thank you very much. Thank you. Thank you for coming out on a Saturday to be here with us. And thank you to the Smithsonian for hosting this event. Thank you to all of the sponsors, and especially thank you to the folks in the room who are making this happen and working hard to see this. What we're here to do, you know, they invited me here to speak at this event. However, I don't consider myself to be in that category of the space and aviation pioneers, but I am standing up here because of the work of those aviation and space pioneers. Right behind me is a jacket from Sally Ride and Guy Bluford, the first American woman in space and the first African American in space. And it's because of folks like that and a whole bunch of folks all over the planet that we were able to do what we do. So thank you for coming out this morning. I don't know if you're like me, but I could look at pictures of people in space all day. But you know, you got to see all phases: launch, on-orbit operations, landing. You got to see phases of our training, and I love that video because it shows every time you saw an astronaut, you probably saw 3 or 4 other people in the picture. And Scott Kelly, the gentleman who returned from the one-year mission in space, he would always say, human spaceflight is the greatest team sport on and off the planet. And that video shows you just some of the effort that it takes to make what we do possible. When we're in the Neutral Buoyancy Lab, you saw that great facility, 100 by 200 by 40 feet deep, 6.2 gallons, 2 million gallons of water where we train for spacewalks. When you saw the 2 people in the suit, did you see them surrounded by those divers? We have a whole team of folks, flight controllers, trainers, even the logistics and budget folks that make what we do possible. So I play that video as a shout out to all of them. So, welcome. Thank you for coming. I'm going to talk to you a little bit about the training, about the background before I got to NASA and what we've done since we showed up, my class in 2013. But you know, all of you adults here, thank you for coming. But I'm really grateful for all of these kids that you brought. And so I'm going to spend the next few minutes talking to them. And so if we ignore all you grown-ups, I apologize now, but this is for the kids. So I like to start with this question. And I know they tell you in school, and it's important to, you know, have your manners, raise your hand, but, you know, don't talk out of turn. But I want you to yell out, okay? If you know what you want to be, I want you to yell it out. What do you want to be when you grow up? Anybody? What do you want to be? Astronaut. I love it. I am doing some good recruiting here today. What else? What do you want to be? Another astronaut. Yes. I'm seeing a trend. I'm seeing a trend. Well, you know what? What do you want to be? Another one! NASA is going to have a lot of applications the next time we hire astronauts. But you know, there's a lot of parts of the room where I'm not hearing answers from. And I think the most common answer to this question is, what do you guys think that's going to say? I don't know. Say it again. I don't know. I don't know either. I don't know. That's the most common response I hear. But you know what? It's okay. I'm standing up here wearing my pajamas, and I go home and play with really expensive toys and, you know, video game type things. No, these are really sophisticated systems, but it's kind of like playing with video games. So I don't really know what I want to be either, but I want to talk to you about some things that you can put into practice right now. I don't know how smart I am. People say, oh, you must be smart. I don't know how to measure that. I don't know how smart I am. But I can control some things, and these are things that you can control too, and you can put them into practice right now. And you should put them in practice all the time. And it is to be gritty, to be a lifelong learner, and to be a good person. And we'll talk some more about that. I'm going to tell you some stories about my education and my career and what got me to NASA and then what this training is like. But I want you to remember that I'm telling you these stories because I'm hoping to connect with something that you've done or seen. I've already done high school. We've got high school students in the audience there. Any of you planning on going to college? Did that a few times. And I've had a career that I've loved. I haven't actually worked a day in my life. I love what I do, and I would pay money to do it. So maybe there's something that you're thinking about doing that you can connect with in these stories. But the purpose of these stories is you. Okay? I came here. NASA sent me here. The Smithsonian asked me to come here to be with you, to spend some time with you. Your parents woke you up this morning. I know they made you brush your teeth and get dressed, comb your hair, but they brought you here for you. Okay? So, remember, I'm going to tell you these stories. I want you to think about something in your life that these can connect to. I hope so. All right, so I'm originally from California. This is one of my favorite pictures, cousins and an uncle. And any idea which one of those is me? It's really deceiving because I have a whole lot of hair. There it is, that guy. Another picture with hair, okay? I'm going to put all pictures up with my hair. So I want to tell you a story about when I was in elementary school. I was in 5th grade, and we had a program called MESA, Mathematics, Engineering, and Science Achievement. What got me into it was building cars powered by mousetraps, building bridges out of popsicle sticks and balsa wood, and then they would stack bricks on top of it until they broke. So I was in there to do stuff with my hands, make a mess, and then break stuff. But they snuck in science and math, making speeches, giving speeches, writing essays, and so I had to learn about some of those things too. But our advisor, his name was Mr. Hargrove. He was one of our 5th grade science teachers at Allison Elementary School in Pomona, California. And he knew that I had this tendency, you know, I would do really well on my tests, but I might turn in my homework, maybe not. And he was giving me a pep talk, encouraging me to do all of that work, to be all that I can be. And he said to me, he said, you know, if you work hard, you would be a great engineer. Now, I have to admit that in 5th grade, I didn't know what it meant to be an engineer. I thought it meant driving trains. That's funny now, but that's true. And I didn't know what it was. And so I didn't have a mentor that had studied engineering in college, but his belief in me made me think that I could do it. And to this day, I am still trying to live up to that belief that Mr. Hargrove had in me. And so I know I said I was going to talk to the kids, but to you adults in the room, any educators in the room? Teachers? Parents, you should raise your hand too. We are constantly engaged in educating. Thank you for your service. And set those bars high. And believe in those kids. But don't forget to communicate your belief in them. Because what Mr. Hargrove said to me in 5th grade still drives me today. And I wouldn't be standing up here if it wasn't for that conversation. So, a story from high school. I was a pretty, earlier someone asked me, what kind of a student I was. I think I was average. I was really, good in math, but I wasn't always good in the study habits and skills and doing all the work. I was involved in community service, probably did at least as much as my peers, maybe a little bit more, and I was really good in athletics. I loved to wrestle, play football, I ran track, and so you kind of squish all that together. I think I was an average student But one of my best experiences happened in a calculus class I'll tell you about. But I do want to show you a couple pictures real quick, though. So the pictures up there are some of my good friends from high school. I was a normal kid. I put the first picture up, though, of me in my cap and gown because I graduated. And that's most important. You're going there for a purpose. Your parents are sending you there for a reason, okay? And so I graduated, but I was a normal kid. I still had fun. I went to the movies, and I had extracurricular activities and hobbies. But at the end of the day, I got the diploma, and that's what your parents are sending you there for, and to grow. So back to this pre-calculus class. Gerald Robinson, Mr. Robinson, my pre-calculus teacher, was also like Mr. Hargrove, trying to encourage me to get the best out of me, and he did something that changed my life. We were working on adding numbers in a series, adding the numbers from 1 to 4. Add the numbers from 1 to 4. And so I was doing my homework. Yeah, I was doing my homework. And I noticed that if I write the numbers out like you see on the screen there, they made a shape. Kids, what shape is that? It's a triangle. That's right. And to find the area of a triangle, you actually turn it into a rectangle. So if I'm adding 1 to 4, now I have 4 by 5 in a rectangle. I multiply that together, I get 20 divided by 2, and it's 10. And I noticed that pattern when I added 1 to 2, 1 to 3, 1 to 4, 1 to 5, that this pattern would work. And I could figure out how to add those numbers up with that formula. The number, so adding the numbers from 1 to 10, you take 10 times 11 divided by 2, 55. 1 to 10 is 1 plus 2 plus 3, all the way to 10 is 55. And I was like, whoa. And I was in his classroom scrawling numbers and pictures on the board, and Gerald Robinson, Mr. Robinson, walks in and sees this on his board. And I said, Mr. Robinson, I discovered a formula. I don't know what we're going to call it. You know, the Pythagorean theorem is cool, so the Victorian theorem. And he takes the calculus book and he flips a few pages and he shows me that formula later in the book. And I was like, oh. And I think he saw sort of a little disappointment. Like at 16, I was actually like thinking I had discovered something nobody else had seen. But he did something that changed my life. He said, why don't you teach that to your classmates? You explain it. That was one of the first moments that I thought, boy, I know people have said I need to go to school and study engineering, but maybe I can do it. Maybe I can do the work. I could tell you stories like that for an hour, but I won't keep you. I know those seats are a little hard. So, I graduate from high school, and I go to Cal Poly San Luis Obispo. I studied engineering. I was on the wrestling team. I was on the football team. Had a great time there. And I met this girl. That's a picture of she and I tutoring. We used to go to junior high schools and high schools to talk to young kids about the importance of science, technology, engineering, and math. You remember that program I told you that I was in 5th grade with Mr. Hargrove, Mesa? I was a Mesa counselor when I was in college. And I used to talk to those kids about making balsa wood bridges. This is about making mousetrap cars. You see the mousetrap in my hand? It's got an antenna on it to make lever arm. We can build mousetraps later outside. They got supplies down the road. So she and I traveled all over California doing that while we were in college. And we traveled so much that we started dating, and now we are married and we have 4 kids, 4 daughters we're blessed with. And I'm very grateful for those days. This is something that's always been important to me. I've loved doing this from as early as I can remember. That other picture is graduating. Again, I went to college and I met her, so the most important thing I got out of college was my wife. But I also got my degree. I went to college and I finished what I started. It's important to finish what you start. And so I left Cal Poly. I was in the Navy, joined the Navy. I got commissioned in 1999, got my wings in 2001. And that picture with all those guys in the green is the first time we took the venerable F-18 to the boat to learn to land it on an aircraft carrier. That's my first time being on an aircraft carrier. What a good memory. And then I showed up into a squadron and got to fly this machine for 3 years, living in Virginia Beach. This is a picture from Operation Iraqi Freedom. This is over a region where we would air refuel, and so I was air refueling, and the guy in the back had a camera and said, hey, pop a flare and I'll take a picture. So that's a great picture, a great memory from that time. 2004, summer to fall of 2004. And then I left there and I got to go to test pilot school. I went back to school and I spent a year learning to test aircrafts and systems, computer systems and weapon systems. I got to be a test pilot for 2 years, and then I went back to school again, the Naval Postgraduate School. And I took a master's degree part-time. And then I went to school full-time. The Navy sent me to study politics and information and military use. and I went to, we call it War College in the military, so I went to school again. And then when I finished that, packed up the family, and we moved to Japan, and I went to another squadron. I flew on the George Washington for 2 years, deploying with some folks that are here in the audience, and 2 great years of our lives. And this is a really special picture. One of the guys that worked on our airplanes in that squadron took this picture of me landing on the boat. And so I'll just describe to you, there are 4 wires on the carrier. We generally aim for number 3. And I will tell you, in this picture, I landed on number 3. So this is a good landing. Actually, you'd see there's no wire there, though, underneath the tail of my airplane where the hook would be. Because we land on it so much, they have to replace them, and so they had taken it off this day. But that was a pretty good landing. So this is a special picture, though, not because of where the airplane touched down, even though that's important. It's a good picture because this was one of my last carrier-arrested landings, and I left there to come here to D.C., and I didn't know that I was going to get this job, so that's actually one of the last times I will ever get to do that. So, very special picture for me. So I moved to Washington, D.C. I decided instead of working in the Pentagon, I was going to apply for something, do something very different, and I got to go work in the Capitol. And this was one of my favorite days. I was sitting at my desk doing my work, and I had some free time. I called up Congressman John Lewis's office, a civil rights icon, the only living speaker from the March on Washington for Jobs and Freedom. You know what that is. That's where Dr. Martin Luther King made the I Have a Dream speech that changed this country and the world. He was a speaker there as well. He was a college student and leader of a movement called the Student Nonviolent Committee, and he got to speak that day. So I got to go over and meet him and just pick his brain, ask him questions. He took me out on his patio, and we had a great conversation. Then he did the same thing for my daughters. What a great experience, and what a great man. A pioneer, no less, a pioneer. And so I worked for this gentleman, and I spent, it was a year-long program. Can you advance that for me? I'm having trouble. I worked for this gentleman, Senator John McCain, a military veteran. He was a POW and now a senator, was a congressman, now a senator. And I learned a lot. One of my favorite days there, well, this was a great day. After we found out we got selected, a few of my classmates that were in the area, we got to go, and he took a picture with us and got to sit and talk to him about NASA in the future. But he brought my whole class together and talked about leadership. And I got to ask him some tough questions, and he got to talk to my entire class, 17 of us, about leadership and about telling the truth even when it's tough. And that was a really inspirational day. And so I was doing that when I got selected. I don't know if my batteries are running out here or what, but next slide. I was there in D.C. when I got selected for this job. And I threw these pictures together because I could just sit on this slide for the whole hour, because those folks are all, and I could throw more pictures up there. There's a Tuskegee Airman in there. There's one of my Mesa advisors from Cal Poly, my academic advisor from Cal Poly, and of course my family in the middle. That picture with my wife and my daughters and that beautiful F-18 in the background, that's like everything important to me in the world. Not because of the airplane, but that F-18 represents a squadron, which is 250 people that come together in any climate, in any place, to do things that you all need them to do, and that is an amazing thing to be a part of. So all of you service members in the audience, thank you for your service as well. So all of those folks helped me to make this next picture, next slide, a reality. Next slide. I got to go from Congress to NASA and begin this journey of becoming an astronaut. Next slide. My class showed up in August, next slide, of 2013 to begin astronaut boot camp training, astronaut candidate training to become an astronaut. And it's amazing training. We showed up and we started right away into the 5 basic competencies that you have to have in order to be an astronaut. Is that working? Because I'm going to need it. Okay. Next slide. Next slide. That says Меня зовут Victor. That means my name is Victor in Russian. We all had to learn to говорить по-русски, to speak Russian. Can anybody imagine why we have to speak Russian in the astronaut corps?
We don't have any rockets to go to space.
We do. They're Soyuz rockets, and we ride with the Russians. Yeah, and that vehicle is made by an aerospace company in Russia, so the buttons, they're in Cyrillic, they're not in English. So we have to learn to read, speak, and hear over the radio in Russian. And we have to learn technical things in Russian as well, so the language training is very challenging. I try to do about 6 hours a week. That stretches your brain. It's very challenging. Next slide. We also have to learn International Space Station systems, because if the toilet breaks, who do you think has to fix it? Whoever broke it, that's right. So, you know, you can't call a plumber though. We don't have space plumbers yet. Maybe one day we will. When we work and live in space now, you guys. Anybody here 16? Everybody 16 and younger, raise your hand. Everybody else, look around at these hands. Humans have worked and lived in space continuously longer than all of these folks have been alive. We started living on the space station, thank you, for November 2nd of 2000. So in November 2nd of last year, we hit 16 years continuous. And so we are beyond 16. We're working on our 17th year of continuous human presence in space. That's a big deal. Whether it's on CNN or MSNBC or not, that's a big deal. So thank you, NASA. But that's why you have to learn ISS systems, because when something breaks, you have to fix it. It also helps you to become a capsule communicator. The people that when they, Houston, I lost my toothbrush. They're talking to a crew member or an engineer who has also gone through systems classes, so you know, hey, it's probably over there by the vents, because everything floats and it sucks down to the air conditioning vent. Next slide. That's a picture of my classmate, Drew Morgan, who is an Army doctor who graduated from Ranger School. You think he knows about telephone repair? This is us repairing a telephone on the International Space Station. So no matter what you did before, school teacher, doctor, scientist, engineer, pilot, you're going to find something in this that's going to stretch your brain. This is working on robotics training in Canada. The Canadian Space Agency built the robotic arm on the space shuttle and the one that's on the space station. And we have to learn to do lots of different operations, from putting a crew member on the end of it when they do a spacewalk to grabbing cargo vehicles. When we launch cargo to the space station, it has to catch the space station. If I want to send this science machine up there, or this bag of apples, it's on the ground right now, not moving. Well, I guess technically we're all moving through space, but you know what I'm saying. It's got zero velocity right now relative to the ground. And the space station is going, anyone know how fast the space station goes around the Earth? Kids, how fast? Really fast, yeah, really fast. 17,500 miles an hour. And so that apple, we have to accelerate it to 17,500 miles an hour. And we do that in these cargo vehicles that get up there and they phase and they do altitude burns and they get up close to the space station. And then some of them, we put it on autopilot and it coasts next to the space station, flying formation like we do in our military airplanes. And then we take that robotic arm and we reach out and we grab it, bam! And then we stick it onto the space station, pressurize it, and then the astronauts can open it up and get the food, pictures of their family, science, hardware, and clothes out of it. Pretty neat. That's one of the things we do with that robotic arm. It's like flying an airplane and using a computer at the same time. And one of my favorite parts of the training, learning to spacewalk. Proof that astronauts put their space pants on one leg at a time. These pictures I like to show because even as I zoom in here on the different phases of getting suited up, getting put in the water, you see I'm not alone in any of these pictures. And you're probably looking at this one thinking, well, he doesn't realize that picture of him right there is him by himself. But if you look in the lower left and right corners, those two spots are divers under the water waiting for me to get all the way under the water so that they can go to work. They weigh us out so that we don't float or sink, but they also make it so that we don't have riding moments. If I were to twist on my side in space, there's not an up and a down. So if I need to get underneath there to, drill in that bolt, I can just go like this, whoop, and now I stay on my side underwater so that it simulates space. It's this was the most fun part of the training for me. I had never done anything like this, and this is a great part of the training. Tons of fun. And so we get underwater and we practice repairing things, replacing computers, pump modules, and other hardware on the space station so that we can work to keep the space station that's in orbit 250 miles over our heads running and working so that we have that lab in space. This is a time lapse of about a 20 to 30 minute period of us putting on the suit, getting pressurized, putting all the tools on, and then initially getting put into the water. And I like that video because it spans the pool deck and you see just how much activity. Just for the two of us, this is my classmate Nick Hague and I getting suited up and getting in the water. You see how many people are on the pool deck? Dozens of folks. Like Scott Kelly said, human spaceflight is the greatest team sport on and off the planet. We've got an amazing team. So, when you finish all those things, I'm sorry, the last one, T-38 flying. I'm a pilot, how can I forget that? Again, no matter what you did before, you could be a scientist or a school teacher or a pilot, you're going to become a fully qualified member in the T-38. This is our afterburning twin-engine trainer aircraft that we fly, and it teaches you to operate in a physiologically challenging environment. You can be upside down, but the blood's not going to run to your head if I put 1G on the airplane, and your eyes see the ground upside down, but your body says I'm upright, and so it can cause your senses to be confused. Sound like anything you heard of? Going into space, right? And we have to use controls while doing other things, pushing buttons and following a checklist like those robotic operations I was telling you about. And you also have to talk to the crewmate in the back and work together on the same thing. It's like living with a crew on the space station. And you also have to talk to people that are far away. Air traffic control towers. It's like being on the station and saying, Houston, station, I lost my toothbrush. You have to get used to talking to folks that you're not in the same room with. And so everybody becomes a fully qualified member in the T-38, and that's a great shot of a bunch of us, 8 of us flying a formation for one of our remembrance days. We fly over the tree grove where we plant trees for astronauts who have passed on, and we do a missing man formation. So this was a very special day. We do that for them every year. And once you get done with that, you become an astronaut, a member of this great team of explorers. And I like to say we're ambassadors of the NASA vision to reach for new heights and reveal the unknown for all humankind. Those are great words. I love those words. Does anyone recognize this picture? That is an actual photograph. Shout it out if you think you know what's in this photograph. There is a moon in that. That moon has a name. It was popular 2 summers ago. Anyone remember the New Horizons mission? Okay, so another one. Everybody who is 10 years old, raise your hand. 10 years old or younger, raise your hand. We launched a spacecraft into space. It was going really fast, 30,000 miles per hour. And it flew your whole life. It was doing that speed for 9 years to get here, to take that picture. The first high-resolution images of Pluto, that's Pluto and its moon Charon, were taken by the New Horizons spacecraft. And it was taken, the reason I tell you all that, this picture, the first up-close images of Pluto were taken on the same day that my classmates and I graduated from astronaut candidate training. So that's a very special picture for me, and so is this. That's my class, the 2013 astronaut class. And you notice, NASA did something for the first time when they picked our class. There are 4 men in that picture and 4 women. First time in history they've done that. Yeah, that is worth applauding for. I think that was awesome. That's right. I have 4 daughters, by the way, okay? I do think that is awesome. So we showed up, we finished training, and that's all of us graduating, all smiles, good times. And we became a member of this great group of explorers.
5, Roger, you're looking good. 3, 2.
Explorers. We have a need to find what is out there. It is a drive inside each and every one of us. The drive to wonder, to push the boundaries, and to explore. We expanded across our lands, settling new frontiers. We took to the oceans and learned that we could cross treacherous expanses in the pursuit of discovery. And then we took to the skies and flew. But that wasn't enough. We left the planet and redefined what was possible. We flew in space. We walked in space. What once was a melodramatic flight of fantasy became reality. Then, a new generation of spaceships captured hearts and minds for 3 decades and helped build a castle in the sky that is our lasting home in space. We have always looked up. For centuries, we wondered what was on the other side of the sky, and we have begun to answer that question. We have learned that all the exploration humankind has achieved is only a beginning. Right now, men and women are working on the next steps to go farther than we have ever gone before. New vessels will carry us, and new destinations await us. Everything we have ever accomplished leads to this moment in time, where exploration will now take us to the planets and the stars. Our nearest neighbors in the night sky have beckoned us, invited us, dared us to reach for them. We are the explorers. Throughout our history, we have taken both small steps and giant leaps in that pursuit. Our next destination awaits. We don't know what new discoveries lie ahead, but this is the very reason we must go.
I love my job. Who's ready to go? I love that video. Anybody recognize the voice in that video? Who was it? Wow. Okay. Okay. What voice does Peter? Optimus Prime. That's what I was expecting. It is Peter Cullen's voice as Optimus Prime. Yes. Wow. Okay. We need to talk. I hope you want to be an astronaut too. Yes. Very special. So we became a part of the astronaut corps, and I'm living this dream job. It's an amazing and humbling and challenging and exciting, and did I say humbling and challenging and exciting experience. And so those are some stories that I thought, might mean some things to you. But remember, kids, talking to you, it was about connecting with something. And I told you earlier some things that you could be now and forever, and that you should try to be. Anybody remember any of those? What was the first one? Be gritty. Number 2, be a lifelong learner. Oh, I love it. If I could get my kids to do this. What was number 3? Be a good person. So, I'm going to just give you a couple little specific things that I think are important about those. So, being gritty. What does that mean? It means work hard. And I know you hear that. Your parents tell you that. Well, I'm telling you again. Work hard. Not just at the things that you like, especially at the things that you don't like. The greatest obstacles that I have encountered in my life were when I didn't believe in myself. Yeah, I've had external obstacles, but those haven't been as tough as I've been on myself. And if you recognize that, it makes you look at the obstacles that are out there in a different way. You can do anything if you put your mind to it. I love this saying. Someone said it to me once, and I take it. I run it through my head every day. Get comfortable being uncomfortable. Do any of you get nervous if you have to make a speech in front of people? Come on, hands up. Let's be honest. Come on. Because there are some kids maybe that feel that way, and you grown-ups admitting it will help them realize it's okay. My hand is up not to encourage you to raise your hand, but because I get nervous as well. But you know what? I practice. I practice. And if you practice, get your little brother or sister, make a speech. Get mommy and daddy together. Give them the speech. Tell your teacher, hey, before I do that presentation to the class, can I just show you? Give them the speech. And by the time you've done it enough, you get comfortable. You know your stuff. And you're going to get up there, and guess what? Those butterflies are going to creep up. You're going to get nervous. But you know what? When you focus on something and you train, you get better. What you put your energy into, you get better at it. And you'll get up there in front of the class, and the butterflies will come up, and those butterflies will fuel you to fly. And you'll be good at making speeches, even if it still makes you nervous. If you could see up close, my hand is shaking. But it doesn't bother me. If you've seen the movie or read the book, The Right Stuff, that's really what it's about. Being able to work through challenges. So go after those things that make you nervous. That's what being gritty is about. Being a lifelong learner. Next slide. This thing doesn't like me. Being a lifelong learner. Next slide. First and foremost, you heard me tell stories about folks who helped me find confidence, who find a path, find a major, and boy, I'm not going to tell you I listened all the time, but I listened, and I'm so grateful that I did. I look back and I go, I should have listened to a whole lot more. Would have saved myself some headaches. Listen, you've got parents, they brought you here. You've got teachers and guidance counselors, ministers, pastors in your church. You've got Boy Scout leaders. You've got team coaches that are all concerned about you and your development. Listen. Next slide, or advance one, please. Another thing you can do to be a lifelong learner is to learn a foreign language. Yes, Russian, Chinese, learn to speak Spanish or French. But also, I lump learning to computer program into that category as well. How many of you are walking around right now with a smartwatch or an electronic phone in your pocket or a gaming device? You ought to know how the inside of that thing works. And you know what those machines actually speak? It's math. Computer programming is just a specific kind of math. So I encourage you, if you're really good at math, if you're doing that kind of math where there's not a lot of numbers and there's a whole lot of words, you're fluent in a foreign language or another language. Advance one, please. For those of you that are still in formal schooling, and being a lifelong learner is about connecting formal schooling and informal schooling, what you learn out in the real world with what you learn in the classroom. And when you synthesize those things, they call it experience. And when you have a lot of experience, they call that wisdom. And who doesn't want that? One of the keys to succeeding in a formal setting is review. If you're in the grades where you have one class all day, if you take 5 to 10 minutes to review that stuff, if you have something hard, you're going to be good at it. You're going to be one of the best people at it. If you have, say, high school 7 classes, 5 to 10 minutes per class would simply be 35 to an hour and 10 minutes. And if you put that time in, you can bring your grades from average to excelling. And here's some specifics on what I would do. You take your notes that you wrote, and maybe you write like me, chicken scratch, so I can't always read what I wrote. So do you think I'm going to remember it a week from now or at the end of the semester? Nope. That day I need to go through to make sure I can read it all. And what I can't read, electrophoresis. Okay. Rewrite it. And then while you're rewriting it, you're reviewing it. You're running it back through your mind. And you get to that part, I don't remember what polymerase chain reaction actually means. Circle that. And then you go to class early and you tell the professor, the teacher, I don't remember what the polymerase chain reaction is. And when they explain to you how important that is to being able to do DNA sequencing, now it's stuck in that brain. You just did 2 things. You did 2 things. One, you filled in that gap of information because the teacher's then going to move on to the next subject that builds on that. You did something else that is equal, if not more important. You showed that teacher that you care. Those educators in the room, raise your hands up again. When the kids come to you for questions outside of class, do you remember those kids? You generally say things like, boy, that Billy is smart. Boy, Susie is smart. Boy, Jordan is smart. So, it's two important things that you're getting done. Next slide, advance one, please. And be a good person. And it's weird to go in. I'm not the judge of what it means to be a good person, but I can tell you some things. If you ask yourself, what would my mama think of this? What would my grandma think about these decisions? You're probably going to make better decisions. If I was up here telling you not to listen to your parents and don't study and to eat garbage and to not work out, sit on your butt and watch TV and play video games instead of making the video games, my grandmother would not be happy with that. And it's on TV, so she would know. I'd get a phone call. What would your grandmother think? That's a great question to ask yourself. Next slide, advance one, please. It's about making healthy, rational choices. It's about putting good things in your body and about good things coming out of your body. It's about getting a good night's sleep. It's about learning and advancing and not being too big-headed to grow and to learn. Healthy, rational choices. Next slide. It's about practicing etiquette. I tell my kids, etiquette is respecting the people around you. Yeah, it's a bunch of things I want you to learn and to understand. It's not about just putting the knives and the forks and the cups in the right place. Okay, bread, meat, water, which one is mine? It's about understanding that those people sitting next to you, maybe they're going to have a conversation or maybe they're doing something that you need to be respectful of. Practicing etiquette, like anything else, what you put your energy into, you get good at. Working here on the Hill, working in Congress, I saw how important things like handwritten notes were. Very important. Things that we don't always think about. We're quick to send a text or to leave a message or an email, electronic mail. But a handwritten note stands out. I know people who got jobs because they wrote a handwritten thank you note to the person that interviewed them. Etiquette and teamwork. Boy, how many times? Human spaceflight is the greatest team sport on and off the planet. And we spend a lot of time trying hard to take care of ourselves and to take care of each other so that we can together accomplish a mission. And you have to practice that. It's not something you're just going to show up and be good at on day one. Next slide. And the last one, and to all the service members, first responders, and all of you parents, you do this every day. You serve something bigger than yourself. And for you young folks, look for that thing. I'm not going to stand here and tell you to follow your passions. I'm going to tell you, find a way to serve. And when you put your energy into doing something else, you are going to grow a passion that you'll keep for the rest of your life. Thank you for your time. Thank you for coming. One more slide. One more slide. Some websites that you can go to and get more information about the missions, the science going on in the space station, and what we do, some of our educational initiatives. Now, while that sits up there, if you have questions for me, there is a microphone here. Yes, you have to stand in the spotlight. But please come forward, ask questions. I would love to take some of your questions. I'm going to ask you questions. There is a quiz if you don't ask me questions. Come on up to the microphone. It's on.
Okay, fine. Wonderful. Thank you so much for sharing that story, especially about the things that you did early on that helped you succeed to where you are now. To people that are in college or have already maybe had some of the experiences or have gone through elementary school and high school and all that, what would you tell them as they move on to the next step of their life post-college that helped you continue building on your success?
Go back to that slide. I think those things are all still applicable. But I would say this, whatever it is that you want to do in life, if you love music and art, it's so important, especially as we now live in space. We need to take more parts of our culture. We don't, humans don't live by, bread alone, right? It's not just about the food and the toilet and the life support systems. You want music and games up there with you, and so those things are important. While you're in college, you might want to go and be an artist, a singer, but you know what? In a technical education, I try to stop saying STEM. It's become a thing, but you can't get a degree in STEM. But science, technology, engineering, and mathematics will serve you no matter what. Like I said, we're all walking around with some type of an electronic device. You ought to know how it works. If you want to, I ask kids, do they like math? And some hands go up. I say, do you like money? Well, people who are good at that other thing usually keep more of that other thing. So, there are lots of ways to skin that cat. If you study math and science, no matter what you want to actually do in your career, those things are going to serve you. So that's one. And here's another. If you do go into the technical workforce, you saw a picture up there when I was working on the Hill. I found that technical folks, the science and technology workforce, generally tends to be a little bit ahistorical and apolitical, meaning they're just not into it. They don't like, it's not about politicians. Politics is about the will of the people, our structure, our roads, our water system, the things that we share collectively, and it's important to follow along and understand how those things work. Read long-form journalism. I could give you some names, but I might get in trouble with some good things to read, but long, well-written articles, you can't get all your news in social media. 140 characters just don't cut it all the time. So you have to read things that are written by people who have a specialty. Afterward, ask me when we're off the recorder, and I'll give you some things that I think you could find out about what's going on in the world. And yeah, great question. Thank you. How old do you have to be an astronaut? Wow, I think we've had folks selected in their 20s. So usually a college graduate. Most of us, though, are in our 30s when we're selected. So I know you're thinking, wow, that's old. Yeah. I'm thinking, I love it. Honesty. I'm thinking, that's pretty young.
Yeah. Good job.
Good question. Thank you. Yeah.
Have you ever lived in space?
I have not yet. I am waiting to be assigned to a mission. When they ask me if I'm ready to go, I'm going to say, yes, let's start this training, and I'm going to go up there and hopefully live on the space station for 6 months. But not yet. Maybe soon. Okay, I've still got my quiz. I will ask you questions. How fast is the space station going around the Earth? 17,500 miles an hour. Okay, they're going to get harder. So how fast does it actually go around the Earth? How long does it take? Spit it out, come on. 90 minutes. So, how many times a day does the space station see the sun rise and set? Carry the 1. 16. And we love sunrise and sunset, don't we? Don't we? Like, it's a special thing when you can actually sit and watch. They're not just sitting watching the sunrise and set, but sometimes when they have free time, that's what they want to do, is look out the window and take pictures. That's what they say. Yes, sir.
Thank you for your wonderful, enlightening presentation.
Thank you.
I have 2 questions. One is, what is the most challenging obstacle you overcame as a teen and as an astronaut? And secondly, what is you view your future?
My future. Great question, sir. Thank you. Greatest challenge as a teen, greatest challenge as an astronaut, and what do I see in my future? As a teen, It was ignorance. It was myself. That's something that I did inside. I'll tell you a story. I didn't put it in this talk. I could have just sat on that one slide of all those people in those pictures for the whole hour. I was a pretty decent athlete. I was the athlete of the year in my high school. The Marine Corps gave me an award for that. And then the Naval Academy recruiter came to my house and said, "Do you want to play football at Annapolis?" I said, "No, thank you." And then not long after that, the West Point recruiter came and said, "Hey, do you want to play football at West Point?" And I said, "No, thank you. Not interested." And Annapolis actually came back and said, "Do you want to wrestle?" I did pretty good my senior year and was all state, and they said, "You want to wrestle at Annapolis?" You know what I said? "No, thank you." And I'm standing here before you, a naval officer and a naval aviator, and I gave up that opportunity to go get a free education at an equal to an Ivy League institution. And but it was because of my ignorance. I wasn't exposed to that, and I didn't know what the opportunity on the other side of that was like. And so I tell that story often, though, because it was me, 16, 17-year-old me, that just couldn't see it. But everything happens for a reason. Everything happens for a reason. Greatest obstacle as an astronaut. This opportunity is unique. It's amazing. I got the phone call standing in the Russell Senate Office building. I was in the rotunda where you see all the senators getting interviewed. I was standing in there when astronaut Janet Kavandi asked me, "Do you want to move to Houston and start training to be an astronaut?" And there's only one answer to that question. Yes! But that decision also meant leaving the Navy full-time. I'm still an active duty Navy officer, but it meant leaving. I've got friends in the audience that I served with, and my first squadron, he was my intelligence officer, and my best friend and a naval intelligence officer. He was the guy in that picture in high school with all the hair. That was him. Good to see you, brother. Leaving my Navy family has been the greatest challenge of this astronaut journey of mine. Hi. Do you have a question for me? What is your question?
How long does it take to the moon?
How long does it take to get to the moon? That is a great question. So, I'm not a rocket scientist, okay, but I play one on TV. So, I believe the fastest thing that we sent to the moon left Earth. So when you see the big fire coming out from liftoff, it wasn't going to the moon, it was going a lot farther. It passed the moon 6 hours later. 6 hours. Anybody remember, did I say it earlier, how far is the moon? 240,000 miles. Was it cooking? It was cooking. That was the New Horizons vehicle that was going to Pluto. It had to go that fast because it had to get all the way to Pluto. It passed the moon 6 hours after takeoff, I believe. Maybe it was 8 hours, but it was very quick. When we send astronauts to the moon, it's a couple of day trip. So it depends on what the mission is and what's going and how much stuff has to go with it. So anywhere from a few hours to a couple of few days. Good question. You're very welcome. I've got more quiz questions. All right, and this one there's no answer key for. What do you think one of the biggest challenges folks have in adjusting to living in space is? This is obviously something that changes. This isn't like a hard and fast thing, but sir.
Well, I'm pretty sure it's like zero gravity affects how you grow.
It does affect how you grow. You actually gain an inch or two when you go up there.
I get nauseous a lot.
Ooh, getting nauseous. That's you do get the adjustment period where you feel congested, you feel your stomach awareness. Yeah, you may be getting nauseous. This could be a long-term thing though. That you may adjust to over time. I used to think, when you see those commercials on TV for a new bed, what do they tell you? This is made with the same technology that NASA uses. Yeah, And you're like, oh man, floating in space must be the best night's sleep. And sleep, for some people, it's great. And for some people, that's one of the toughest things to do. But think about this. So yeah, you're probably floating and you're feeling like, oh, that's a great position. But here, when you get in the bed, the cool sheets, that's a sensation that you're used to. Laying down. I'm standing, the pressure's on the bottom of my feet, the blood is being pulled to my feet, my heart's pushing it around. When you lay down, all of that changes. Your body senses all that. The somatosensory, the tactile sensation of laying, all that pressure along the side of your body. We try to simulate that by strapping in a sleeping bag into your crew quarters, and then you kind of just strap yourself into it so that it holds you up against a wall, but you can't lay down in space. Think about it. So, sleep is one of the more challenging things to do. The other one, using the bathroom. We won't talk about that.
How long does it take to get to Saturn?
I'm sorry, sir?
How long does it take to get to Saturn?
How long does it take to get to Saturn? Probably not 9 years like Pluto, because it's a little bit closer. But you know what? You want to find out? Let's ask someone exactly and see if we can get ourselves an answer here. Let's see. Siri, how long does it take to get to Saturn?
Okay, give me a moment. Here is what I found.
6.05 years. That's what Siri says. But you know what I think you should do? You go look it up and you tell me when I come back. Deal? More questions? Well, listen, out of my etiquette for your time, if you, okay, please.
I want to talk to people about space exploration and the benefits for actual people on Earth, mankind. What do you tell them about that? What do you, especially recently, have we been discovering more things that have a direct impact on our lives on Earth?
Absolutely. It depends on how much time they have. As you can see, I like to discuss this kind of stuff. You know, it's kind of interesting to me. So one of the things that we have working on the space station, the experiment going on is this protein crystal growth experiment where we can grow very nicely structured and much larger protein crystals. And what that enables us to do here on the planet is to make chemical therapy medicines that are better and more suited for whatever it is that you're taking it for. So that's the pharmaceutical companies are very much interested in is it feasible to manufacture things in space, or at least what we learn about them in space, can we make better materials here on the ground? Here's another one, astronaut health. We are one of the primary research objects up there, and bone health. You've got this cortical and trabecular bone, sort of the hard outside and the softer inside, like the marrow on chicken leg, you know. So those two parts of your bone, they go away and come back at different rates, and we were finding astronauts were coming home with less dense bones. So we developed a chemical therapy, some medications that they can take. But the biggest thing is we've changed our exercises. We have a machine that's like a big weight machine, and you got to lift heavy. Right before you come home for landing, you are lifting heavy weights, up to 600 pounds, and it's a vacuum tube because there's no weight in microgravity. But you've got this weight protocol and a running protocol. We actually started sprinting because they found that the heel strike helps your bones to stay more dense. Well, guess who really cares about that? Half of the world's population, women, osteoporosis. Yeah, so that research is going on right now, but I can guarantee you those things are being fed right back here on the surface to help folks on the planet deal with bone health. Yeah, lots of good things. And those websites that I put up there, you can read about as much time as you have. You can spend it reading about the missions and going on the space station. Good question. Thank you. Hi.
Hi.
Do you have a question?
Yeah.
What's your question?
How does it feel to be in a rocket ship?
How does it feel to be in a rocket ship? Well, I haven't been in a rocket ship. I've been in a spacecraft, and you know what? It's unreal to know that something you're in is going to go into space. Very unreal and cool. Great question. Thank you for the question. Okay, so I think they're giving me the signal that we have to wrap it up. Thank you for your time. Thank you for coming out and allowing me to do this. Really enjoyed it. Thank you.
This nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth.
Godspeed, John Glenn. All systems are go. Roger, 0G, and I feel fine.
We choose to go to the moon in this decade and do the other thing.
focus of the entire project landing successfully on Mars.
That will be put in an orbit and provide living space for astronauts and particularly astronaut sciences.
Contact. I'm using the polar shaking hands now. America's first space shuttle. And the shuttle has cleared the tower.
Nothing as beautiful as Chandra sailing off on its way to work.
We've had an excellent week on Mars.
Houston, Atlantis, we have captured.
After World War II in 1946, a group of 118 scientists from Peenemünde, Germany, came to America under Operation Paperclip to continue their work on rocket research. They were headed by Dr. Werner von Braun at White Sands Proving Grounds, New Mexico. Eventually, over 3,500 German scientists are brought to the United States. But at the same time, 6,000 German scientists, or specialists as they were called,
moon map.
reactivate this reservation that was there. And that was the first time that it became general knowledge or began to spread at all. But still at that time, the individuals were not well known. Werner was not a name to the American people yet at that time.
General Bruce Medeiros returned during his life to the source of all things, the faith in God. In the very neighborhood of Florida Space Center, he is now a minister of the Parish of the Good Shepherd. At a few miles distance, in Cocoa Beach on the other side of the famous base, Dr. Kurt Debus lives, co-designer, founder and former director of Cape Kennedy. Debus, also one of the 118 from Peenemünde, retired in 1974. In close cooperation with von Braun, he was involved with all NASA projects, Mercury, Gemini, and especially Apollo and Skylab. As the responsible man for the course of events at Cape Kennedy, with 26,000 employees in 1969, he still controlled his brainchild after the Apollo project had finished.
So we had to find a way to transport it vertically, and that is how we execute the total program.
But how can you compare it with the system the Soviet Union is doing it? Because they are still transporting their huge rockets by train.
Well, I do not wish to comment on how the rockets are working.
Okay.
How was it for you to come out of Germany and to start here in America? And,
we were originally shipped over here for exploitation, but then it was recognized that our original intent to go to the west or not to support the east with what we had in our archive and in our heads was recognized, and then we were asked to do something to help the West in building up a new rocket. The Korean War came along about that time, and great hopes was put on the development of a 150-mile rocket, which later became the Redstone rocket.
I know, yeah.
And then we had full support with very minimal means. I mean, for several years we had $5 million or something.
I know.
Yes, it was a very small effort, but it worked out, and the group got busy and started to develop American engineers into our line of thinking.
Unvergessliche Angelegenheit für mich. Wir hatten Herrn McElroy den ganzen Tag hier rumgeführt, auf unserem Redstone Arsenal Einrichtungen und Prüfständen und so weiter. Und etwa nachmittags um 4:30 oder so zog er sich für eine Stunde auf sein Zimmer zurück, um sich zu waschen und umzuziehen. Und wir wollten uns dann zum Abendessen wieder treffen. Und ich ging während dieser einen Stunde in mein Büro rauf. Plötzlich klingelte das Telefon und da war ein Reporter von New York am Apparat und er fragte mich, was ich denn für einen Kommentar dazu hätte. Ich fragte ihn, wozu? Ich hatte keine Ahnung. Und er sagte, ja, haben Sie denn nicht gehört, die Russen haben gerade eben einen Satelliten erfolgreich in Orbit gebracht. Und Sie können sich vorstellen, dass das natürlich das Gespräch des Abends war. Und ich sagte dann dem neuen Verteidigungsminister, er hatte noch nicht sein Amt angetreten, er war noch auf einer Rundreise, um sich zu orientieren. Und ich glaube, er trat sein Amt erst 4 Wochen später an. Ich sagte ihm, wenn Sie nach Washington zurückkommen und Sie finden, dass da die Hölle los ist über diese russische Leistung, dann erinnern Sie sich bitte daran, dass wir binnen 60 Tagen das auch machen können, einen Satelliten in die Umlaufbahn zu bringen. Mein Boss damals, der General Bruce Maderas, der unterbrach mich dann und sagte, Werner, wollen wir es nicht lieber 90 Tage machen als 60?
Yeah, that's one of the best stories around, because it happened that the newly named Secretary of Defense, McElroy, who was taking Mr. Wilson's place as Secretary of Defense, was on a trip around to the various installations to get acquainted and was visiting us at Huntsville, the Missile Command, the night that we got word of the launching of the first Sputnik. The message was delivered to me and immediately to some other people there and began to be buzzed, and Werner and I, as if we had been galvanized by the same spring, we got a hold of McElroy. We practically almost got a hold of him physically. We both of us, I think, felt like shaking him. He was the upcoming Secretary of Defense. And all we could say was, see, this is what's happened. Now, we can put something around in orbit, and we can do it. And we know we can do it, but nobody will let us, and we were on him.
Well, the shock here was fantastic. The shock wave came, we had...
Where were you, Tony?
I was in Huntsville together with Werner von Braun, and the incoming Secretary of Defense, McElroy, was just visiting. And there was a general on my left, and Werner was called out and came back, red head, and he said, Mr. Secretary, the Russians just launched their first satellite. The star went up in the east. And the general on my side said, oh, that little bauble. But it made...
Not General Medaris.
No, on the contrary, but I do not wish to say the name. That little bauble, and I think he would have liked to eat his words later on.
And I still remember that Werner said we could do it in 60 days, and I said, no, Werner, that's too fast. We can do it in 90 days, and we did in 90 days.
Good morning, gentlemen. Be seated, please. I have a very important announcement for you. We've been assigned the mission of launching a scientific Earth satellite. And we will use the Jupiter-C configuration as a carrier that we developed along with the Jet Propulsion Laboratory. I promised the Secretary of the Army that we would be ready in 90 days or less. Let's go, Werner.
Nahmen also die 90 Tage an und wir haben es nachher, glaube ich, nach 81 Tagen geschafft.
Sie haben es eingehalten?
Ja, wir bekamen das grüne Licht nicht gleich, weil Mr. McElroy ja natürlich das Amt noch nicht angetreten hatte. Aber 2 Tage nachdem er Verteidigungsminister wurde, bekamen wir ein Telegramm. Es hieß ganz einfach, go ahead, McElroy.
A moment of triumph for General Medaris and his staff. Werner von Braun and his technicians now try to reduce the Soviets' lead as much as possible. Elsewhere in the United States, people are working on the satellite, which has to be taken into space by the Jupiter of the Army. The leadership is in the hands of James Van Allen. But a very keen competition for the lead in space exploration arises between the Army, the Air Force, and the Navy. The consequences are disastrous. A premature dream of the Navy vanishes into thin air.
I put it this way, that we cannot and will not ever get into this race as we should, so long as all of our objectives are short-term objectives. We've got to have no finite end to our objectives. The end of our objectives should be as far as we can see at any given time, but right now we need a 10 to 12-year program that has as its ultimate goal the manned domination of space. And if we don't, we're going to be in trouble.
When we're clear to start generators. Connect assembly to igniters. Okay, tie down the lead. Roger, install your protective tabs. AFMTC telemeter calibration tape on. Check all operating lights and meters for proper operation. Power panel check. Power panel okay. Control panel check. Control panel okay. Roger. Measuring panel check. Measuring panel okay. Power transfer test on. Observe and record all voltages. Power transfer test on. Once you're clear for launch, clear to launch. Yeah. 021, deflection of jet main number 2. We've either got a relay kicking out or there's something dropping down on the jet main instantaneously here. Hold. Lane 2 is deflected. What do you want to do?
Forget it.
Okay, resume count.
Okay, can we go ahead, Jim? It looks like it. Roger. Instruct arm. Left complete. All right, give me range safe, pass safety. I don't have it yet. Range safe. Range safe. JPL telemetry recording on. Telemetry recording on. UEL recording on. Yes. 20 seconds. Frequency 111, Terry. Roger, Joe. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Fire command. Fire command. Fuel tank pressurized. Launch tank pressurized. Missile power. Ignition. Range safe. Lift off. Lift off.
The lift-off was a success, but it seemed an eternity before the first signals arrived from space that the satellite had reached its orbit.
Hello, Lem. You can send this off to the secretary. That our satellite is definitely on orbit.
The 31st of October 1957 there was an article in a Dutch newspaper that there were 6 satellites ready in the United States to be launched before Sputnik 1. Is that a true story?
No, that's a slight exaggeration. The fact is that the basic...
in Huntsville?
Yes,
in
the basic vehicles were there. We had 6 of the 3-stage vehicles. We had no completed 4th stage, which was the satellite itself, but was also the final accelerator. And so it would not be proper to say that there were 6 that were ready to launch, because even after we did get the word to go ahead, we were on about as fast a time scale as we could have made to do it in about 90 days. To get them ready, finish them off, get some experiment in the satellite itself, get a compatible beeper system in there to communicate with the ground, and test and be confident of the capability of the 4th stage. It took that long. So you couldn't say they were ready. We had the basic hardware, but not the satellites.
We had offered to launch the first satellite a long time, and we had one ready to go. We had a long-range missile based on the same principle, only no satellite in it. No solid rocket stage on that very last end. And I was inspected here whether we had or did not have a solid rocket on that payload. And because one was afraid we would put one in. So over a year we were capable of launching a satellite and were not permitted to. For reasons, General Eisenhower, the president at that time, did not wish to have a military rocket deliver a so-called peaceful satellite. It was the International Geophysical League, and he didn't want to do it. But he was influenced by groups of people, which is pretty well known today. And it was an inter-service fight. The various branches of the services were fighting each other, and so the poor army was standing by with a ready satellite and wasn't permitted to launch it. But I think it was all to the good of the country, because when Sputnik 1 came up and came over the horizon with this beep, which is beeping today in Russia, if you visit Russia, I am told the remote villages, every radio announcer, whenever there's a break, what we have as signs here, that is a beep, 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 reminding how great they are.
I think we had an impressive number of successful satellite and deep space flights during the past year, and I think in the area of scientific achievement, the field of space exploration, we probably have caught up very well. In fact, many people believe that we have produced more scientific knowledge with our smaller vehicles than the Russians have with their much larger ones.
Do you share that opinion?
In the scientific field, yes, sir. But I believe the Russians still have an edge on us in the payload capability, and it is for this reason that it is felt that the Saturn booster is so vitally necessary. The Saturn booster will be at least twice as powerful as the most powerful rocket, Russian rocket demonstrated so far. And if we continue working on the Saturn on an accelerated rate, we feel we have a very good chance of catching up with the present Russian payload capabilities.
Do you feel better now that the President has asked for more money for Saturn?
Oh, yes, definitely.
More secure? I mean...
Well, it's just, it used to be a shoestring program, and now we can really develop a sound program with emphasis on reliability and component testing and all the other things we couldn't afford so far.
Dr. von Braun, how would you say we stand in relation to the Russians, and do you think we can ever catch up?
I'm convinced that in the space field, the Russians are ahead of us, particularly in large weightlifting capability, and that at the moment the problem is not so much to catch up, but first build up the working speed that they have already demonstrated. After we are running as fast as they do, there's still a considerable gap to close, and only the future will tell whether we'll manage to close that gap.
That this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
A gigantic launching site was built on Cape Canaveral. More than $1 billion were appropriated by the American Congress to adapt this out-of-the-way corner of Florida to the building and launching of Saturn rockets. A huge assembling building, large control rooms, 2 launching pads, press sites, and working and eating facilities for 50,000 people were built. In contrast to President Eisenhower, President Kennedy made this development possible. At regular intervals, he showed his personal interest.
On the next flight, we have no useful payload at all. The problem here is nobody wants to entrust a multi-million-dollar payload to a completely unproven launch vehicle. For that reason, we fly the next test, lavishly instrumented for launch vehicle development, but with no useful payload whatsoever. We just have a water tank in the nose.
But there was also great disaster in this tumultuous period in development of the American space program. During a launching tryout on the Cape, the first Apollo capsule was burned out completely. 3 astronauts got killed. The historic Christmas Eve of 1968. Apollo 8. 3 men on their way to another planet. The moon described from very near. A Christmas message to all people on earth.
And the earth was without form and void, and darkness was upon the face of the deep. And the Spirit of God moved upon the face of the waters. And God said, "Let there be light." And there was light. And God saw the light, that it was good. And God divided the light from the darkness.
And then, July 20, 1969, Apollo 11, 2 people set foot on the moon. From Peenemünde to Apollo's Eagle, the dream of the 118 from Germany has become reality. John F. Kennedy's promise of May 25, 1961, redeemed. The end of an era.
30 seconds. Contact light. Okay, engine stop. APA at a descent. Mode control both auto, descent engine command override off. Engine arm off. 113 is in. We copy you down, Eagle. Listen, Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot. Thank you. That's one small step for man, one giant leap for mankind. As the
In his hometown of Huntsville, Alabama, all admiration of the excited spectators fell to Wernher von Braun, who has been the drive behind his American space success.
When I was 17 and started all this, the moon looked a lot closer to me than it did for a long, long time in between. Today it looks again very close, but in the meantime, of course, we've learned a few things. Among others, I've learned, for example, what $1 billion is, something I had no conception for in the early days.
You know, these brainy people I had to work with, they had all kinds of ideas. And when you work with rockets and see this tremendous power set free in a test stand, I think, for what can we use this power? And our idea was to use the power to get up out of the atmosphere in space. We were space fanatics. We wanted to go to the stars. We wanted to go first to the moon. And we talked about it. It's a casino. It's a bowling alley. At families. We talked about it. But we worked on a weapon. And somebody in the German hierarchy decided we should be supervised. And they sent some spies in our private discussions, and they listened to our boasting of our people. They want to go to the moon. And then Hitler said, in a war, talking about going to the moon, they should make the rocket ready for operation at the front and not going to the moon. That is sabotage. They didn't spend their energy for the weapons, they spent their energy for dreams. And therefore Braun and 3 of his boys were arrested and put in jail. It took me I went there to Hitler's headquarters and told him how the situation is. And he said, okay, if you guarantee and vote, give me your oath, that without these people the weapon cannot be finished, you get them free. I did, and I got them free.
Well, I think it does matter a great deal. Remember, I was a very young man in Germany, and I was so busy with my rockets that maybe in retrospect I sometimes wonder whether I shouldn't have worried a little more about some of these aspects. And as I grew older, of course, and saw the ramifications, of course, also the suffering that's involved, you rethink some of these things. On the other hand, I do not believe that I'm all alone in this respect, because I think as I see, the early pioneers in aviation went to exactly the same thing. They wanted to fly, and they tried to find the money wherever they could get it to do these things.
Still, many people wonder whether the technical developments, which were originated by space travel, have contributed to a peaceful society on Earth.
Ich glaube, dass sowohl in der Wissenschaft als auch in der Technologie es absolut notwendig ist, dass ein Stimulus vorhanden ist, der die Wissenschaften und die Technologien zu Höchstleistungen anspornt. Die Raumfahrt hat sich hier, als in den Vereinigten Staaten zumindest, und ich glaube in Russland auch, als bei weitem der effektivste Stimulus erwiesen, einfach weil sie in praktisch alle Gebiete der Naturwissenschaften und der Technologie hereingreift. Sie verlangt von den Medizinern Sachen, die Mediziner nicht können, und von den Materialleuten Sachen, die Materialleute nicht können, von Elektronikern Schaltungen, die nicht konnten und so weiter. So geht das im ganzen Gebiet. Ja. Selbst die Kernphysik ist drin mit elektrischer Stromerzeugung im Weltraum. Und ich glaube, wenn man heute der amerikanischen Industrie und der amerikanischen Wissenschaft diesen Stimulus wegnehmen würde, dann würde das zu ganz katastrophalen Folgen führen. Und ich habe auch das Gefühl, dass in der Sowjetunion genau dasselbe gilt und dass dies einer der Hauptgründe ist, warum die beiden größten Länder der Welt so viel Geld für diese Sache ausgeben.
The more deeply you go into science, the more you're compelled to know that the universe is no accident. And if it's no accident, then somebody planned it. And the existence of a supreme God, to me, is absolutely an inevitable conclusion of a person who really goes objectively into the depths of science.
Yeah, Wernher von Braun turned into a religious man too. May I remind you, I tell you the story about the question, what should be the answer to the problems in the world? There was one day a representative, a reporter from the Christian Science Monitor, who came to von Braun and talked for days in his house with him about these problems in the world, what the answers were. And they didn't come up with one clear answer. And finally the reporter asked him, but I had to write in my paper that you have an answer. What is your answer to all the problems in the world? And Braun told him, you should go more to church and pray more. That will help.
How would you rate his contribution, in fact, to
his contribution
space?
Is enormous. It's very difficult even to limit. His the push he gave his total cause and the ideas he put to work in building these large boosters and in use of space, the satellites, the space stations that he proposed, all of that had a tremendous influence on the development of this, the rocketry and space use.
Throughout that whole command, von Braun with the scientists and the people of technology in the laboratories, and then with the military that had been handpicked to support the other parts of the operation and bring industry in with it. See, we depended a lot on industry. We had a communication net that was superb with the industries that were supporting us. The whole thing was just a smooth, very smooth, well-oiled machine.
He was certainly the most challenging boss to work for and to work with. He is an extremely unusual man in every respect, very outstanding in his talent, in his brilliance, in his flow of ideas, in his capability to be a leader, to produce not only new ideas but solutions to problems which seem insoluble at first. And besides that, he's an extremely pleasant man. I recall that I was sitting with him in hundreds of meetings, and many of the meetings on very serious and difficult and problematic subjects. But I do not believe that there was any 15-minute period in which not all of us laughed heartily from the bottom of our hearts because he had made such a good joke.
I'm very optimistic that man will stay on top of things in spite of the problems that engineers, among other people, create. I think somehow space flight for the first time gives mankind a chance to become immortal.
Von Braun, as I told you already, had one goal in mind, and there was nothing which could distract him from that. And he knew, and he was one of the few really intelligent people who can put their goal far enough in the future, far out in the future, and realize that it can be done. Braun, same as myself, followed this philosophy. When you recognize something as possible, do all you can to do it. All you can. Give everything you have and get your co-workers. You can do it alone. There are hundreds and thousands of modern technology. There are so many questions, so different areas of mathematics, physics, chemistry, and everything, which all have to fall together to solve one big problem, which is far in the future. And Braun is one of these men who did that and succeeded. And therefore, when he succeeded, he resigned. Because nobody can do more than one big world-changing thing than once in his lifetime. His time was up.
40 seconds away from the Apollo 11 liftoff. All the second stage tanks now pressurized. 35 seconds and counting. We are still go with Apollo 11. 30 seconds and counting. Astronauts report it feels good. T-minus 25 seconds. 20 seconds and counting. T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence start. 6.
3 stages, 28 stories tall, with 11 engines as powerful as all the waterfalls in North America combined. Years in the planning, months in the building and testing, the Saturn first stage lived but 2 minutes 41 seconds.
Houston, thrust is go. All engines, you're looking good. Roger, you're loud and clear.
2 minutes 41 seconds. Time to throw Apollo 40 miles up into the sky, and then an empty shell to fall back into the sea.
Neil Armstrong confirming both the engine skirt separation and the launch escape tower separation.
Houston, Apollo 11 and Saturn gave us a magnificent ride. Roger, 11, we'll pass that on, and it certainly looks like you're well on your way now. 11 Houston, your guidance is converged, you're looking good.
Downrange 140 miles, altitude 62 miles.
These are sounds of our times. Called telemetry, it is the way satellites orbiting in space report to controllers on Earth. Each spacecraft has its own signature, a unique tone. Engineers call it data. You may see it later as a weather report or a television picture from around the world. Space down to Earth with application satellites. What they are, what they're doing for you now, and what will be happening in the decade of the 70s. Weather, communications, Earth resources. These will be among the main topics for dialogue in the 1970s. Each has its own type of impact on our lifestyles. At times, we will be more concerned about one than the other, but always they will be there. Case in point, weather. Spacecraft like Tyros, Nimbus, and the application technology satellites. satellites that return daily weather information over the entire world. What do they report? A continuous watch of the Earth's moving cloud cover, tracking storms, measuring winds, recording temperatures at different heights, and testing the moisture content of the atmosphere. As a result, computer systems are built that can receive and analyze vast amounts of global information from many sources, making forecasting more accurate. Hurricanes, with their devastating winds and flood-causing rains, a perennial threat. In 1969, Hurricane Camille was first observed and then tracked by satellite. Because the storm's arrival was predicted accurately enough in advance, it was possible to evacuate people from the Gulf Coast. Without this early warning, the Weather Bureau estimated that 50,000 people might have been killed. In contrast, during Hurricane Laurie in November 1969, observations and tracking by satellite enabled the weather forecasters to predict that Laurie would not strike the coast. It is estimated that $3 million was saved from this satellite-prompted decision not to evacuate and not to protect property. TIROS, Television Infrared Operational Satellite. Over the past 10 years, 20 of these hatbox-shaped satellites have been successfully launched for use by NASA and the Weather Bureau. The television eyes of TIROS scan the entire globe daily, reporting on cloud cover and warning of major storms. Since the first operational weather satellites started clicking off pictures, roughly 600 severe storms have been detected, followed, and predictions made about their course. They have sent back more than 1 million pictures of weather conditions around the globe. Cameras on board the Applications Technology satellite scan the Earth and return color images as often as every 20 minutes. Here's a view showing 6 hurricanes on one picture. This near continuous surveillance of 40% of the Earth's surface has proven so useful that the reports have been incorporated into routine weather forecasts and have pointed the way for even more sophisticated meteorological satellites. Major airlines make use of satellite data in planning their flights. Pilots routinely receive weather photos of their transoceanic routes. Before satellite tracking of hurricanes, U.S. Navy hurricane hunters had to search out the killer storms. Weather satellites now locate the storms, and the Navy flies directly to them to make their measurements. The Navy also uses weather satellite pictures for ice patrols. Remote stations in the Antarctic benefit too. Giant resupply ski planes can be safely scheduled for landings in the icy outposts without worrying about being trapped by snowstorms. Supply ships benefit from improved scheduling as well. A recent satellite in the TIROS series does the work of 2 spacecraft. Carrying twice as many cameras, it's capable of discerning cloud formations as small as 2 miles across. The improved TIROS operational satellite carries a proton monitoring instrument that helps spot solar flares. The same instrument can measure the amount of heat reflected from and absorbed by the Earth's atmosphere. This is very important in weather forecasting. In addition, radio frequencies affected by solar storms can be changed in advance, and manned flights to the moon better planned. Nimbus, research and development craft studying advanced techniques and concepts for meteorological Earth observations. Nimbus is measuring the atmosphere's temperature and moisture at various altitudes, as well as making day and nighttime cloud photographs. These measurements are considered the key to accurate long-range weather forecasts. By the end of this decade,